esteemed chief guest, distinguished members, faculty and students of HBNI, a very good morning. My name is Karunya Devi. I'm a PhD student at HBNI and also a scientific officer at BARC. On behalf of HBNI, it is my absolute pleasure to welcome you all to this discussion meeting on basic sciences, DIMBS 2022. This meeting spans 3 days, and for that duration, I'm very happy to be your hostess. The year 2022 has been declared by the United Nations as the International Year of Basic Sciences for Sustainable Development. It is on this occasion that HBNI is organizing this meeting for the first time with the objective of providing a platform for interaction and catalyzing collaboration between the faculty and students of its 10 constituent institutes and one off-campus center. Without further ado, let me invite the dignitaries to the dais to commence the inaugural program. Firstly, I humbly invite Dr. R. Chidambaram, former scientific advisor to PM, who's gracing this occasion as a chief guest. Sir, please. We also have with us Professor A.K. Mohanty, Director, Baba Atomic Research Center, who's presiding over today's function. Please join me in welcoming Sir to the dais. Lastly, I request Professor Vasudeva Rao, Chairman of the meeting, Professor P.D. Nayak, Co-Chairman of the meeting, Professor D.K. Maiti, Convener of the meeting, to please join our esteemed dignitaries on the dais. Thank you, sir. I now request Professor Nayak to kindly deliver the welcome address.
Good morning to everyone, and thanks for joining discussion meeting on basic sciences organized by HBNI in association with the BARC and TMC. I, P.D. Naik, on behalf of Omi Baba National Institute and my behalf, welcome you all to the discussion meeting. In fact, many of our dignitaries and participants have joined online for these functions, either on WebEx or YouTube platform. I welcome them all. Dr. R. Chidambaram, Omi Baba Chair Professor, former Chairman, Atomic Energy Commission, and Principal Scientific Advisor to Government of India, and chief guest of today's function. Thank you, sir, for considering our request to grace the function. Sir, your presence here this morning is a great morale booster to all the participants of the meeting. We feel extremely honored by the presence of Professor A.K. Mohanty, Director, Baba Atomic Research Center, who agreed to our request to grace the occasion and preside over the function. Professor P.R. Vasudeva, Chairman, Organizing Committee and VC HBNI, Professor D.K. Maiti, Convener of the discussion meeting and Associate Dean HBNI. I'm glad to announce that this meeting is being witnessed by our beloved Chancellor, Dr. Anil Kakodkar. I extend very warm welcome to Professor R.V. Grover, Professor Emeritus HBNI and Founder Director HBNI, Professor R.A. Badwe, Director TMC, Professor B. Venkataman, Director IGCAR, Professor Sudhakar Panda, Director NISER, Professor Gautam Bhattacharjee, Director SINP, Professor V. Ravindran, Director IMSc, who are present here, and also present online, Dr. S.V. Nake, Director RRCAT, Dr. Sasank Chaturvedi, Director IPR, Professor Nanda, Director IOP, Professor J.B. Joshi, Professor Emeritus HBNI, members of Council of Management, members of Planning and Monitoring Board, members of Academic Council, members of Board of Studies, Dean Academic of various institutes of HBNI, speakers of the discussion meeting from various CIs and OCC of HBNI. Many of them are present here. Faculty members of HBNI, staff of HBNI Center Office, and also staffs of various CIs and OCC of HBNI, and our students. This discussion meeting was conceptualized by BC. In fact, the concept behind this meeting were thought long back, maybe 2 years back on other things. But then we had decided this is the right occasion because of declaration by UN as the International Year for Basic Sciences for Sustainable Development. The concepts came from VC for good interactions among the faculty at various CIs and OCC along with their students, so that resources and other facilities available at various CIs and OCC can be utilized by not faculty from same institute, but from other institutes also. I thank VC for this beautiful idea, and he is going to discuss on that in his brief address. Today, all of us are missing the presence of our beloved Chairman, Council of Management, CK and Vyas, because of his busy study, his engagement with other important officer commitment at Delhi, he is not among with us. We received a message from him for the participants. I'm reading it now on his behalf. Quote, I welcome all the participants in my absence here on behalf of HBNI Council of Management and my behalf. First of all, I would like to apologize for not being among you for the important interaction meeting due to my other official commitments. This is the first meeting of its kind where the important research areas and research infrastructures of various constituent institutions and off-campus center of HBNI, popularly known as CIs and OCC, are going to be discussed on a common platform. I wish all the participants fruitful discussions and excellent interactions with their peers from various institutions. One of the main mandates of HBNI is to create an environment for strong interactions among its institutions for generating excellent basic and applied research outcomes for benefit of DAE and society. Although HBNI, along with its CIs and OCC, has achieved success in establishing excellence and harmony in its academic programs, more efforts are required to achieve strong interactions to fulfill the dream of DAE, to see that the potential of all its scientific and academic resources are fully utilized for benefit of DAE and society. This meeting is the first meeting towards understanding the expertise and facilities available at various CIs and OCC of HBNI on a common platform, with a goal to achieve research programs which are not only in particular institute but in joint mode by participation from faculty and research students from various CIs and OCC. And this will give the students with enhanced opportunities. It is apt that this discussion meeting takes place during the year 2022, which has been declared by the United Nations as the International Year of Basic Sciences for Sustainable Development. Although there is nothing like attending personally for the event, I hope that I will get opportunity to go through these deliberations in the coming days. Once again, I wish you all fruitful and stimulating days ahead. Be safe and take care. Thank you all. KNVS. Unquote. On my own behalf, I thank you all and wish you all an inspiring discussion meeting. Thank you.
Thank you, sir. Next, I humbly request the chairman to say a few words about the meeting.
Respected Dr. Chidambaram, Professor Mohanty, Professor P.D. Nayak, Professor Maiti, directors of various constituent institutions and off-campus center of HBNI who are gathered here and also online, senior colleagues and faculty members, ladies and gentlemen. I add my own words of welcome to all of you to this discussion meeting, and I wish you all fruitful discussions and interactions during the event. I also want to wish all the outstation participants, many of whom have traveled after a very long time across the country and who have decided to join us here, a special word of welcome and wishes for a pleasant stay at Mumbai. We will be listening to Dr. Chidambaram and Dr. Mohanty shortly, both of them champions of basic research. So I will be brief in my remarks. There are numerous instances in science history in which what started as curiosity-driven research finally resulted in breakthroughs that led to new processes, products, or technology that were of immense benefit to the mankind. The discovery of radioactivity itself is an outstanding example, because what started as a study of the mysterious rays emitted by uranium compounds ultimately ended up in development of nuclear reactors and numerous benefits to the common man and society. The message of Chairman, Council of Management aptly emphasized the importance of synergy between the basic research programs and the mission-oriented developmental activities in the department. We are well aware that the constituent institutions and off-campus center of HBNI are all engaged in basic research in different disciplines and have demonstrated excellence at the global level. And therefore, we felt that in this International Year of Basic Sciences, we should gather faculty from different CIs and OCC in a discussion meeting to further promote interactions between them and also catalyze collaborations. Also, as a university, I believe that HBNI has to move towards a regime when a student who joins HBNI in a particular CI or OCC for a doctoral degree program, let's say, he can exercise the option to work on problems at the interface of disciplines or work in different environments, part of the work in one place and part in another, utilize experimental and computational facilities available either in his own CI or even other CIs, and even obtain joint guidance for the research work from faculty across the institutions. For this, it is important that the faculty and students are conversant with research infrastructure and research programs that are available in various CIs or OCC. In fact, student mobility and flexibility in pursuing courses are also key elements of the recently declared National Education Policy. Therefore, we hope that this meeting will provide a platform for progress in these directions and pave the way for further interactions. We have accordingly designed this meeting with emphasis on informal discussions and a visit to BRC, especially by outstation faculty, and we plan to organize more such meetings. In fact, considering the specific objective of the meeting and considering the tight schedule, we have even organized online discussion with all the speakers in advance. And we hope that the speakers will highlight those aspects that will provide some sparks for collaborative ventures for mutual benefit. Before closing, I wish to express our sincere thanks to all the seniors who have spontaneously encouraged us to organize this meeting. And we thank Chairman, Council of Management for his important message. And along with you, I keenly look forward to the addresses by Dr. Chidambaram and Dr. Mohanty today, and Dr. Kakotkar tomorrow, and Professor Grover on the day after. So thank you very much.
Thank you, sir. I now humbly invite Professor Mohanty, Director, BARC, to deliver his presidential address.
Good morning to all of you. Respected Chidambaram sir, Honorable Vice Chancellor Professor Rao, Professor Naik, Dean HBNI, Professor Maiti, Associate Dean HBNI, and delegates in the audience, Dr. Badwe, Professor Panda, Professor Bhattacharjee, Professor Rabindran, and so many HBNI faculties, my TC colleagues, invitees, and ladies and gentlemen. I will also be very brief because I'm also eagerly waiting to listen to Chidambaram sir, who will be talking more on the fundamental research. But what I will be saying here, that this is I'll compliment HBNI, particularly Professor Rao and team, arranging such a wonderful meeting, because I have never seen a discussion exclusively on basic science, which has been arranged by them and bringing all the units of the department together under one umbrella. And it is going to be very fruitful, definitely. But as you all know, this year, it has been declared the International Year of Basic Science with a rider for sustainable development. And expectations are much more. I was just seeing what do we mean by sustainable development and which way basic science is expected to solve. And a few lists, if I say, it expects basic sciences as sources of international dialogue and peace. Science as a global public good, innovation and economic development, education and human development, meeting global challenges like energy security, food security, health security, etc., while balancing between economy, ecology, and environment. So expectations are much more. And in fact, for basic science to meet this is also equally challenging. The way I look at the basic science, I generally classify into three categories: basic research. It is a fundamental research, direct or targeted research, and translational research. When I say fundamental research, it is basically a curiosity-driven research generating knowledge. It has no immediate applications. If you ask what is the use of this fundamental research, probably providing an answer will be very, very difficult. Then comes the directed research, targeted research, and it has a target. You can keep a delivery. That's why you can write a project of 4 years, 5 years or something, and at the end you can deliver something, and which directly go to the society. Because we say science for society, this is something you can realize. And translational research, what generally popularly we call it, research from lab to land. And that is also happening. And fortunately, all those three things prominently appears in our DI visions, DI mandate. If you say Vision 8 and Vision 9, it addresses this, basic science and education and directed research. We have been adequately addressing these issues and we are supporting this also. But let me just address one thing, that when you come to the directed research, and it covers both targeted research as well as translational research, it is an object-oriented program. But then I feel that this program, it is like a river. It will flow, but it may easily dry up as soon as a feed, that is a water source, is cut up. And this feed is nothing but the knowledge. And knowledge is driven by the basic research. That's why basic research and all other research, directed research, should go together. And in this context, I will give an example which I personally met or encountered. That is in 2014, when I gave a public briefing about the Higgs boson discovery, God particle. And I was addressing the common people there. At the end of the talk, one gentleman came forward very politely and seriously, started asking me, can I, sir, ask a question? I said, definitely, yes, ask. Then he says, this God particle, which is giving mass to everybody, or the process which is responsible for generating mass, can I patent it? I asked, what for? He says, no, if I can patent it, then I'll use to decrease the weight of the iron. Then I asked, what for? He says, I have a steel furniture manufacturing factory, so that I'll want to reduce the weight of the steel. So what I mean to say, his question is not wrong, but the expectation that science always for the society is always in the mind of the people. That's why he is asking whether it can be used immediately. But then my answer telling, it generates knowledge, knowledge is wealth, probably would not have satisfied him. And in this context, it is exactly happening. Today, we have our, if you know, GDP, 0.6% of the GDP we are spending in R&D. While China is spending more than 2%, Israel is 5%. So when we are limited, because we are a big country, we have many problems. So we cannot spend so much money. So when it is a limited money, it is obvious to ask that if you are doing this or you are spending on this science or this research, so what is the outcome? Outcome, output, budget. Immediately we are talking about it. It does make sense. Then you have to convince people. In this context, I will give an example that long back, his name is Abraham Flexner. If you recall, he was the first director of Institute of Advanced Studies at Princeton, New Jersey. He wrote a very seminal paper. Title is Usefulness of Useless Knowledge. And it refers to the discovery of Maxwell in 1865 about his 4 Maxwell equations, mathematical formulation. That time Maxwell never knew what for he is doing it, 1865. But today, this audience know what is the importance of 4 equation of Maxwell on electromagnetic radiations or electromagnetic theory. Maxwell himself did not know what he is doing for. What is his ambition or what for he is doing. Karmanya badhikarastha mafalisu kadachano. It is exactly fitting into this, that do your job, don't worry about. So when you are trying to search for knowledge, you really don't worry what for you are doing it. But then it has a long-term investment. It pays you. Today, a Maxwell equation, we may not be knowing how we are using. It generates economy. It drives economy, even it can make the economies go down also. So this is the wonderful of the fundamental research, basic research. So this is what happened. We have to convey, fortunately department supporting all of them. And even we are supporting the research in mathematics as well. We are the only department who is supporting mathematics. You know Professor Saha, he is many of you will be knowing, he is the first scientist to become member of parliament in 1952 as an independent candidate from West Bengal. And then I have read somewhere an article, the title says, when the stalwarts adorn the parliament. Actually, it refers to a parliament debate in 1952 in Lok Sabha. Great Ganesh Mablankar was the speaker of the Lok Sabha. Pandit Nehru was in the treasury bench. And in the opposition, there are people like great parliamentarians and stalwarts and orators like Hiren Mukherjee, Shema Pradhan Mukherjee, Rammohan Lohia, S.A. Dange, etc. And they are participating in the debate. Suddenly one gentleman rose up and told, if government of India gives me 4 crores, no question asked, I'll change India into this hub of science and technology. Give me 400 crore, I want to buy the components of the cyclotron. And this is none other than Professor Meghnad Saha. And I wonder today, in our history of democracy, such a debate will be repeating ever again. Probably the answer is no. And then he made the cyclotron in 1952. And he made for basic research. But today we know what is the use of cyclotron. It is a tool for even medical science. It produces radioisotopes. And 1956, Baba also produced the first reactor of Apsara, and that is called Apsara, when it is the first reactor in Asia. So, and much before that, he created fundamental research, Tata Institute of Fundamental Research. So the importance of fundamental science and basic science has been given by this country from the time immemorial, and of course by the department itself. So today, if you see, we are also strengthening these efforts. We have research reactors, we have research accelerators, we are light source, synchrotron light source, and we are putting more money also to update them for fundamental and basic research. We have LIGO in the country. We are participating in international collaborations as well. CERN is an example. We are participating in ITER program. Same thing. You know that we have a 3-stage program. Today, we have to solve the energy crisis. We have to produce energy in a green and clean way. Probably nuclear is the only solution, or definitely it is going to add. The moment I say nuclear, it's not necessarily fission. Fusion also gives a lot of energy. Today, we have a 3-stage program, and we are doing quite well. But I believe that we may have to add one more stage in future. That is fusion research reactor. Technology is getting adapted. And one day I believe we'll able to produce that things like fusion process, which will also be solving the energy problem. Same thing is being asked today, that ITER research is very expensive. 7 countries, including EU, 35 countries, but 7 participants, including India, are participating in this research. But then this research is very expensive, ITER. By 2025, we will be producing 5 megawatt of power at the expense of 50 megawatt with a Q value of 10. And then we expect by end of this century, fusion will also be taking a shape. This is the process which even stars and suns are getting fueled. It is a natural process of creating energy. And hopefully, we will be able to create lots of suns in the earth by the end of this century. And that is the time when probably the energy crisis will be mitigated. And today also, we are not free from questions. Even those who are doing basic science today, they do also ask me, why should you invest in ITER? What is the usefulness of this useless technology? Same question is being asked, but then you know what is the answer to be given. Probably no answer can be given today. So having said that, let me just summarize this meeting, because there will be important. Chidambaram sir will be much more meaningful way than what I'm talking. But I just want to summarize with one saying that 2022 has been declared as the International Year of Basic Sciences for Sustainable Development. This discussion meeting would not only bring out the ongoing contributions of our curiosity-driven research, but also delve into future research programs which can contribute towards solving larger national and global issues such as hunger, poverty, universal health care, climate change, and biodiversity, which are all critical towards a sustainable future for all mankind. Sustaining and supporting basic research activities is of crucial importance in fulfilling this objective. A solution for most of the problems of mankind have emerged from the fruits of basic research, be it antibiotics, vaccines, nuclear energy, communication, etc., to name a few. Wish DIE MBS all success. Thank you and Jai Hind.
Thank you for that inspiring address, sir. Now it is time for our esteemed chief guest's address. So please join me in welcoming Dr. R. Chidambaram to the podium. I request the other dignitaries to please take their seats in the audience.
Importance of basic science. Sharing mode. Okay, sir. Yeah.
Thank you. Professor Mohanty, Professor Vasudeva Rao, Professor Naik, Professor Maiti, participants in this discussion meeting. And I'm very happy to see in person a number of senior scientists, including director. My friend Dr. Badwe is here, because basic research is also very important in cancer. And of course, so many others who are connected online. This is an excellent initiative by Dr. Vasudeva Rao
to hold a meeting on basic sciences. It's a kind of an open-ended brainstorming kind of discussion meeting. And you heard just now an excellent talk by Professor A.K. Mahanti addressing a number of very important issues related to this subject. I thought I'll talk on the importance of basic sciences, and that's why I've given the title of my talk. And as you heard from several people, that 2022 is the International Year of Basic Sciences, declared by the UN General Assembly. And you know, there is, as you all know, International Science Council. There is IUPAC, Pure and Applied Physics, Pure and Applied Chemistry. And the proposal for the year was developed by the International Union of Pure and Applied Physics under the leadership of Michael Spiro, IUPAC president, with encouragement and support of the International Science Council, its many members, partner institutions, and UNESCO. You know, there is also a certain amount of intuition involved in basic research. See, at one time, C.V. Raman was interested why the sky is blue. If he had asked for a funding project, the referees could have asked him, sky has always been blue. Why are you worried about the blue of the sky? Don't you have anything more important to discuss or think about? What new thing are you going to discover? But that is what led him to the discovery of the Raman effect. And today, Raman effect is not just a fascinating phenomenon, also gave one of the early proofs of quantum mechanics. But Raman spectroscopy is a valuable non-destructive chemical analysis technique. The moral of the story is, and I think people who review projects should remember it, the highest intellects must be left free to select research problems of their choice. Don't analyze it too much. They can't explain it. Partly it is intuition which drives them to some areas. Basic science and medicine, it's in all areas. Basic science is in all areas, not just basic chemistry. Focuses on determining the causal mechanisms behind the functioning of the human body, both in health and in illness. That's what the Association of American Medical Colleges say. In cancer, for example, basic research could involve understanding the various aspects of the differences between the growth of healthy cells and the growth of cancer cells. This could be a starting point for proceeding to develop treatment methodologies. Dr. Badwe, I prepared this slide before I knew you are going to be here. Any area you take for example, communications and electronics. The simplest vacuum tube and the diode invented in 1904 by John Ambrose Fleming, it contains only a heated electron emitting cathode and anode. And that was the result of basic research. And today, devices developed from this beginning created the entire discipline of electronics. Quantum mechanics was a fascinating field. Schrödinger equation, all of us know about all those things, and Heisenberg uncertainty principle and all that. But that is what led to the development of the transistor and the laser, many other electronic devices. And recently also to the possibility of quantum computers. They have not yet come, probably next 10 years. Classical computers, you've got only 2 bits, 0 or 1. But in quantum computers, there is a possibility of any number of quantum bits or qubits as they are called. And if it comes, no cryptology, Any RSA code can be broken by a quantum computer. That's why there is also a field of what we call post-quantum cryptography, once that comes. I've always talked about what I call directed basic research. See, directed basic research is not applied research. It is basic research. Deliverable nothing except knowledge generation. But the areas selected are areas we should think maybe you have used technology, foresight to do that. Society, benefit Indian society in the long term, Indian industry in the long term, Indian strategic interests in the long term. It's what I wrote sometime in 2007 in Current Science. And when you are talking of a knowledge economy, all of us want India to become a knowledge economy. An economy, a country capable of producing new knowledge and capable of appropriating knowledge generated anywhere in the world. That's what the developed countries have been doing. And now it has become the diffusion of basic research knowledge because of the internet. See, take Bell Labs. They discovered the principle of the transistor, made money out of the transistor. No longer it's possible. Make a discovery today, tomorrow it's on the net, one way or another, and everybody knows about it. And we have to learn to operate, how to build up our knowledge economy in this context. And I talked about intuition. This is one of my favorites at my mind. You might have seen it also. Enrico Fermi was the only man who had studied neutron cross sections. And when they were building a Hanford reactor, you must know the neutron cross sections of all the isotopes they may be produced. Otherwise, how do you build that Hanford machine? So the method they said was go near Enrico Fermi and you say this isotope, I think this is the cross section of that isotope. If Fermi gets agitated, that means it's wrong. Then you go on changing it. No, sir, I think it's 10 times lower, 10 times more, 10 times whatever. Finally, you reach a stage where Fermi shrugs. Minimum Fermi reaction. Then most probably that is the correct cross section. So this knowledge is not there. You have to go out for intuition. And this is what his student Cronin has written in his... and remember, Fermi was a basic research scientist. And they are building a reactor, Hanford, and they are consulting a basic research scientist how to build high technology system like a nuclear reactor. Plutonium is the other example I found. Plutonium is a very difficult element. It has been called a physicist's dream, but an engineer's nightmare. Apart from its lethal radioactivity, it has a large number of phases. And one of the problems Manhattan Project has, I've told it to Vasudev Rao before this, that it solidifies in delta phase, 15 gram per cc, goes to the alpha phase, 19 gram per cc. Now, if you solidify a material at a lower density and take it to a higher density, it becomes porous and brittle. So the only way they could do was go to Cyril Stanley Smith. He's a basic metallurgist, basic research metallurgist. And he said, what do? We can't make nuclear weapons out of a porous sphere of plutonium. So Smith told them, add a little bit of gallium, it will never go to the alpha phase. He was not working on nuclear weapons, but he had studied the phase diagram of actinides. And he knew, look at the phase diagram, actinides, other alloys, what will happen if you add a trivalent element like gallium to that. That is why I always say, even if you are building a very big, working on high technology project, problems will arise, only basic research scientists can solve them. You must work in an ambience of basic sciences, either in-house or something which is accessible to you from other organizations. Of course, basic science also needs technology support. It works both ways. I think Dr. Mohanty referred to the Higgs boson. Higgs boson was discovered in the Large Hadron Collider. And look at all the advanced technologies which were used in the Large Hadron Collider. Without that, this experiment could not have been done. Similarly, you take our synchrotron radiation sources. To build that, build the beam lines, build the insertion devices, you need to have very advanced technologies. Let me give you some quotes on coming to the end of my brief talk. Some quotes on basic research. Albert Einstein. If you knew what we were doing, it would not be called basic research, would it? Einstein. Glenn Seaborg. Most of my scientific work has been basic research. There were no immediate uses for my discoveries. But today, the radioisotopes are the workhorses of nuclear medicine. He continues. Talks about plutonium at that time. Immediately afterwards, it was used as an energy source in the space program. That is what I have always said. You can't build an advanced technology superstructure without the foundation of basic research. And that brings me to the end of my talk with a quote by Werner von Braun, who was a German-American space engineer. And he says, basic research is what I am doing when I don't know what I am doing. Thank you very much.
Thank you for the invigorating and encouraging address, sir. With this, we are nearing the end of the inaugural session. At this juncture, I request Professor Maiti, convener of the meeting, to propose a vote of thanks.
Okay. Good morning, everybody. It's my pleasant duty to propose vote of thanks. At the outset, we sincerely thank our chief guest of today's inaugural function, Dr. R. Chidambaram, for gracing the occasion and giving a wonderful talk. We express our heartfelt thanks to Professor Mohanty for giving an excellent talk and presiding over this occasion. We thank Director BARC and Director TMC for co-hosting this meeting. Our heartfelt thank goes to all the directors of our CI and OCC for nominating speakers from their institutions and also for participating in this meeting in person. Our sincere thanks for all the speakers, especially Dr. Anil Kakutkar, Chancellor HBNI, who is giving an evening talk tomorrow. Sincere thank goes to all the members of the organizing committee. Finally, we thank all the participants, those are attending in person in this hall, as well as those are participating online through WebEx or YouTube Live, particularly members of Council of Management, Academic Council, and Board of Studies. We express our heartfelt thanks to Chairman Council of Management for sending his message and for his constant encouragement. Thank you all. Now we will start the first scientific session. Before that, I would like to have a couple of announcements. Tea, coffee, water, snacks will be available throughout the day, and there will be no tea break as such. Already we are delayed. Please give PPT of your talk, all the speakers, please give your PPT of your talk to Mr. Anurag and Rishabh, who are sitting there. If you have not given yet, I request all the speakers to limit their talk to 30 minutes so that we have 5 minutes for discussion. There are small changes in the program. Those who are attending online, they can visit HBNI webpage for the updates. First session, also there is a change. First session will be chaired now by Dr. Badwe, Director of Tata Memorial Center. Over to Karunya. Thank you all.
The first session of today will be chaired by Dr. Arup, Director, Tata Memorial Center. I humbly request Professor Bajwe to please conduct session 1. Sir, please.
Oh, yes, sorry. Thank you. Okay, thank you. Thank you, Professor Rao, and Professor Chidambaram, thank you very much for that excellent talk. And Dr. Mohanty, I must say that this is one of the unique platforms that has been thought of by Professor Rao and supported by Dr. Mohanty. And I always believe that if we were to do and change something what we are doing, we need to first say that I don't know. Because unless we say I don't know, you will not open the door for knowing something more. We are so very imbued in saying that I have known everything. Our education system also works like this, that this is the total knowledge. Take it and start your shop. If that is the kind of education, instead of that, if we were to say, we know this much, and there is a huge amount of unknown. And that unknown, if we were to learn some system or methods of taming that unknown, that much better we will change, I suppose. And towards that, I find that this thought of having physics, applied engineering, and biology together is one of the unique platforms where we can have an interaction, wherein I feel that every science walks, sometimes runs, and sometimes sprints even faster. And knowing from the adjacent or the juxtaposed science how fast it has gone, how has it gone fast, a lot of it can be borrowed by the other sciences from the adjacent science, and that's where this interaction will be excellent. So may I invite Professor Amit Ghosh from SINP to give his talk, please. Professor Amit Ghosh.
Okay, good morning, everybody. Thank you for arranging and organizing the meeting. Okay, so let me first share with you something that you know that once in Ishwar Chandra Vidyasagar, who was a Renaissance man in Bengal, he asked Michael Madhusudan Datta, who was a Renaissance poet in Bengali literature, that Michael, can you write a full paragraph in English without the English alphabet E? So Michael was, smiling. And he was very innovative, of course. So after a while, he said, I doubt I can. It's a major part of many, many words. Omitting it is as hard as making muffins without flour. It's as hard as spitting without saliva, napping without a pillow, driving a train without tracks, sailing to Russia without a boat, washing your hands without soap. And anyway, what would I gain? An award, a cash bonus, bragging rights? Why should I strain my brain? It's not worth doing. Anyway, so it's a joke. You notice that in the whole paragraph, he did not use the word E. Now, my situation today is somewhat similar to Michael because I am actually a theoretical physicist and I am supposed to tell you about experimental facilities in the institute. So my answer is very much like Michael, I doubt I can. Anyway, so you know that in SINP, the major research facilities are basically spread over 4 research groups. And I'll be talking about only the 3 groups, the condensed matter, surface physics, material science, nuclear high energy and interdisciplinary science, and theoretical physics. Biophysical sciences will be covered in some later presentation. So basically, the theoretical physics group is a 30-member group in SINP, consisting of faculty members, postdocs, and research fellows. The broad research areas are various things: particle physics, phenomenology, quantum field theory, condensed matter physics, statistical physics. There are mathematical methods, string theory, gravitational physics, and all areas in these sub-fields, they have multiple national and international collaborations as expected. The next group is the high energy and nuclear physics group. It's a larger group, 72 group members, 19 faculty members and postdocs, and a large number of research fellows. The research activities span over various spectroscopy, positron annihilation spectroscopy, nuclear spectroscopy, atomic physics and laser spectroscopy. Then we have various heavy ion collision experiments and theory, nuclear structure, reactions, and obviously low energy nuclear astrophysics, about which we will come back later. The other group that I'll also talk about is condensed matter and surface physics and material science. It's a 56-member group consisting of 10 faculty members and a lot of students. And there are various facilities: single crystal growth facilities, quantum structures, physics of transition metals, and various other things. I will talk about it very soon. The major facility concerning the theory group, the only facility that I will talk about is the computational facility in SINP. There is a central computing facility in the institute that consists of basically 1 Intel parallel clusters consisting of roughly 15 servers. These computational nodes are basically servers, and with computational capacity of about 500 core. That means you can run about 500 jobs parallelly. And the speed is roughly, it's a theoretical estimate, is 37 teraflop per second. So that's quite a good computing facility we have. Of course, we are adding, very soon we are going to add 500 more cores to this facility, so it will be more powerful. There is an IBM cluster machine as well with much less speed, 800 gigaflop per second, and less computational core. Then there are other clusters which are distributed in rather group-wise. So these clusters, the earlier clusters were central facilities. These are available, these facilities are available to a group of faculty members. There is about a 10 server cluster with 325 computational core, and speed is 31 teraflop. Then there is a 4-node server with 4-node cluster, 450 computational core, and 8 teraflop per second. And there is also a 16-node server with 10 teraflop per second. So that's basically the kind of computational facilities we have in the institute. Now I will come back to the experimental facilities one by one. First of all, we have what is called a flat zone mirror furnace. Now, this flat zone mirror furnace, you know that it is primarily used to make oxide-based single crystal, growth of oxide-based single crystal. Basically, you take elements, and then from these elements in a furnace, you make a polycrystalline rod, and you put this rod, you insert this rod in this machine and make small granules of single crystals. Now, these machines, this instrument is used to make single crystals, but to characterize them, you have to use other facilities, and some of which are not available in SINP. Our faculty members use facilities of other places to characterize them. There is a pulsed laser deposition system. Basically, it is used to grow thin films by laser. So basically, you keep a target and hit it by pulsed laser on a metal target. And then what happens is that once the laser hits the metal target, the metal things, they are ablazed, and these basically vaporized, and that vapor is deposited on a sample to make a thin film of that sample. This is an in-house facility mostly used by in-house students and faculty members. Apart from that, we have a clean room. This is a recent facility. We have a clean room of class 10,000. It means that, roughly speaking, there are 10,000 dust particles per meter cube in the room. And it is said that the dust particles of size, say, 10 micron and above, they are completely removed from this room. There are air particles, but no dust particle. Dust particle less than 10 micron size, up to 10,000 particles per meter cube. So in that clean room facility, we have a bunch of device fabrication facilities, like thin film device fabrication facilities. One is photolithography, wet and dry etching. You know that when they use wet etching, they used acid. When they make dry etching, they use plasma. And vapor deposition, this thermal deposition method. This has attracted some collaborations from neighboring institutions like Bose Institute, Cultivation of Sciences, SN Bose, and NISER, Kolkata, as you can see. We have also a rotating anode X-ray crystallography system. So basically what happens is that from the cathode, a high power electron beam comes and hit on a anode where there is a metal, and that anode keeps on rotating. It rotates to avoid being damaged or get heated up. And X-rays are emitted, and those X-rays are used to study and characterize various crystal structures. And the good thing about this instrument is that it can be used under temperature variations. As you know that as you vary the temperature, crystal structures sometimes change. You can use this instrument to study all that. And this is a very popular machine. As you can see that it attracts a lot of collaborations from various institutions in the country. We have also a squid sensor in the institute that that it can measure very small, very tiny magnetic fields, and it is used to study magnetization, susceptibility with temperature variation. And this is also a very popular machine in the institute, and it's not easy to get slot in this machine. You cannot just drop by the corridor of SINP and ask for a squid measurement. You have to ask for it well in advance. Slots are not easily available. We have also what is called the PPMS facility. Basically, it's a cryostat with some superconducting magnet in it. It is used to study various magnetic transport properties, magnetization, susceptibility, heat capacity, thermal power, etc. And it is used over a range of temperature from 2 degree Kelvin to up to room temperature, 400 or something Kelvin. And it is also very popular. It attracts a lot of collaborations and facility users from neighboring institutions. The institute also has a dilution refrigerator with the recent technology, that is superconducting magnet installed in it. This is used to study transport properties of various systems like quantum Hall effect. This is a very standard thing now. As you know, that it's dilution because it's a helium-3, helium-4 mixture. With helium-3 or helium-4 alone, you cannot go down to temperature as low as millikelvin, but with a dilution, with a correct dilution, one can achieve that. And this facility is also available. It has quite a good number of collaborations from IIT Bombay, SN Bose, and Cultivation of Sciences. There are some common facilities which are also quite popular, like I think this is not very uncommon to most of the institutions have that, is a photoluminescence and Raman spectroscopy. Photoluminescence, they use powder on thin films, on low dimensional materials or layered materials. And the samples are basically stimulated by laser, and they measure the emission spectra using photoluminescence, and Raman spectroscopy is also used for studying various properties. It is quite popular in neighboring institutions. Here is a picture of the photoluminescence setup. It is basically a helium-cadmium laser, which is the source, and it operates from 300 to 1500 nanometer wavelength. We have another facility which is called ARPS. It is a photo emission spectroscopic facility. You know that photo emission, when photo emitted electrons, they are scattered, and these electrons, if you measure their angular distribution and energy, then it can be used also as a spectroscopic technique. It is basically an integrated facility. It has an XPS in it, the X-ray photo electron spectroscopy, and a LEED facility, low energy electron diffraction facility. So this facility can be used to make thin films as well as measure thin films. So it's an integrated thing, and it is quite popular. It has quite a number of users, including neighboring institutions as well as IOP and IIT Kharagpur. Apart from that, there is also a facility which is called LIMPIM facility. You know, this is also some low energy electron microscopy, and used in two kinds of modes, LIM mode and the PIM mode. PIM mode, it gives you resolution of the order of 10 nanometer. In the in the LIM mode, it is much higher resolution, 5 nanometer. So it is also a photo emission electron microscopy technology. It gives you fast image, real-time surface measurements at the order of nanoscale. And it can be used for potentially for many applications. It is, so far, its uses has been restricted to cultivation of sciences, SINP and IIT Kharagpur. We have also an XRD, high resolution XRD facility. It's a facility to, it's very, the machine instrument is very similar, the earlier rotating anode instrument. But in this case, in this machine, you can use thin films and powdered samples so that you can measure the high resolution X-ray scattering or reflection from the samples. Basically, in parallel beam with grazing incidence is sent on the sample, and you measure reflection or scattering with very minute angular graduation of the order of millidegrees. So that gives a very good study structure of the crystal structure of the sample. And fortunately, there are two kinds of X-ray sources you can use. The copper X-ray source that gives you up to 8 kilo electron volt, and there is a molybdenum source that gives you up to 18 kilo electron volt. So you can use it low energy and high energy, as well as this machine is integrated with bulk studies where you can use some spectroscopic measurements as well, which can give you crystalline structure of the powdered sample and also multi-layered samples. And this instrument is also quite popular, as you can see, that it is used by various institutions, cultivation of sciences, SN Ghosh, ISER Mohali, also some private universities, and so on. The institute has a beam line at RRCAT facility. It's a grazing incidence X-ray scattering beam line. You know, you take a beam which is of rectangular size, 35 millimeter by 15 millimeter, and when it is focused using mirrors on the sample, it gives you a beam size of the order of 0.5 millimeter to 0.2 millimeter. So it's a very focused beam on the sample, and this X-ray is incident grazing at grazing angles to the sample. The beam size is of the order of 32 meter. So the 32 meter beam is focused on the sample. And it is used for similar studies, reflectivity and scattering from thin films and multi-layer samples, diffraction, also diffraction from multi-layer samples and crystals. This color variation from this blue things, these are yet to come. You know, the idea was that you can use this facility from a low temperature, like 4 degree Kelvin, to high temperature, 1200 degree Kelvin. And for that, a closed cycle refrigerator, CCR, has already been purchased, but these facilities have to be updated, and it will be soon available, I think, in a month or two. There is also an updation planned, namely grazing incidence diffraction from liquid surface. You know that if you take a solid surface or a powder surface, then you can rotate the sample stage. There is this facility, the sample stage and the detector stage both have independent rotations. You can rotate the sample stage for non-liquid samples. But for liquid samples, you cannot rotate the sample stage. You have to take the beam geometry very seriously, and that facility probably will be available in a year or so. This has attracted a lot of users from various parts of the country, BRC, RRCAT, and CSIR institutions, and also various universities, including obviously SINP and neighboring institution, VECC, who use this facility also. The institute has a transmission electron microscope. Now, this electron microscope, you know that is just like an optical microscope. Electron beam is fallen on some material, and then it is used by some electromagnetic lenses. It is focused and gives you a very high magnified image of 60 to a million magnification in the TEM mode. So when it is only used in the transmission electron microscopic mode, it is this magnification. When it is used with the scanning tunneling, scanning transmission microscopy mode, it gives you about 100 times more resolution. It is because it can, in that mode, you can capture more high angle electrons using the special detection technology. And using this instrument, you can use various images, 2D, and using tomography holder, you can also make 3D images. So basically, you superimpose many 2D images to make a 3D image. Along with that, you can use spectroscopic measurements using this instrument with X-ray analyzer and EELS facility. This is, I must say that basically the whole thing is summarized in this page. There are, all these facilities are available in the institute. We using this TEM mode and also in STM mode. We have also a local expertise in SINP about interface, studying interface of this sample. So along with this TEM mode, there is a very small facility to prepare samples. And this preparing samples institute has good expertise, and we can prepare sample in such a way that the interfaces are very nicely coming out in the picture. And that is why it is very popular, this instrument, including in the country and also internationally. I didn't put up the international collaborations, but inside the country, you can see from the list that it's a very popular machine used all over India, and many institutions are involved. Apart from that, we have what is called the laboratory of laser laboratory, light matter interactions. Basically, this is the facility to study what is called the electromagnetic induced transparency, EIT. So this is a new technology. You know that this is, suppose this is the absorption line of the rubidium atom. And using laser, what you can do is that inside the absorption line, you make a hole, you make a dip. So this absorption line becomes transparent, part of it becomes transparent in between, and through that transparent window, you can put some light. But what happens is that this transparent window doesn't become quite transparent. It is very dispersive, this window, and with very high optical density. So it slows down light. So there is a light that can pass through. It's not totally absorbed, but part of it slows down. So that you can compare by putting a normal speed of light, and this yellow graph, you can see that it's a slowed down light. So this slow light, with the use of this EIT, electromagnetically induced transparency, is used for various quantum mechanical things like quantum memory, or various other technologies in using quantum computers, qubit, etc. There is an opposite thing you can do, namely you can make a transparent things suddenly absorbing. So highly transparent medium, this peak, becomes suddenly absorbing using laser. So this is also used in quantum switching devices. So this facility is for studying this using rubidium atoms at room temperature. There is another optical table where the similar things have been planned for cold rubidium atoms, cold of the order of 10 microkelvin. And this has been, the instruments are available. So basically it's a magneto-optical trap where rubidium atom, as you can see in the middle, has been trapped by 6 lasers from all sides, from all 6 sides, and also using the magnetic rings. So this is a cold rubidium atom. It is almost trapped. And this thing is used to absorb light in its quantum state. So basically, using the electromagnetic induced transmission, you absorb light at the cold stage. It means that you absorb a quantum mechanical state without measuring it. So what quantum numbers goes into the state, you don't measure it, and that is a quantum information. So once you switch off the laser, this quantum information should be released. That is the idea, and this idea is could be used perhaps in what is called the quantum mechanical memory storage. Just like optical storage devices we use for memories in CD-ROM and other devices. These kind of things are planned for quantum mechanical computation as storage devices. So, but this is not completely ready yet. This is yet to be ready. The facility is would be fully operational perhaps in near future. I'm sorry for this, perhaps it can be seen. Yeah, as you know that the institute has, SINP has been building a underground science laboratory in UCIL, Jodugura campus, Jodugura, UCIL campus. It's a science laboratory at a 550-meter depth underground in the UCIL mines. The idea is to basically, at this stage, measure backgrounds very carefully at this depth and compared with the surface laboratory. And in future, the facility should come up with various measurements, should be ready for various measurements. One of them is low mass dark matter search, the technology which is called the superheated liquid detector technology that is available in the institute. Also, it has potential to measure rare events, short-lived nuclei, and annual modulation of cosmic muon and muons at various depths of the earth, etc. And as you can see that from the list that a large number of faculty members from SINP and VECC are interested. So there is no problem of mass. There is a lot of participation, only that a little bit of velocity perhaps will produce a lot of momentum in this activity, and we are looking forward to that. Hopefully it will come up in a nice way. And as you know that there is a facility which we call FRENA, Facility for Research in Low Energy Nuclear Astrophysics, that has come up. The building has come up, the machine has come up. And I must say here that from tremendous force top down from various various chairmen and directors, and also by some tireless efforts of some of the faculty members and staffs of the institute. Actually, one of them has also left us forever. This facility has come up to this stage, and it is now ready for calibration. And hopefully, we are looking forward to this facility to come up in a big way. Various institutions are involved: SINP, VECC, TIFR, IUAC, and also IOP. Right now, the facility can provide a 100 microampere current at 2 MeV, and it is stable up to 6 hours. This has been tested with minor, fluctuations. And with this kind of background, we are planning to go forward to calibration studies. And let us see how, when this facility can be really open for experiments. Very recently, a user committee has been set up, as you can see, consisting of members from various institutions, BRC, TIFR, IUSC, VECC, and of course SINP. And let us see how the user committee. Now, so the kind of facilities that I have given to you is obviously a very, very limited snapshot of SINP. The whole institute is a facility. It's not that only these are only some representative snapshots of the facility. And how the whole institute is a facility, for that you have to visit the institute and see that what are the secrets and hidden gems that are there in the institute. And that can be only explored by visiting and through collaborations. Obviously, the institute has some major international collaborations. I did not quite want to mention it, but just to be complete, it has a collaboration both in the CERN experiment, in ALICE and CMS. I put CMS in gray, as you know, because it is still waiting for some approvals. There is a MAGIC collaboration. This is a Cherenkov telescope system in Spain, in Granada, and some imaging facility. Institute is part of that. There is a snow lab facility underground at Sudbury, Canada, and it was part of that also. It is also not clear whether how long that we can continue with that, because there is only one faculty member involved. There is an Indian beamline at Photon Factory, Japan. It was made by India and now also maintained and basically run by Indian students and postdocs. And SINP is also part of that. So let me just end with this famous quote of one of the most successful, person who made the most successful science collaboration happened in the history of science, the Manhattan Project. And this is the quote from Robert Oppenheimer. And let me interpret it in my way, that in collaboration, he said that, and now let me say that in collaboration, the secrets of nature do not really put any hindrance to collaboration. It is the secret of other things, like the secrets of our own thoughts and intentions, that put hindrance to collaboration. And only if we can overcome that, then only a successful collaboration will be possible. Thank you very much. I hope I am within time.
Yes, just within time. Thank you. Thank you very much, Professor Ghosh. If there are any questions from the floor. Can the people online can also ask questions? Yes.
I hope I have been quick enough to confuse everybody, not to ask too many questions.
The whole spectrum of things that are possible, I gather it just stuns everybody. But I'm sure people will digest and deliberate on this.
Yes.
But you have elaborated the processes, what is possible, very eloquently. And I'm sure there will be people who will find their needs,
Yes.
like in any science, as to how and the process is easy to understand or to know. Finally, it's the why that decides what answers we'll get. Thank you. Thank you very much, Professor Ghosh. Thank you.
Hello, I have just a question.
Yes, please.
Yeah. Thank you for the nice presentation. My question is just Indian beamline at Photon Factory. So what type of photon energy beam you will get?
Sorry?
Will you repeat that question, please?
Photon Indian beam line at Photon Factory, Japan. Just I want to know about the type of photon beam you will get.
Japan?
Yeah. This transparency is showing.
The last one, Indian beamline at Photon
Yes,
Factory.
so you were asking what kind of beam? Yeah. See, I have not that ready answer to that. But please, I will request you to go to. Sorry.
Hello.
Oh, you are okay. Please.
I am very much aware of this because this is a X-ray diffraction beam line at the Photon Factory. There is a huge temperature variation facility, and this has been routinely used by many users from Indian community. Yes, but beam what we get, that experiments what we do, it is X-ray diffraction.
So basically, I will suggest that please go to the SINP website. There is a link to this photon factory facility, and you will get much more details there.
Sir, I have a little question. Actually, even though you briefed about the facilities that are available, my little doubt is, you said in a lab that is set up for light matter interaction, you have a rubidium atom and you have absorption edge. And you work somehow that absorption edge becomes transparent. So what is a physical, like how do I visualize that you have made an absorption edge transparent?
Oh, that has been known for quite some time. It is not a discovery made in SINP.
Okay.
It's a very standard thing. This electromagnetic induced transmission. It has been discovered some years ago. I think what they are trying to master the technology in the laboratory using rubidium atoms. I mean, the thing was discovered much before that. But to characterize them and to control this thing, so that you can use it for various other technologies is the clue, and that is what people in SINP are doing.
Thank you.
I think in many cases, since the presentation is really covering the entire institute, the concerned speaker may not be able to give immediate answer. But perhaps there is I see the purpose is to provide opportunity. Later on, we can interact and find out who is the correct person in the institute who can provide more answers. Yeah, I think he's online. Professor Thangadurai is online, so
maybe it may be a good idea to send an email to any one of us. I mean, whose email is available there? Probably Amit's email is
yes,
with the organizers. My email is also there. So we will transfer the questions to the right persons, and the person will get back to you. I think that is a better way of handling the thing instead of addressing all the issues here.
yes.
Agreed. Thank you very much for that input. May I now request Dr. Suryakant Gupta from IPR to make his presentation.
So, Namaskar. I am from Institute for Plasma Research, Gandhinagar, and today I will discuss the development of plasma technologies at IPR for the benefit of society. So, the major program at IPR is fusion-related research, and at present we have two operational tokamak. First is the Aditya, it means Surya, and second is steady-state tokamak SST-1. IPR is also contributing in International Thermonuclear Experimental Reactor Project, that is ITER. It is coming up at France. And for these topics, my colleague, Dr. Shishir Deshpande, will deliver a talk tomorrow at 12:40 in second session. In 1997, IPR has established a center named as FCIPT, means Facilitation Center for Industrial Plasma Technology. So at this center, we develop new technologies through phase of conceptualization, development, incubation, and technology transfer. So this center acts as a bridge organization between IPR and the Indian industries. I come from this center, so my talk is focused on the technologies developed in IPR. We know about the three states of matter, that is solid, liquid, and gas. So when we apply energy to the gas, then the gas gets ionized and we get the plasma state. That is the fourth state of matter. So usually in gas, we have only one species. In case of plasma, we have more than one species, that is electron and ion. So we know gas is used for switching the very high voltages. So it has an insulating behavior. Whereas in case of plasma, we have electrons. So it acts like a conducting media. So plasma doesn't have any shape or a consistent volume. Plasma can easily flow into the container and it takes shape of the container. The substance in plasma state will remain in the plasma state as long as the sufficient energy is maintained. So these are few examples of plasma in our daily life, like the glow signboard, CFL, plasma display panel, plasma globe, and tube light. So these are the example of man-made plasma. In nature also, plasma exists in the form of sun and lightning. So plasma can be categorized into two types, like hot plasma. It is also called thermal plasma. So in hot plasma or thermal plasma, the temperature of electron is equal, very close to the ion temperature. Whereas in case of cold plasma, which is also known as a non-thermal plasma, the electron temperature is much, much higher than the ion temperature. So 99% of the visible universe is in the plasma state. So it touches almost all aspects of our daily life, like starting from energy, surface engineering, medicine, automobile, space science, textile, waste destruction, photovoltaic, environment, food, water disinfection, and nanotechnology. So in my presentation, I will present some of the technologies developed in our center. You know, municipal solid waste is a big problem because daily few lakhs of ton of municipal solid waste is produced, and out of this waste, around 20% is plastic waste. In big cities, in hospitals, few tons of medical waste is produced, which is a very big problem, how to dispose this type of waste. So the conventional techniques are incineration. Incineration means burning of waste in large quantity of air. So because of air, the cold zones are formed in the reaction chamber. And because of these cold zones, these carcinogenic gases like dioxin, furans are produced and it pollutes the environment. So plasma pyrolysis is an ideal technology for the waste disposal because it break the large polymer molecules into smaller molecules like hydrogen, CO, and methane. So this is a which you can see a graphite plasma torch developed at our center. And using this graphite plasma torch, we have developed a plasma pyrolysis system, which has been commissioned in different parts of our country. This system is capable to treat 15 kilogram of waste, biomedical waste per hour, and this quantity is sufficient to cater the requirement of a 300-bed hospital. We have performed the emission measurement, and the emission measurements are within the CPCB limit. In next slide, I will show these measurements. And the technology has been transferred to the industry. In this slide, you can see these are the standards prescribed by the CPCB, that is Central Pollution Control Board. And these are the measurement performed in the plasma pyrolysis system developed at IPR. You can see the emission are much less than the CPCB prescribed standards. The other alternatives like microwave, it also sterilizes the waste, but the volume reduction of waste is very less, only 20%. In case of incineration, residue is less, but it pollutes the environment because toxic gases or say carcinogenic gases like furans are formed. And plasma pyrolysis, it sterilizes the waste. And you can see if we put 100 kilogram of waste, more than 99% volume reduction takes place, and it is a eco-friendly process. This technology has been recognized by the Government of India for the safe disposal of biomedical waste. Now, I will come to the another application which we have developed in our center. This is a picture of Angora rabbit. These rabbits are grown up in Himalayan region. Their fibers are very warm, soft, and very silky to touch, means human friendly to the human skin. But due to the slippery nature, we cannot spin thread out of it, and it is difficult to produce 100% Angora fiber cloth. So if you see if you have noticed the sweaters, so they always mention 10% Angora fiber, 20% Angora fiber, or 30% Angora fiber. It means they have to add either cotton or cashmere in their product. So what we have done, we have treated the Angora fiber, which is very smooth. You can see the SEM image. After the plasma treatment, we could introduce the roughness on the fiber surface. And due to this roughness, the friction coefficient was increased, and we could make the thread out of Angora fiber. And this is a machine which we have commissioned in Kullu, Himachal Pradesh. So on one side, we just load the Angora fiber, and after the plasma treatment, the treated wool is collected from the another end. So you can see these are the 100% Angora fiber based product which they have prepared in Himachal Pradesh. Plasma can also be used to modify the textile surface. Like on the left hand side, this image is an untreated fabric. Once if we treat this fabric with plasma and then we do the dyeing process, so you can see the difference in the color. So basically it increases the dye uptake property. Similarly, in a single textile material, we can introduce two types of property like hydrophobic surface and also the hydrophilic surface. We need the hydrophilic surface for our inner garments because it touches our body and it should absorb the sweat. Whereas the exterior part of cloth, it should have hydrophobic surface. So in a single cloth, we can introduce inner side with the hydrophilic property and the exterior as a hydrophobic surface. So we have tried to scale it up. This is a machine where we have multiple treatment zone, and it can treat 2.5 meter wide textile cloth surface. So a roll is loaded, and from after the treatment, the treated textile is collected. And now this machine has been commissioned at Man-Made Textile Research Association, Surat, and the experiments are going on. This is a facility, this is based on thermal plasma, and we have produced metal oxide nano powder for ZNO and titanium oxide. So this is a picture in which you can see there are tea stains, coffee stain, and turmeric stain on a uncoated fabric. On a coated fabric, when we have exposed that fabric to the sun for 4 hours, you can see all the stains have been removed. So this is a self-cleaning textile. So apart from this, nanoparticle have several applications in the pharmaceutical industries, paint industries, cosmetic industries. It improves the coolant performance and lubrication efficiency also. So this technique is a single step process in which high quality nanopowder can be produced. This is a very interesting example. There is a company in Bangalore named as a Triton. So they manufacture the brass valve used in the automobile industry. So you can see it is a brass part and this is a rubber part. So they have to bond the brass with rubber. So as per the conventional procedure, so they take the brass valve, they remove the grease on it, and then there are several chemical steps are involved. So what we did, we have removed all these steps by a single plasma treatment in which we consume only electricity and air. So this technique is an eco-friendly process which bond the brass with rubber without using any adhesive. So you see, initially we begin with 2 valves per batch. And finally, we have developed a industrial scale demonstration unit. You can see it here, in which we can treat 5,000 valves per batch. So this is an industrial scale system. You can see the footprint is very small, and the area is very clean. This is an image of brass valves exposed to the plasma discharge. So basically, as per our understanding, what we have observed, after the plasma treatment, it activates the brass surface, which generate oxide and also create nanotexture. It helps in the bonding. So what is the benefit? As per this company, they have informed us with this, due to the installation of this reactor, they could save 65,000 liters of water per day, because no chemical is used. So they need not to use any chemical storage unit. They need not to treat the effluent. So this has reduced the cost of their treatment of brass valve. Similarly, in case of steel, we have to harden the surface of steel for various application. The conventional techniques are either cyanide salt or ammonia salt, means liquid nitriding or gas nitriding. In both of the case, it takes longer treatment time, and also it pollutes the environment. Whereas in IPR, at IPR, we have developed the plasma nitriding process. You can see it's a very clean system, and only hydrogen and nitrogen gas mixture is used. It is a relatively fast process and also the eco-friendly process. We have performed the measurement, and in various steel, we have measured that hardness has been increased by 300%. So we do have job shop at IPR because we would like to promote this technology in the industry. So in the job shop, we are catering the industry following industrial sectors like automobile, textile, foundry, construction industries, tool and die making industries, and power industry. I would like to highlight this center image of gears is the gears supplied by the ISRO. So since last more than 20 years, all the Indian satellites gears which they are using to rotate the solar panels have been treated in the plasma and nitriding system at IPR. Plasma treatment can also be used for the water filtration application. Nowadays, RO systems are very commonly used at our home. And in these RO systems, this type of candles, membrane candles are used. These candles are made out of activated carbon. Because activated carbon is powerful absorbent, it has a large surface area. And since it is produced from the coconut, so it also maintains the good quality or good taste of the water. But it is hydrophobic in the nature, means water cannot percolate it through this material. So a pump is required. So there is a company in Bangalore named as Filtrex. So they approached us. They were interested to develop some candle which can be used at gravity pressure. Means if we connect that candle to any bucket, so bucket mouth, so we can get the filtered water. I will show you a small video clip. You can see here, this disc half is made from the coated plasma treated charcoal and half is untreated charcoal. So first this water drop falls on the untreated charcoal material, and you can see water droplet remains here for some time and then it enters into the disc. The rest of the part was made out of treated activated carbon, and you can see here when the water droplet falls on this part, it immediately percolates in the disc. So basically, if we make candle out of this type of material, so it can be used at the gravity pressure. So we have developed this machine. On the one end, we just loaded the water, this charcoal powder, and from the another end, they have collected the powder. Since they had some business issues, so they did not disclose the further outcome of this activity. So what we feel still study is required to scale it further, and what is the reason behind this process that can be studied further. This is a small experimental setup to produce plasma activated water. And you can see here in this graph that when we treat this water with plasma, so its ORP, that is oxidation reduction potential, increases, which gives a hope that it can be used for the water disinfection application. Similarly, as the time grows, its pH is reduced, So in the system, nitrite and nitrates are formed, which can be used as a manure or a fertilizer for the agriculture crop. So in this slide, you can see this is a control of this microorganism. After the plasma treatment, almost 7 log reduction has been observed. So this is a SEM image. We can see here, this is the microorganisms. After the treatment, the cell wall has been ruptured and the protein has come out from this. And you can see that protein react with some compound and it forms the dye. And in the fluorescence spectroscopy, it confirmed that cell rupture has took place, or we can say cell lysis has took place. Plasma can also be a potential candidate for the agriculture application. This is a seed. So after the plasma treatment, what we have noticed, the surface area of the seed has been increased. So basically it increases the water uptake property. Because of this, we have noticed that germination rate of seed has been increased by 10 to 15%. So it means the total productivity of crop will also increase. The same technique can also be used for the insect control or to remove the pesticides from the vegetable or the fruit. We have also observed when these seeds are implanted, then the growth of treated and untreated plant have been found different. So the plasma treated seeds have shown the larger plant growth. This is in the previous slide, I have shown the thermal plasma based torch. This is a cold plasma torch, so one can touch it. So this type of torches can be used for the coagulation of blood during accidents. So suppose in 108 sort of ambulance, if such torches are there, and if some patient is there, so immediately this blood coagulation can take place and we can save life of the humans. These torches are also used for the sterilization of wound in the cosmetic surgery, skin treatment, dental surgery, and also for the cancer treatment. So this is an array of multi-torch so that we can cover or we can treat larger area in a single treatment process. So here you can see here the normal blood coagulation process, it takes around 200 seconds. Whereas in case of argon plasma, it takes only 12 seconds. So this is the advantage we have observed. We have carried out some preliminary study in collaboration with BARC, and you can see here the cell viability has been increased. This is another example which we are doing with the AIMS, and here we have noticed that ROS has been increased. So it shows that damage of tumor cell has occurred because of the oxidative stress in the system. Now I will show a slide about the plasma sterilization process. You know, the conventional sterilizers are based on the steam, that is high pressure and high temperature based system. But nowadays, in the medical science, many tools or equipment are made out of polymer compounds. So those type of devices cannot be sterilized in the conventional high temperature sterilizers. So for that type of component, we have to go for the low temperature sterilizer. So existing techniques like ethylene oxide, it is a well-proven technique, but it occupies a larger area. And also the treatment cycle is very long. And finally, it also pollutes the environment. The second one is the ionizing radiation. This is also a well-proven technique, and it is being accepted by the industry. But it also occupies the larger area, and also it is a capital intensive. Whereas plasma sterilizer is a very compact device. It can be kept inside the operation theater. You can see very small, almost, this is around 2 feet, 2 feet by 2 feet. So why plasma sterilizer is a potential candidate for the sterilizer? Because in plasma, we have UV light, we have reactive species like hydroxyl radical, hydrogen peroxide, ozone, and also we have electrical field and charges. So what we have observed that the combined effect of all this is a good recipe to kill microorganisms present in the medical devices, because it's a low temperature process. So all the temperature sensitive tools can be sterilized in this setup. No chemical is used, no toxic residue, and there's no hazardous emission. So the experiments are going on. We are hoping that this will be helpful in the remote areas where the conventional, which I've shown, the ethylene and ionizing radiation cannot be used, but plasma sterilized can be used easily. Plasma technology can also be used for the space science. You know, in the satellite, there are three major components. First is the antenna, which is used to receive and transmit the signal from Earth and from satellite to again Earth. Transponder is this part, which is the center part of the satellite. It receives the signal from the Earth, it modifies the frequency, and then also amplify the signal so that it can reach to the Earth. And third is the solar array. In the space, solar array are the only source of providing power to the satellite. And in solar arrays, small cells are connected such that we get a bus voltage of around 42 volt. So at the time of eclipse, the whole power load gets shifted to the batteries. So this is very important component in the satellite. As I said, typical bus voltage is only 40 volt. So suppose if we have to develop or design a 1 kilowatt satellite, so the current of the bus voltage will be around 25 ampere. But we know nowadays the requirement of satellite has been increasing day by day. So we need high power satellite. So for an example, suppose if we have to design 10 kilowatt satellite, and if we keep the bus voltage 40 volt, so the current will shoot to 250 ampere. To carry such 250 ampere current, we need a thick conductor. So because of this thick conductor, the overall weight of the satellite will increase and the launching cost will also increase. So this has forced us to increase the bus voltage so that the conductor thickness can be reduced. But when we increase the current voltage of this bus voltage, then this type of arcing takes place on the satellite solar panel. So these arcings are very dangerous because it can interrupt the path between satellite solar panels and the basically transponders. So once if this connection is damaged, so satellite will not get any power, and in that case we have to abandon the satellite. So URSC, that is UR Rao Satellite Center of ISRO in Bangalore, and IPR have started a joint project which is named as a spacecraft plasma interaction facility. This facility, in this facility, we have a 1 meter diameter and 1 meter length chamber. In this chamber, we create lower Earth orbit-like space-like conditions and geosynchronous Earth orbit-like conditions. So ISRO provides us the satellite solar panel, which we exposed in this environment. And this is a completely LabVIEW-based system. So after conducting the experiment, we get the data in report form. I will show you this. This is an actual arc which we have observed on the satellite solar panel when we created the test, we performed the test. And these arcs are classified into different category based upon their duration. So like primary arc, non-sustained arc, temporary sustained arc, permanent sustained arc. So this is the actual image of satellite solar panel. So after the experiment, we have observed this blue color dot means primary arcs. The green color dot means non-sustained arc, which you can see here. And the yellow dots are temporary sustained arc. And the most dangerous is the permanent sustained arc, because the permanent sustained arc can completely damage the solar panel, and then it can harm substantially to the satellite. And as per the satellite insurance companies, 50% of the satellite failures are just because of this arcing only. So as per the global scenario, USA, the NASA and US Air Force, they were the pioneers in developing such facility. Then the European Space Agency, they have started this activity in mid of 80s. In 90s, Japanese have started in JAXA, and then China and India, we have started working together, means simultaneously. And now we have this facility in operation mode, and our results have been presented in different spacecraft charging conference, and our results are at par with the result obtained in other laboratories. So we have seen that plasma can do, or plasma can solve our problem, and it works very well. So it is like a very potential source for the sustainable development. But we need to know why it works. So this is a scientific problem. We also need to make it work as a large scale. That's where the engineering come into the picture. So I would like to summarize my talk. Eco-friendly plasma-based technologies have various industrial applications apart from fusion research. Low temperature plasma requires a detailed understanding from the interdisciplinary domain expert. There are several unknown areas where potential of plasma is yet to be explored. Basic studies on low temperature plasma and their application in diverse fields are ideal topic for PhD and master project. IPR has developed and demonstrated several techniques from concept to prototype level, and we are looking forward for the fruitful collaborative studies. Thank you very much.
Thank you, Dr. Gupta. If there are quick one or two questions, otherwise we leave it for that online. Yes, please.
What, sir?
You showed a current versus time curve, I think, I versus T. So can you go back to that thing I want? No, I think you've gone too far.
I versus T.
Yeah.
I have shown this slide.
No, after that. After that.
This one?
No, after that. No, now it is. Thank you.
I will show once again. So this is first, second, third. There is no slides.
Yeah, just go.
R plus.
Yes.
Okay.
So this is at a constant temperature.
Pardon, sir?
This curve you have drawn.
Yes.
It is at a constant temperature.
It is at room temperature. We have performed all the experiment at room temperature.
At room temperature.
Yes, sir.
But generally, we expect that if you want to use it for space, etc., there will be temperature variation.
Yes, but this is in the space-like conditions, sir.
I mean, you will create the zero temperature in space-like condition, then make the study.
So actually in JAXA, they have performed some study at the cryogenic conditions because in space they have extreme conditions.
Yes.
And what they have observed, whatever the arc behavior at room temperature, very similar experience they have observed at the cryogenic temperature also.
So suppose I say that, okay, I will not work on zero temperature, I will increase the temperature or decrease the temperature. How will this curve change?
Okay, sir, basically the reason behind this arc is little different from the typical electrical discharge happening in our electrical like switchgear applications.
Yeah.
Here, what happens because you have seen the cells are made out of silicon and the top surface is made out of glass and there is an interconnect. So there is a formation of triple junction, means like this is a cell. So this is a glass, then there is an interconnect which is metallic and it is surrounded with the plasma. So because of triple junction, electrical field enhancement takes place because otherwise the voltage is very less, only 50 volt.
That's right.
Usually we don't get arc at 50 volt, but here we are getting arc at 50 volt. So this condition is little bit different and still people are trying to understand the reason behind arcing in LEO condition as well as in GEO condition, sir.
That's right.
Because in LEO condition, the plasma density is little higher and in GEO condition, plasma density is very less. But in GEO condition, particle energy is very high, whereas in case of LEO, the particle energy is very less. So the space condition is little different than what we are getting in the atmospheric conditions. So this arcings, as I've shown here, the arcing duration is of few microsecond. Here few tens of microsecond, here few hundreds of microsecond. In case of a permanent sustained arc, the duration of arc is more than 1.5 millisecond because it is a matter of categorization. So there is a consortium of NASA, ESA, that is European Space Agency, and JAXA. So they have formed a group, and based upon their several experiments performed in their own laboratories, they have came out with the ISO guideline. So as per the ISO guideline, they have proposed this categorization of arc. So in the facility, in this facility, accordingly, we have made the program and we can categorize the arc automatically. we can also find out the location of arc. So based upon our finding, we have suggested the feedback on arc mitigation technique to ISRO, and ISRO has modified their solar panel design, and at present, all the satellites launched by the ISRO, they are operating at 70 volt bus voltage. We have already submitted our recommendation for 90 volt, and these are under review at ISRO. And recently we have got a new project in which we would like to increase the, we would like to propose the mitigation technique beyond 100 volt or so. So this is what we are doing, sir.
Okay, thank you.
Thank you very much, Dr. Gupta. In fact, I find that this technology is utilizable in so many areas that each one of us could give it a thought as to how, and there is huge amount of application in medical field for safety. So thank you very much. The only thing I can compare the state utilization everywhere is like pulley. Pulley is used in almost everything.
Yes, sir.
We don't give much of credence to that. Similarly, this can be used in various areas and that much utility it is.
Yes, sir. We are
Thank you.
always open to go for the new collaborative project. Thank you, sir.
Thank you. May I now request Dr. Prasanna to give us the life science related what's being done and how utilizable it is in other walks of life. Dr. Prasanna, Director, Cancer Research Institute, ACTREC.
Thank you, Dr. Badve. Thank you, Professor Rao, and thank you, Dr. Maiti and Dr. Nayak for putting, and the team for putting up this conference, symposia, whatever we want to call it. It's definitely unique, and it is going to be, what I'm going to talk now will be completely different from the previous two talks. And you heard a lot of technologies and facilities that are available at these institutes. My talk will be mostly conceptual, because that's what we do in life science basic research. And I'll also introduce the translational component, how the basic research can lead to products or therapeutic targets and drugs that can benefit the patients. And I'll also show why there is such a big gap between the basic research and the products that can reach the patient. And that is where the challenge is. And maybe some of us working in completely different areas can come together to accelerate this process. And I'll give you some of the hints, what I understand. And there probably are better ideas and visions from more experienced folks that can bring in the flavor that is necessary. So a brief introduction for ACTREC. It is integral part of Tata Memorial Center. We have two important components, the Cancer Research Institute and the Clinical Research Institute. Cancer Research Institute is where basic and translation research is conducted. The Clinical Research Center is where the directly patient-related questions are addressed in terms of either empirical observations or evidence-based observations that can lead into clinical trials which change practice across the world. We are renowned for that. And there is also a Center for Cancer Epidemiology, where one asks what is the prevalence of cancer in India, which areas do you find a prevalence for a particular cancer, like a gallbladder cancer. And the origin of the CRI, the Cancer Research Institute, was laid by vision from this great pathologist, Dr. Khanolkar. He pioneered the research in smoking and chewing of tobacco as a causative agent for oral cancer. And this is what he laid out as a goal. You need to elucidate the nature of cancer so as to devise means for preventing and curing it. That is an obvious goal of a research institute, which is connected to a hospital. And the vision is you need to establish an institute, which this was way back in 1962 or so. Establish an institute dedicated to understanding the mechanism underlying the conversion of a normal cell to a cancer cell, with the ultimate goal of translating this understanding to prevention of and cure of cancer. This is extremely important given the talk today by various dignitaries who emphasized why basic research is important. It is a curiosity-driven research. Not only that, it is just not curiosity. You need to understand the underlying mechanism of transformation of otherwise normal cell in our own body that becomes bizarre and begins to grow uncontrollably, causing this dreaded disease for which most of the time when it gets past the organ of origin, there is no cure. So you need to understand the underlying mechanism, and the PIs at Cancer Research Institute are focused on trying to understand the mechanism. And what they believe is that in whichever area their curiosity is driven, they believe that their research will lead to somewhere along the line, a product that can benefit the patients. That is a long road to translation. So scope and mandate currently of the institutes is to acknowledge cancer as a syndrome, because it is not a single problem, it is a multiple problem, and provide mechanistic insight into its multiple facets. If we understand that it is a syndrome, it's not a single disease, it is not caused by one mutation, and to be able to translate these insights into tools and techniques for better diagnosis, prognosis, that is to be able to predict the outcome of a patient. That is, if you treat a patient today, are they going to come back or are they going to be completely cured? And new modes of treatment. That is the goal at CRI. Now we have principal investigators and we have clinical scientists working in collaboration. We have professors, postdocs, and we also have the primary workforce is the PhD students. So this is what I laid out, that we need to understand the mechanism. Now, how do we do it? We use in vitro systems, we use cell lines. This is for the benefit of all my colleagues and friends who are from different fields like mathematics and physics. You might have heard about it, but it is always nice to see it in one continuous perspective, so you'll understand where we are. Using in vitro systems, cell lines in vitro, I mean really purified system. I'll show you an example how we break down the complexity. Patient-derived cell lines, primary cells, and animal models. And we work in close association with clinicians. And we also work under thematic groups. Why this? Because at least there are many big brains that have put their thought into how does one condense all the information that is available on cancer, this multifaceted disease. Can we bring it into some groups that we can understand? Can we characterize it into some molecular properties or phenotypes so that we understand it better? And there are some hallmarks of cancer that are described. That is, these cancer cells sustain proliferative signaling, they evade growth suppressors, they avoid immune system, etc., etc. So under the thematic groups, we have 6 groups which closely work on any one or many of the hallmarks of cancer. You have people working on biomolecular structure, function, and alteration. We have people working on cell and tumor biology. We have people working on therapy resistance and stem cell biology. And we have people working on carcinogenesis, genome biology, and precision medicine. We have folks working on cancer theranostics and clinical pharmacology. And we also have people working on tumor immunology and immunotherapy. And I briefly mentioned about cancer epidemiology. This is a separate unit in ACTREC, and it is headed by Dr. Rajesh Dikshit, and this is what their mandate is. They want to understand the cancer burden in India. They want to understand the prevalence of risk factors, and they want to understand how it is related to lifestyle. This is very important, and is something that you do by gathering information and also converting those information into scientific questions, which then can be tested in the laboratory. So this I wanted to bring in because for myself and for a few folks some of my colleagues who sat and thought about this integration of clinicians and the scientists and how it should go to the society. In trying to think about it, I have put this slide. the philosophy of integrating the clinical and basic research and coming with outstanding questions. What I have put on the left is the common problem, whether it is a clinician addressing cancer or whether it is a scientist addressing the cancer, even the patients. How would an oncologist look at it and how would a scientist look at it? And by distributing this, what I'm aiming for is all our physician and mathematician and computational colleagues that you could also think about these in your own way where you would have encountered some information or the other. Now, the common problem is early detection. An oncologist will say clinical diagnosis. And the scientist would ask what causes the cancer. Now, there will be a common problem of severity of the disease. Oncologists will want to find out has the disease spread, and they would like to find out sooner, as soon as possible, whether the disease has spread. A scientist would ask what caused it to spread. And the common problem is what treatment to give. The oncologist would choose any of these available modalities, surgery, radiation, chemotherapy, and in a few cases, targeted therapy. That is, you know what molecule to hit, and therefore you have drugs for that. And what would a scientist ask? What all changes happen when the cancer cells are treated by radiation and chemo? How do these guys die? And then the common problem is how effective is the treatment? Then the oncologist begins to ask prognostication. They'll anticipate based on their clinical studies, pathology, and their whole lot of experience, which are the people who are going to come back with the disease. Patient A may come back, patient B is likely to survive long. Now, a scientist would ask, how do cancer cells escape these treatment? What makes them survive? How do these cancer cells differ from a patient who comes back with the disease and others who do not? Now, we have been having an active discussion on what is called as dormancy. That is, these cells, which after treatment, some of these cells, you can't obviously kill all of them. Some of them remain back, and they remain silent. They are sleeping. And somewhere over the time, they wake up and they spread to other places. Now, what triggers these sleeping dormant cells to wake up and become aggressive is one of the questions that interests, which is absolutely a curious question to ask. And what to do when the patient comes back? That's again a common problem. So the oncologist worries about how do I treat this relapsed patient? We have already given all these aggressive treatment. What else? What more can I do? And they use radiation, new combination, or new chemotherapeutic drugs. And what is the scientist has to do? They have to find new targets. They have to find new drugs. They have to innovate because this is what it is. And in order to provide solutions for a disease that lives in the patient for a long period of time, these are serious issues. And we need to ask very basic and fundamental questions. I like this two slides also because figures speak for themselves. This is what an oncologist would do. They've diagnosed the tumor. They have very quick options. They will hit it with the radiation. If it is a surgeon, he will remove like Dr. Badwe. And then there will be my colleague, Naveen, who would do a bone marrow transplant. And there will be chemo that would be given. What scientists would do, they can't work with the live person. So they have to take, somebody's trash is their, gold mine. So if the oncologist throws a tissue away, the researcher is happy to take it. So we need to work with those cells, and then we try to understand how these cells, which start as normal ones, undergo transformation to become a mass of these cells, whereas they should have remained as single ones. And this I think most of us know. This is what the dogma of biology is. You have a chromosome, then you have the gene makes the proteins, then you make all these molecules, they come together to function as a cell, and there is a community of cell, then there is a community of tissue, then community of organs. Now, what the scientists can do is that they can bring this complexity down. They know this is a normal cell because all the chromosomes, this is a painted picture of chromosomes, all are fine, they are in pairs. And you look at the tumor cell, it has lost the chromosome, it has gained a chromosome all over, problem all over. It is actually a sick cell, but it is transformed, it has gained some functions. Now, this normal cell will make a nice ordered functional entity the tumor cell cannot form such a functional entity. What scientists do and what we do at CRI is to try and understand this complexity. We may work with one molecule of interest because it is hypothesis driven. We may look at bulk of the molecules, like what was shown. If I'm doing something which I don't know, it's simply because I don't know what's going on, right? And there was also a nice saying yesterday on one of the PI's website: all wanderers are not lost. They're wandering because they're trying to find out what is behind all these processes. So this, pardon me, I have used the principal component reduction as an analogy. That is, this is a human complexity in normal and disease condition. And what we try to do is to reduce it into smaller dimensions so that we can deal with it. The complexity is so much, you will have to reduce it to deal with it. And this is one human being's construct when it is normal. And this is one in the disease conditions. Don't worry, what about it? It is a network of molecules. And what, as scientists, we try to do is that we need to try and understand the delta or the difference between the two. If we do this delta, what we are doing is that we can only work on this. Then we can extrapolate this to who it comes from. And then we can find out the delta. And here is a biomarker or a therapeutic drug target if we are fortunate enough to nail it down. So this is the conceptual idea in which the CRI scientists work. I'm not going to pinpoint to each PS who are going to do it. I will now switch to general facilities in the lab at CRI. I was told not to repeat some of the facilities that may be present in other institutes. This is a flair for what we have, and these are these things that are required for everyday research in most of the biological laboratory. You have a digital imaging, which consists of confocal microscopes. We have a mass spectrometry proteomics facility. Animal House is unique because we have good tumor models. We have a biophysics facilities we are trying to expand. And one of the unique facilities is a drug screening facility and a small animal imaging facility. If some of you are going to visit ACTREC, you will be taken through this drug screening and small imaging, animal imaging facility. We also have proton therapy at the clinical side, which also you will be visiting. And we will be coming up with a hypercomputing center and for artificial intelligence, which probably Dr. Gupta will talk about in his talk. Now, I spoke about the drug screening facility is definitely unique because we have people all over the country coming to our facility with molecules, and they want to see whether these molecules are effective against cancer cells, or will they kill, are they also toxic? So we have a facility which has multiple, I think about 30 cell lines which can be used for screening these drugs. And if there are any hit molecules that are found out, then we can also use animal models. And we also have a pharmacologist who can do the preclinical studies. So this is a battery of facility that is available. Anybody can walk in and then talk to these people at the facility. Dr. Jyoti Kode heads this facility, and you can use the facility for identifying some new compounds. The other is the CAR T cell therapy, which is also hosted in CRI, which is an ambitious project. We want to become self-sufficient in terms of cellular therapy. And this also will be discussed in detail by Dr. Gupta. So these are some of the state-of-art equipments that are there in the institute. This is a molecular imaging facility where you can actually follow the tumor when the animal is live. So most often what happens is that when you put the tumor cells in the animal and the tumor grows, after a while you'll have to sacrifice. And you don't know the events that take place in between. And you don't know if the tumor has initiated very early on. Bioluminescence technology allows you to look at these tumors when they are very small, and as they grow, you can capture them. And when they grow to distant organ, you can capture them. And this is a live cell imaging that is there, and Dr. Abhijit heads this. And we have an equivalent of SPR for protein-protein interaction. We have a spinning disk system, and then we also have nano DSF, which can look at protein-ligand interactions. But these are many of these are present in other institutes, so I'm not going to go into the details. Now, I just wanted to bridge the gap between the basic research and translational research, right? So our goal was to find novel concepts and ideas that explain the phenomenon of cancer. Now, what would be the product? Emergence of novel therapeutic targets, novel small molecules and peptide derivatives, and their lead molecules effective in killing cancer cells, potential new combination of therapies. And we are also looking at drug tolerance or dose modulation for malnourished young cancer patients. This is extremely important because the same dose that you use for patients who are older, you can't use it for these malnourished children who are young, they don't tolerate it. And this is one of the areas of investigation, which will have a direct effect on the patients. Mutation-assisted decisions for therapeutic interventions in cancer patients, this also has a direct implications. Novel mechanism of therapy resistance and biomarkers for better bone marrow transplantation strategies. So this is what the step one was, to acknowledge cancer as a syndrome. Yes, we are doing it very well. We are doing some of fantastic research in this area. The second is to be able to translate these insights into tools and techniques for better diagnosis, prognosis, and treatment, which means the deliverables I mentioned should now go to products that can benefit the patients. Now, this is where the whole gamut of problem is. And this is a problem that all of us have to understand. The people who are leaders in life science have to understand. If we expect the life science to and the health science to produce and make a difference in the society in terms of health and disease, it is a large leap in what we have to do. And this is, the scientist considers this as a research problem. A patient, for a clinician, it is a patient problem. And you have a question. Recognitions that some of these findings should be taken forward and which one should be taken forward. So we have initiated in TMC under the leadership of Dr. Padwe and Dr. Gupta that there will be a translational cell for the specific purpose. So I'll give you one or two examples of what is the finding in CRI and what may be the translational component in this. For example, if you said that there is a molecule, nuclear H1 alpha expression in locally advanced head and neck cancer in patients who are treated with some drug. Now, the mechanism is the PI has gone ahead and found out what is the mechanism behind this. They know these are the two molecules that are important in this axis. How did they do it? They did it with patient tissues. They did it with cell lines. And now what is the translational component here? They have to measure the levels of these molecules. They will have to correlate what these levels of molecules result in terms of the survival of the patient. It can be 5 years, it can be 10 years, which means you will have to follow it up for a longer time. Then you will have to, then what happens is that in this case, we are lucky because there is an EGFR inhibitor. That is one of the molecule in the axis there is an inhibitor for. Because they found this connection between these two molecules, they can use some of the drugs that were prescribed for EGFR in this context. That is what the PI hopes for. Now, this is a true translational component, but will it result in a clinical trial, effective clinical trial where this will be tested? There is a long gap in that. And here, for example, lipocalin-2 expression in colorectal cancer. Dr. Saurabh Dalal is in the audience also. They have done a nice work in trying to understand what this molecule's level does in colorectal cancer. And they found out it is important for tumor progression and therapy resistant. That is when the levels increase, the tumors are resistant, and they also result in people coming back with the disease. Now they have used patients' tissues, cell lines, and animal models. And they have to develop now inhibitors of LCN2. That is an action point. This is an action point for translation. Now what it takes, of course it takes a lot of money. And he has to find an antibody for this. And he is collaborating with people who know the technical know of making these monoclonal antibodies. And we also had an ambitious project coming together with IIT Mumbai and ICT in Mumbai, that is to come up with what we call as a biocluster, to take all these findings and then convert them into products that can benefit life science. That has gone through 2 rounds of DBT. We don't know where it is now. So what I wanted to say is that these are findings which are targeted towards understanding a targeted question that has resulted in a mechanism, plausible mechanism, why such thing happens. There is a probable solution, but before the solution converts into an action point, there are a lot of things that are needed, and I think many stakeholders are necessary to convert this into a tangible problem which will benefit the society. So incubators, industries, and sister institutes of HPMI can come, not only for cancer, we could provide our experience to other problems that face the society and other institutes which are interested in. So what is necessary is that clinicians, chemists, mathematics, bioinformatics, cellular biophysicists, geneticists, physicists, all of these people have to come together. Can you change the landscape now? So this is all putting together multiple pieces. Can we change this landscape? And then is there an acceleration that can take us from this point to the next point, where more products can be seen in the society? There can be a 5-year plan for that, because I was told to provide a vision and a possibility that other people can collaborate. So I'm taking the liberty, what I understand, and I'm projecting it. So for a 5-year plan, you will have to, at least some novel drugs have to come out. There should be some biomarkers. There can be a drug repurposing, just like said for EGFR. You want chemical biological tools. We have got very good set of PIs who can engineer molecules that can look at various phenotypes in the cell. So this is from a Bristol Mayor website, which is a big company, right? And why I wanted to put this is that everybody knows we have come so far in fight against the cancer in many ways. We are also just at the beginning. Dr. Badwe said it very nicely. If you don't know something, you acknowledge that you don't know. You don't start with something that I know everything. It doesn't happen, not especially in the field of cancer. We are pursuing new therapies and at the forefront of scientific innovation by advancing research into cell therapy, immuno-oncology. These are buzzwords of the day. Protein homeostasis, this is a little ancient, but getting its due credit again, and more novel platforms. Through additional validation, continued research into existing therapies, the exploration of novel combination and application of translational medicine, the goal of leveraging biological insights to drive precision medicine for patients is reachable. This is a company, it's a huge company. Even if they are saying that it is a continuous research, you can understand what basic research at CRI should do. And it's a hard task. So in patient care, there are not one stakeholders. There is a researcher, there is a patient, there is a pharma industry, there is cancer organization, there are decision makers. Of course, there are our clinicians who are central to driving this process. So we have to come together. And if we are thinking that HPNI would take this knowledge of basic science and will fulfill the dream of DAE in life science area, we have to work a lot harder. So in the end, I just wanted to thank you. This is a protein structure. This is not a bouquet. So each of those spherical molecules that you're seeing as protein molecules, which I personally am interested in working at. So thank you very much for your patience, and I'll be happy to take any questions. And I said, these are the unique facilities that you can visit, and I'll be very happy. More people, more merrier it is. Thank you very much.
Thank you, Prasanna. If there are any, yes, sir.
A very good and comprehensive talk you have given. You also talked about novel therapeutic targets. Now, I want if there is information of whether machine learning and artificial intelligence is being used in looking for this these new targets.
So it's an excellent question. So the hypercomputing facility that is going to come up is actually looking at images of patient samples and trying to derive the information which obviously human brain cannot comprehend. And they're going to understand the molecular basis of cancer by looking at it. From there, you are likely to get some of the targets. But then in the high throughput studies where you are not looking at one protein at a time, you're looking at multiple proteins, multiple genes, multiple modifications, which require genomics, proteomics kind of platforms. You could take all the data that is there, and then you can have machine learning algorithms to come up with few set of markers, few set of genes that say, okay, this is the characteristic of the early stages of the disease, this is the characteristic at late stage, and this is probably our probable candidates, which you can block. You may kill the cancer cells. There are applications of machine learning.
Also, you know, normal drug design, they also look for druggable targets using AI. Maybe one should also look at that. This is very good, what you explained.
So now what has happened in the field of protein folding, the protein folding ustads used to ask this question, which is in Upanishad. What is that one thing that I know, if I understand, can I understand everything? They used to talk about this for this simple protein folding problem. What AI has done is now you give it to any sequence, it has learned and it is so smart that it can predict the three-dimensional fold of the protein, which is important for function, in a jiffy. And accuracy is about 98 to 99%. So now people are thinking, because earlier, unless you had the structure of the protein, it is very difficult to see what you can target or which pocket you can target and what molecule can be used. You could use that screening. I am a very big fan of screening as well, but that also costs money. But AI can do it in a jiffy, and people are using that to find out, take all small molecules, throw it and see where it will bind.
Thank you. Thank you.
Thank you, sir.
Yes, one more question there, please.
Yeah, good morning, Mr. Prasanna, and congratulations, you put it rightly. And this is the right forum possibly where CIs...
I was worried about that, whether I am crossing the limits or...
Why my question is, this cancer treatment, whether it is metastasis or a organ or a very small cells under trouble, you know, this physical sciences started all this. Lawrence cyclotron put it into the treatment, hadron therapies. And they started with neutrons, then there were problems, and now the proton and the new machine that you have got at ACTREC,
yes,
we will be happy to see that. That was the comment.
Sure.
Professor Badwe sir, we started in July 19 the discussion to bring in context an Indian treatment, proton and multi-ion therapies, which will be definitely a targeted thing to come up. This was the comment, madam. So thanks to HBNI, all the CIS institutes are there. Large CIs like BRC and RRCAT, who can actually bring the engineering part and the physics part. You know, this electrical engineering and physics form the major part of how you deliver how you give the beam delivery systems also, yes, besides producing the beam of the size required. This was the comment part. The question will be, madam, how the relapse of cancer happens. So, relapse. So, which of the three treatments you showed, surgery, radiation, and the drugs part, which one will prevent relapse? That part, which is, in your opinion, should be the best ones?
So there is something called there is a phrase in Tamil. I don't know how many of you know Tamil. Kamban veetu kattu thariyum kavi paadum. That is, there is a great, maybe Professor Rao will know. There is a great poet called as Kamban in Tamil Nadu. Okay. And he was so great a poet that even the building blocks begin to recite poetry in his house. So his knowledge was so great. But then, what I meant is that if we are in close proximity with Dr. Badwe and Dr. Sudeep, we can answer some of this. But when he is there, why will I answer that?
I leave it for him.
Request him to answer that question.
Your vast experience, Professor Badwe.
Expert and proper answer.
Your question needs probably one full day's deliberation between you and me, and we shall deal with that. Thank you very much. But in general, relapse is something that was quite a bit with single therapy. With multiple therapies, the relapse rate has come down. But the bottom line remains, right from Sushruta's day, relapse tumor was not curable, and today, relapse tumor remains incurable. You can control it. You can shake hands with it. But to eradicate that is not possible. So preventing relapse is one of the best policies. Thank you. Thank you very much, Prasanna. I would just summarize in one or two statements as to what I gained out of the session that we went through is that here is a view from various vantage points that were presented to us that at sub-gross level, whether molecular level, at particle level, there are some things that can be done. They will have an impact at the ground level. We need to understand how that happens. And that impact or that intervention and its effect at the ground level, how does it affect when it goes to a bigger picture? How does it affect our environment? How does it affect the whole humanity? Each of these are three different vantage points. And in medicine, we have a unique facility or unique opportunity wherein we can see at microscopic, submicroscopic, and at smaller and smaller level to understand what cancer is. We tweak something there to understand whether cancer as it affects individual makes any difference or not. And if it makes a difference, does it make a difference at population level? What our epidemiology people think that if I were to look at that I have cured some 30% improvement in cure rate of a cancer, does it change the mortality at the country level or at a state level? So at each of these time points, if there is a uniformity of findings of a hypothesis that may have generated at the epidemiology level, at the clinical level, or at laboratory level, if there is a uniformity across, then that much greater possibility that hypothesis is true. There are kind of discriminatory findings that we get sometimes or incongruent findings. There are lots of places wherein we find that the survival improves, but the mortality at the population level increases. There are so many areas where these kinds of findings are very foxing, and they're foxing only because we don't see the whole picture across. But here is an opportunity to understand that if you see the whole picture, and if you have an intervention that will improve at all three levels, that much better it will be, that much long lasting or sustainable or close to the truth it will be. Thank you very much.
On behalf of HBNI, I thank the session chair and all the speakers. We now move on to the second session, which will be chaired by Professor Gautam Bhattacharjee, Director of Saha Institute of Nuclear Physics. So please join me in welcoming Professor Bhattacharjee to the session chair's table.
It's working? Yeah, okay. So first of all, I take this opportunity to compliment Professor Vasudeva Rao to conceive this wonderful meeting. And as Dr. Badwe already mentioned, to bring people across different formats, life science people, physics people under one umbrella, as well as mathematics, professors and engineers as well. Now, I mean, for me, this is a wonderful opportunity as well to travel as long as 2.5 hours of flight after 2.5 years. I mean, this is the first time I did and I really enjoyed. Yesterday, I told this to Professor Rao. Now, I'd like to mention a few things like, you know, I mean, it is also very difficult to categorize a basic scientist, whether he is a life science person or a physicist or a mathematician. I'm giving you an example. In early 60s, in 62 or 1962 or 63, there was a guy, his name is Gilbert. He joined the Imperial College under the, you know, I mean, in the group of Abdus Salam to do particle physics. Now, he wrote only a few papers, Mr. Gilbert. One of them was kind of a no-go theorem of a very important theoretical physics question which was going on at that time. I mean, regarding something called spontaneous symmetry breaking. Now, the no-go theorem says that, that if you want to, create a particle which will eventually be a Higgs-like particle, it has to be massless eventually. You cannot escape that. Now, at the same time, a student who did his PhD in biophysics, if you could call biophysics in those days, in molecular dynamics, his name was Peter Higgs. He was entering into this, theoretical physics chessboard, and he was fascinated by this particle physics question. Now, what happened later on is history. Peter Higgs went on to bypass that no-go theorem, to drive home his point of view, which eventually got him the Nobel Prize a few years back. And Gilbert was he was not dejected, but by the time he wrote his influential paper in the 60s, he got a postdoc in Princeton, and he used to share the same corridor with Watson, and got fascinated in the DNA structure. Years later, maybe 10, 15 years later, with that particle physics background, he got Nobel Prize in life science on the DNA structure, and he was one of the first persons who worked on the Human Genome Project. So it is very difficult to categorize who is going to be what is he at this point of time. And Professor Mohanty mentioned about the usefulness of the Maxwell equation. I'm going to give you, another example where some interesting conversation happened between Michael Faraday and one of the parliamentarians in British Parliament. So Michael Faraday was asked this question: what is the use of your work on electricity? So Faraday answered, one day, sir, you will be able to tax it. So, and another thing which is a much recent, conversation between one American scientist, I don't remember his name. It was during the period of the Cold War. So he was called in the American Senate and asked, he probably, submitted a very expensive project, which cost a lot of money. And so there were a lot of questions in the parliament, in the American Congress. So the chief of defense staff asked him, and many people asked him many questions, that what is the use of your work on this, what you call basic science? He said that, you see that there is no immediate use the way you look at it. And this chief of defense also asked this question, is it going to improve our defense system? Because the Cold War is in the backdrop. He said it has to do, the answer was, it has to do with the respect and regard with which we treat each other. It has to do with the overall knowledge and the quality of society and the civilization that we are, that we think we should have. There is no immediate application in the defense system, but at least it will make our society worth defending. So that is the message that Dr. Chidambaram also mentioned. So with this background, and the stage is very nicely set with such wonderful talks. And we had a talk in physics, one in engineering, one already in life science. And now I'm requesting a mathematician, Professor Mahajan, Meena Mahajan, to present her talk.
Yeah, good morning, everybody. Maybe I should start by saying that I'm not a mathematician, I'm a computer scientist, and I'm going to talk about the theoretical computer science group at IMSc. Theoretical computer science itself is very mathematical in nature, and I admit increasingly nowadays that I myself am not sure whether I am doing more what would be termed mathematics rather than computer science. But let me come to that in a minute. In fact, the very next slide, I would like to position theoretical computer science within the field of computer science and engineering. So my basic training at a bachelor's and master's level was in a computer science and engineering department. And computer science and engineering applications are ubiquitous. Today, we cannot think of a society which functions without all that computers can bring to them. What computer science and engineering is giving us is going to change day by day. In fact, it is changing very, very rapidly, the nature of applications. Many of the engineering applications that I learned as an undergrad are not even being taught in today's curriculum because we have gone way beyond them and we are doing completely different things now. Today's students in their internships, they are doing very different kind of projects. So as technology advances, computer science and engineering changes, it is going to continue changing. But the theoretical underpinnings are not going to change. So even though curricula in computer science engineering has changed a fair amount, the theory curriculum has not changed that much for the simple reason that those principles remain as relevant now as they were 50 years ago, and they will probably remain as relevant for the next 100, 200 years. I cannot see beyond that, given how fast the field changes. So these underpinnings are constant. They are essential for understanding. They are essential for adapting and for upgrading abilities. This is something that we hear repeatedly from our counterparts in the IT industry. What can theory give to them? Do they look for a good theoretical training in the graduates that they hire? And the answer is a very unequivocal yes, because the theoretical training allows people to use whatever skills they have in a kind of transferable way across applications. You cannot go out trained in one application and say, I can do this and nothing else. And theory allows you to also make these shifts very easily. So what exactly is this theoretical computer science about? I've highlighted here this mathematical foundations of computation, which is why it's in some sense a mathematical science. What we are concerned with is trying to understand the very nature of computation. What exactly is computation? And when put this way, this is a philosophical question. And some of the questions in theoretical computer science indeed have been addressed even by philosophers several centuries ago. But we are also interested in exploring the limits of computation, limits both in terms of abstract machines as well as in terms of real world machines as they are being implemented today, as they may be implemented a few years down the line. We are definitely interested in looking for efficiency. So here one may think that this is probably a much more engineering aspect of it, that not only do we want computer-based solutions to various problems, we want the solutions to be efficient so that they can make a difference in the world. Within real time. The theoretical computer science group at IMSc is actually quite a small group. It's one of the earliest TCS research groups in the country. It was started in 1986. And within HBNI, there is TCS research in only 2 of the 11 institutes under this university, one at IMSc and the other at NISER. The core areas of theoretical computer science, almost all the core areas of theoretical computer science are addressed within this group at IMSc. Algorithm design, automata theory, combinatorics, computational complexity, and logical foundations of computer science. A very brief run through of what the group composition is and what is the scope of the activities of the group. At the moment, the group has 8 faculty members. It has remained a small group. From the time it started, the strength of the group has ranged from, when it started, obviously it was 1, but it was 5 or 6 for a long time, and the maximum it has reached is 9. We do hope to grow, but right now it is 8. And at the moment, we have 12 research scholars. The number of research scholars has varied between 2 and 24 at a time. I don't think we have ever crossed 24 simultaneously, but the number of faculty members is also small, remember that. Right now we have 4 postdoctoral fellows. So our students are our biggest strength, and I would like to have this one slide devoted to telling you what our alumni are doing. Since the time the group started, 60 PhD theses have been defended from our group. 52 of them have been after the inception of HBNI. And almost all our graduates are in academia. They are not directly going into industry. There are maybe 3 of them from what I can see who are in industry. They are all in academia. Most of them are in academia in India. One of our alumni, we are very proud to have been able to hire back. 19 of them are spread out across multiple IITs in the country. 6 are at the Chennai Mathematical Institute. And then there are others in various other engineering colleges in the country. So we are training theoretical computer scientists to go into departments which teach computer science and engineering, not just theoretical computer science. So in full-fledged CAC departments, they go and give the relevant theoretical computer science training to newer generations of computer scientists. There's of course a lot of transient population in the group as well. At any time, there are typically 0 to 5 postdoctoral fellows. Right now, there are 4. We have an active visitors program, but of course, this is nothing specific to theoretical computer science. This is true for the institute as such. We do have regular summer student program for selected undergraduates. Again, most institutes under HBNI do have summer student programs. One major highlight of our program is that the summer student program is conducted almost entirely by our PhD students. And very often the first and second year PhD students take the lead role in organizing this event, and it's a very good testing ground for them also. To see what it is that what kind of training they can impart to undergrads who come in with a somewhat inadequate notion of what theory can give to them. The main research areas, I very briefly mentioned them in one slide earlier. Here is a little bit more. So this is just a kind of laundry list of various buzzwords, but I wanted to put it out here. So in case there is anything here that catches your attention, that this is something that perhaps you were looking for, somebody with expertise in this, then there are people in IMSc who would be working on this. So algorithms, combinatorics, and data structures is of course the biggest group, the biggest research area in IMSc. And within that, there are many sub areas that I've listed out here. Computational complexity is a relatively smaller group. Logic, automata, and concurrency, in fact, right now is very small, but it is worth highlighting that this is the area of theoretical computer science with which the group actually started originally. And we hope that the group will, this sub-area will also continue to grow. Some research highlights, well, I mean, even though we are a very small group, in terms of publication statistics, our record has been very good, both at a national and at an international level. There have been several conference and journal papers. Maybe this is a good point to highlight that in theoretical computer science, conference publications are also highly prestigious. In fact, some of the leading papers in the field with breakthrough results have never been published in journals. They have only been presented at conferences and published in conference proceedings. So for us, conference proceedings are really very, very important, and we have been systematically publishing in very high-end conferences over the years. Our group members have participated in many prestigious international research seminars. And ACM India, which is a body which started in the last 10-15 years ACM is the Association for Computational Machinery. The India group started about 15 years ago. They instituted the doctoral dissertation awards 10 years ago. And 3 theses from IMSc have been honored in this series. They instituted the Early Career Research Award 2 years ago, and the first inaugural award went to my colleague in IMSc. So more about, I've mentioned here Saket Saurabh, whose research is really been making waves in many ways domestically as well as internationally. And I will talk a little bit more about his research also soon. In terms of participation in the research community, there's one thing about the international community. In the international community, this slide is just to say how we are positioned. Our faculty are on the editorial boards of top journals. They're reviewing and on the program committees of most of the top conferences and journals in the field and so on. At the level of research collaboration, they have collaborations with multiple groups across the world. But within India also, we have active collaborations with researchers. As far as I know, this is the current list of institutes, but there may be more because I did not individually check with all my colleagues. IIT Hyderabad, IIT Jodhpur, NISER Bhubaneswar, and of course, Chennai Mathematical Institute, which is with whom we have always had very close ties since their inception. IMSc, the Theoretical Computer Science Group, has taken the lead in organizing many multiple events at many different levels, starting at research level workshops, instructional schools for graduate students as well as for college teachers, conferences which report on research findings, refresher and update meetings also for faculty at engineering colleges. Most recently, just last month, there was this event called the Recent Trends in Algorithms, which was organized jointly between IMSc and NISER. In terms of contributions to education, again, the group, which has always been very small, but has played a very major role in on the domestic front in formulating curricula for computer science with particular attention to theoretical computer science. So many advanced elective courses in theoretical computer science have been designed for our graduate students and have been offered to our students, but with also participation from students in other neighboring institutes. Several of my colleagues have also done distance teaching for institutes elsewhere. This is not just during the pandemic. We've been doing distance teaching for the last 10 years or so. Short instructional schools at multiple venues have been organized by my colleagues, and also my colleagues have contributed as resource persons when other groups are organizing such events. My colleagues have been on the have been members of boards of studies for many institutes, and they are contributing to development of curricula, syllabus, academic procedures, and so on. They play an active role in both these national bodies. ACM India I already mentioned, and a much older body, IARCS, the Indian Association for Research in Computer Science, has always had very strong participation from IMSc. So now in the rest of my presentation, I want to focus on two research threads where people in IMSc have been pursuing research. I would like to briefly tell you what these research threads are about and what kind of work is being done at IMSc. So these two threads that I have picked out, one is formal methods for verification, and the other is multivariate algorithm analysis. And the reason why I've picked these out of those many, I had a slide with many buzzwords. I picked out these two simply because these are the ones which are most likely to lead to more interdisciplinary collaboration. Not necessarily that these are the largest groups, but they're most likely to have to bring something of interest across groups. Okay. So let me start with formal methods for verification. What exactly is this area about? Well, we use programs, we use computers, computer systems, we use algorithms to solve many varied tasks. In some cases, the use of computers just makes our work simpler. It's convenient to use them. In some cases, it's high stake. Maybe the high stake is money. You know, you save an enormous amount of money by using computational power. If you didn't have it, you would not be able to save that money. And in some cases, it's absolutely critical. Without throwing computational power at this problem, you simply cannot solve it with the information that is available at our hands today. So there are these many varied tasks. There are programs of different types, different sizes. And especially when we come to the high stake programs and to the critical programs, we need some confidence that these programs that we are using are actually correct. We cannot be in this situation where you throw a problem at a machine, it spits out an answer yes, and then you go ahead and build up a whole lot of stuff after this, assuming that that answer yes was correct. Ideally, programs will log proofs. They will also tell you why they have given a particular answer. But often the why of the answer is too long. You know, you can't write it down and then check it. So we need some way of developing this confidence that the answer given has been correct. And well, one way to develop such a confidence would be to extensively test the program. Testing certainly helps in building up that confidence, but it's not comprehensive enough. So this is where verification comes in. Verification aims at formally proving correctness, not just testing on specific instances, but formally proving that no matter what kind of input instances are given to this program is going to be correct. So how are you going to do something like this? For the first thing, you need to specify what are the correctness criteria. You're trying to prove that a program is correct. What exactly do you mean by correct? Can you write it down in unambiguous terms? This is where we need formalisms from mathematical logic. Mathematics is the language which kind of banishes ambiguity. So when we want the unambiguous formalisms, mathematical logic is absolutely the right language to look for. We also need to model the programs and the systems, because programs and systems can vary. The same algorithm implemented by two different programmers running on two different machines, the code could look different, but it is essentially doing the same thing. And the right abstract model should be able to take these two things and produce the same abstraction out of them, so that one proof of correctness will work for both. So we need abstract machines to model these programs, and the answer to this is provided by automata theory. Both of these are areas which predate the actual use of real-world computers. Mathematical logic is centuries old, but automata theory has also been around much earlier than real computers have been in the real world. And we're trying to bring these two together to kind of come up with a program by which we can, a research program by which we can prove the correctness of programs. Now, in general, what's going to happen is that the system and the correctness criteria could both be quite complex. The ideal goal would be that somebody should be able to write this master program. And this master program, you give it as input program 1 and a correctness criterion. So the description of the program and a correctness criterion. And your master program says yes, no, with perhaps some reason for it. Now, unfortunately, this is something which is not just difficult. This is a theoretical impossibility. And this goes back to the work of Gödel and von Neumann. We know that such a program simply cannot exist. So now this tells us that we are perhaps being too ambitious. We need to scale back. Do we really need a program which can give such answers against all possible abstractions? Not necessarily. So we're going to look for answers in restricted settings. And what we would want to look at is, let's start small. Let's assume that the correctness criteria we're looking for is something very simple. For instance, it could just be that you have a system of printers and print requests which are coming, and the program which is scheduling jobs and sending print requests to different printers should not keep sending everything to one printer and let the other printers lie idle. So you want to formulate this somehow in the language of logic. A correctness criterion would say that the jobs are being distributed across all printers, printers don't lie idle, and every job eventually gets serviced. This is a reasonable criterion. It's simple enough also. Then we want to identify appropriate abstract machines. And these are, like I said, mathematical models for real computers. So these models, they should be expressive enough so that they can model the system that is at hand. So they don't need to model every possible computer system in the world, but the system that we are trying to analyze, the abstract model should be powerful enough to express what it does. At the same time, it should not be so powerful that answering this question for those computers is theoretically impossible. There are these theoretical limits and we should not hit those. So we want it to be powerful, but not too powerful. And then finally coming to the engineering question, we want these models actually to be simple enough so that not only are there programs which can answer these questions, but those programs are efficient. If those programs are going to take years and years to deliver their answers, then again, it is useless. We cannot really use them. So these are the challenges that we face in finding what are the right mathematical models to deal with the verification problem at hand. So many of the tools which are actively employed in the industry are based on this technique of verification, identifying the right mathematical model and using the right language from logic. And in our group, there is active participation in these research areas. In particular, here are two threads which I have picked out. One is that modern day programs are often, they are not like monolithic programs running on one single computer. They are often cooperating processes running on multiple multi-core systems. They are multi-threaded. Several things are happening in parallel, and then they have to talk to each other in an appropriate way. So then it is not just a question of modeling the actual step-by-step computation, but you also need to model the communication. And modeling communication turns out to be quite hairy. It brings a new set of challenges because now you need to ask whether the communication is synchronous. Is there a fixed clock and you know that at every time step some message is exchanged? Or is it that one party waits for a message until it comes and then responds a completely asynchronous way? If it is asynchronous, then how do you know whether a message is coming at all, and when do you give up and move on to the next phase of communication? So modeling communication throws in new challenges, and the models need to be completely revamped. So the abstract models of automata theory, which are now 50, 60 years old, are not adequate to directly talk about communication. They need to be adapted in non-trivial ways. And this is something where members of our group have been working on. So that's one thread. Another thread is that modern day architectures and compilers, they often, they have all kinds of built-in optimization techniques. So A programmer may write a program to solve a program and feed it into the computer and think that, it's going to run exactly the way it is written. But that's not always true. So internally, once the program is compiled, there may be an optimizer which kicks in, which may reorder the instructions, which may break up parts of the code and give them to different processes to be run in parallel and then occasionally meet and synchronize. So in particular, this reordering of instructions, because some kind of parallelism has been detected and therefore it is okay to reorder. This is what is called relaxed memory models. It is done so that execution can be done faster. But once you allow relaxed memory models, then the correctness criteria have to be changed considerably. So maybe till around 10-15 years ago, the correctness criteria, the way they were formulated in the language of logic, they were not taking this feature into account. So it was assumed that the program ran in a particular way as specified. But the moment these reorderings come into the play, some of the conclusions that were being drawn earlier are no longer valid and have to be reworked. So the programs need to be checked for correctness under these assumptions. This makes the thing, again, way more challenging and calls for newer techniques. So my colleagues are working on developing techniques which can allow us to talk about correctness even under even in such circumstances. So to give a very brief flavor of the kind of, so here is one paper by my colleague Prakash Saivasan with multiple co-authors, which is looking at one particular correctness criterion, which is reachability. So there is a kind of, there's a large system and you talk about the configurations of the system. There is a target configuration which you would like to reach, but you're starting from a specific configuration. Do you ever reach that target configuration? So reachability is the correctness criterion says that yes, you reach that target configuration. There is a specific formal model which is being talked about here, PX86. And what is being done in this paper is to show that for this particular system and this particular correctness criterion, indeed, the problem is decidable. Now, this seems like so far away from what we really want in practice. All we are saying when we say that the problem is decidable is we're saying that it is not impossible, it is possible. There is an algorithm that can solve this problem. That's all we're saying. For that algorithm to be actually useful, that algorithm will have to run in a reasonable amount of time. It will have to run using a reasonable amount of memory. All that is still far away. But the first step, proof of concept, would be to show that it is decidable at all. Because if it were not decidable, then there is no question of finding an efficient algorithm, if there is no algorithm at all. So in this paper, they're showing that this question is decidable. And this is a paper which was presented at this Principles of Programming Languages conference. So you can see that in very cutting edge recent research, questions of decidability have not gone away. And these are for real world problems that are, this is this Intel 86 architecture is something that we are using all the time. Reachability is a correctness criterion that would come up in many, many different contexts. But even there, something as basic as decidability was not yet known and is now been shown last year. Scaling further beyond this, here is a very different kind of algorithm, a different kind of result, which does not, where the correctness criterion is now consistency. There's a certain large system and you are asking, this is one of those relaxed memory models. So you are asking whether an inconsistent state is ever reached in the execution of this program. So the model has changed, the correctness criterion has changed. In this case, decidability was not an issue. And what is being solved in this paper is to show that there is in fact an efficient algorithm under certain conditions. So in general, consistency is a very hard problem. There is a buzzword here, NP-complete, suggesting that it's very hard. But in this paper, these authors have shown that fast deterministic algorithms can be designed under certain situations. So this is the flavor of the kind of work that is being done in this thread, formal methods for verification. Okay, having said that, let me move to the second thread, which is multivariate algorithm analysis. Here, so what are we talking about? Well, as I already said from the previous slide, we're not just seeking algorithms for problems, we're seeking efficient algorithms. right? Without efficiency, those algorithms are no use. So how do we measure efficiency? Again, there are theoretical ways of measuring efficiency. There is a mathematical model. So it's clear that you have a program which solves a problem of a certain type, and you give it inputs of different sizes, the time it will take will differ depending on the size of the input. So the runtime of a program is bound to depend on the size of the input. It will grow with the input of size. It should not grow exponentially. That's what we take as a working definition of efficiency. Preferably, we want the growth to be polynomial. So for inputs of size n, the runtime should be n square, n cube, n to the 100, not 2 to the n. That would be bad. So now, if this is our definition of efficiency, then there's a vast array of computational problems which are practical, which we are interested in, and for which there are no known efficient algorithms. The theory of NP completeness, in fact, is providing evidence for why these problems are hard. It's saying that they are all kind of related to each other, they encode each other in a certain way. And the best minds in the world have so far not succeeded in coming up with efficient algorithms for these. But the problems don't go away. The problems still have to be solved. Protein folding is an NP-complete problem, but it is something that we need to do all the time. And yes, we do have solutions for them. How did we manage this? So there are ways to cope with NP hardness. What we would want to do is we want to confine this exponential growth to runtime in restricted settings. Recognize that, okay, there are going to be inputs where any algorithm is going to take a long time, but maybe the inputs that we are interested in are not those bad inputs. So this whole NP hardness business is a worst case construct. And let's recognize that in practice, most inputs are not worst possible inputs. So those in practice inputs, can we at least solve those? How do we recognize what are the features of those inputs that are arising in practice that we can exploit? So we would like to use specific information about input instance classes to devise better algorithms. And this is the field of parameterized algorithms. We would like to analyze the algorithm performance in terms of different input parameters. It's not just input size n, runtime 2 to the n, oh, this is bad. There are multiple parameters which characterize what is the input description. So there is the input size, there are structural parameters about the input. You can look at all of them and say, how does the runtime behave on all of them, in terms of all of them. So that is what we call multivariate analysis. So you have one algorithm which solves one problem and you want its runtime analyzed in terms of many different facets of the input, not just a one-dimensional analysis, but a multi-dimensional analysis. And even in such settings, there are still problems that remain hard. So you want to develop tools which will provide the evidence of hardness in such settings, and that's parameterized complexity. So in our group, we have very active participation of our group members in these research areas. In particular, exploiting budget bounds. This is what I call parameterization by solution size. A fairly simple example of this would be, if you look at the problem of, given a large network, there are towns and there are roads connecting them. And let's say that some service provider wants to choose certain towns as hubs to locate some facility. Ideally, you would like that every other town is reachable from a hub location by one hop. Okay? So now what is the minimum number of hubs that you would need to open so that you can cover the entire network? This is a problem which, stated like this in full generality, in worst case, is NP hard, which means that there is no known efficient algorithm. We do not even believe that there is an efficient algorithm. But yet in practice, we do solve this problem all the time. And the reason why we often succeed is because a practical setting is not going to say that, your network has 1 million nodes and maybe you're being allowed to set up 500,000 hubs. Typically, the number of hubs you would be allowed to open is some limited number based on what resources are available with the service provider. Maybe 20, maybe 100, some very small number. So now if your algorithm is going to take time, which is exponential in the number of hubs, it's not a big deal. The number of hubs permitted is anyway so small that exponential in that is fine. Exponential in the size of the network is not fine. The network has, maybe 1 million nodes, exponential in that, your algorithm will time out. But you could allow runtime, which is a huge, fast-growing function of the solution size. So this parameterization by solution size often gives algorithms which are efficient enough in practice. And it calls for a different kind of design of the algorithms. The algorithms themselves are supposed to keep in mind the fact that, look, here there is this budget which is small and I should use the fact that it is small. So that's the first thread. The second one here is parameter, like pushing the limits of how efficient you can make these kind of algorithms. So you want to parameterize not just by solution size, but above guaranteed values. So for instance, maybe you're given the network, you have said that I don't want to open more than 100 hubs. And I know already looking at this network that minimum 50 is needed. So now how much more than 50? Now that is an even smaller number. And can you confine your growth to that increment over 50? Maybe you can. There are many interesting settings in which, yes, algorithms of this kind have been designed. So that's the parameterization above the minimum guaranteed value. The third approach is exploiting structural properties of the input. So going back to the same example of a network, networks could be arbitrary. I mean, you can think of the Facebook network of how people are connected to each other, or you could think of a disease spreading network, people and who is communicating, transferring germs to whom, and so on. And these could, in principle, be completely arbitrary. But in practice, they are not arbitrary. And here is one structural parameter that has turned out to be extremely useful in exploiting features of the network. Tree width. Tree width is a measure of how far away is this network from being a tree. So a network is a collection of nodes connected to each other by some links. A tree is a network which is minimally connected. It is a network, it is everything in it is connected to everything else, but there isn't even a single redundant link. If you remove even one link, the network disconnects. That's a tree. The tree width of a network is a measure of how far away it is from being a tree. And what has been observed is that in many, many instances of practical problems, so in the worst case, a network which has 1 million nodes could have tree width 1 million. In practice, the networks which arise in practice very often have much, much smaller tree width, logarithmic in the input size, or maybe even sub-logarithmic. So you could exploit that to come up with more efficient algorithms. Am I out of time? Okay, so let me. This was just talking about what is happening in multivariate analysis, and now let me very briefly show you. So here is a handbook chapter written by my colleagues Venkatesh and Saket on fixed parameter algorithms and complexity. It has been a very useful resource for people in the community. There are these 2 textbooks authored by my colleague Saket along with many of his international collaborators, parameterized algorithms and kernelization. Kernelization is what is harnessing the power of pre-processing. So many important techniques are very nicely described in this, and this would be a very good starting point for somebody who needs more information here. I had also picked out, as I did for the formal methods thing, 2 papers to highlight here, but maybe I will skip this completely because it's not that important. And yeah, with that, thank you very much for your attention.
Comments?
It's a non-specialist question. Maybe Dr. Bhattacharjee is somewhere in the audience. He may be able to phrase it better. I am just trying to think that with regard to the nuclear reactor safety, whenever there's softwares are written to run the safety systems, I have heard in many meetings of safety committees and all that they use the word verification and validation of those software. I don't know whether that is linked to this, but I thought it's a very important application in that case, if it is so. Just I wanted to have your comment.
So is it linked? Well, it is exactly the same area of verification that I talked about here, and the verification done there does use formal methods. So the work which I talked about is at a much more theoretical level. but it is people who do this kind of verification who have also been talking to the verification team, not from IMSc, but I think the group from IIT Bombay is involved in this verification, in some of the verification work, I believe.
Maybe Dr. Tiwari can. Anup is.
Yeah, thank you, Professor Vasudeva Rao, for pointing out this important question to Professor Meena Mahajan. Yes, indeed, we had a a big collaboration with IIT Bombay. In fact, looking at two aspects. One was that how do you use formal verification for specifying and verifying important properties of control systems. In fact, it was a very large collaboration with IIT Bombay. The other thing that we also looked at was, in fact, how do you have talked about programs. In fact, how do you analyze programs using abstract interpretation? So, in fact, I remember I was attending a talk by Professor Patrick Couso in TIFR way back in 90s. When he talked about abstract interpretation, how it can be used for analyzing program properties, runtime properties. So in fact, this is one of the area where BRC had put in a lot of effort to understand that how these techniques can be used. And to a large extent, I think one group was there in BRC, which was quite involved into using these techniques. And I could actually could make out that whatever you have talked about in terms of collaboration, how effective this collaboration could be in the HBNI framework between BRC and IMSc. So thank you, sir, even pointing out this. So this is definitely important.
Yeah, thank you.
Because we have run out of time and I don't see any other hand raised. So let's thank Dr. Mahajan.
Thank you.
And I now request Dr. Debasis from BRC to take the stage.
Before this talk gets ready, a very good afternoon to all of you. And thanks to the organizer for arranging this nice meeting, which will enable the effective collaboration among the CIs. So I will be talking about the condensed matter research at BRC. Yeah, just. Thank you. So the condensed matter research at BRC is very rich. At the same time, it has a very wide spectrum. So in the next 30 minutes, I will try to give a glimpse of the condensed matter research at BRC and hope I will be able to make a proper justice of it. And now the plan is like this. I will discuss about the facilities and research and developments in this area, and then a glimpse of research in this. But I will be mixing these two during the course of the talk, and then I will summarize and future outlook. So condensed matter is basically, it concerns about the atoms and the atomic clusters which are very close proximity, and because of their interactions, there are very nice collective and cooperative phenomena occurs. And as a condensed matter physicist, we try to understand these properties and these important length scales which govern this condensed matter is starting from 1 angstrom to say 1000 nanometer, which is a very wide length scale. And at the same time, the dynamics also typically sub-picosecond to femtosecond order, and that also governs the various properties of condensed matter. So our aim also will be to understand this length scale and this dynamics in this very condensed matter systems. So this shows that, okay, there are various interesting condensed matter systems starting from crystals to nanoparticle systems and then various large scale structures. And this all covers the condensed matter. And the research and development directions in BRC mainly constitutes these terms, what I have mentioned here, like this magnetism and crystallography, soft matter, functional and energy materials, then dynamics in various materials, then also very important materials under extreme conditions, and also computational condensed matter physics. Then in development directions, there are several arenas, like primary thing is neutron-based instrumentation and synchrotron beamlines. And in addition, of course, there are something cold neutron source, neutron guides, detectors and sensors, which is very important, mass spectrometer, superconducting magnets, and of course, a very good initiative has been started for this quantum technology and then thermoelectric devices, etc. So, why these neutrons and these X-rays are important? Because of their particular property, which this thermal neutron and these X-rays, typically of the order of 5 keV to 20 keV, they have, I have listed down this property, and in fact, they are complementary in nature. And using these two probes, we can probe this various condensed matter and their structure function correlation we can establish with this. Now, when we do this either neutron or X-ray scattering, the data is in basically in reciprocal space. And then I have tried to elaborate this in like this with a, which is analogous to say physical optics like single slit diffraction. When I have very small slit, this scattering is over a broad angle, but when I increase this slit size, it is concentrated at very small angle. So basically it happens here also. When I'm interested in the crystal structure, the information reflected at higher angle or higher Q, which is nothing but the wave vector transfer, which is depends on the scattering angle. And also the vice versa, when I'm trying to look the larger length scales, it will be reflected at smaller angles or small Q. So now, first I will come to the neutron facilities, which is around the Dhruva reactor. And we can see that there are several neutron facilities here around the reactor. And we also have a guide tube where the neutron is transported through neutron guides. And there also we have several facilities in this guide tube hall. And this facility is operated, all these neutron scattering facilities operated by Solid State Physics Division of Physics Group, BARC. Now, as I told that I will try to give in between also a few examples in one of these directions. So first is this magnetism and crystallography, which is very important. And for this purpose, there are several facilities like different powder diffractometers, polarized neutron spectrometer, single crystal diffractometer, and high Q diffractometer for the non-crystalline or glassy materials. At the same time, we have the complementary facilities like physical property measurement systems, magnetic refrigerator, Laue camera, then setup for spin-Sivak effect, Mossberg spectroscopy, XRD, and magnetotransport measurement. Also, for preparation of samples, there are several interesting sample preparation like optical floating zone furnace, and there are other also sample methods for hydrothermal synthesis for making low-dimensional magnets. So before going to further, let us try to give one example in these directions. As we know that the classical phase transformations are basically controlled by the thermal fluctuations. However, in a quantum systems, basically quantum fluctuations play a very important role, and this low-dimensional magnetism, magnetic materials effectively provides a nice playground for validating these quantum states or to understand these various phenomena in the quantum states. And let us see, if we see this triangular lattice, it is a story of, say, three lovers. If these two spin states, they are in opposite direction, the third spin, it doesn't know where to go. So there is some kind of quantum fluctuations. And because of these quantum fluctuations, one of the expression is that even at the low temperature, there is a not long-range ordering in this system. So in this, like this, we have shown here that one Kagome lattice, this term Kagome has come from the Japanese bamboo weaving basket. So this kind of lattice, we can see that there is a strong change in the magnetic entropy without ordering. And similar things like this honeycomb lattice, we can see the presence of commensurate and the incommensurate structure where the magnetic structure is not in integral multiple of the chemical structures. All these things can be obtained from this neutron scattering. So similarly, 1D triangular chain, 2D Kagome lattice, anisotropic triangular lattice, etc. are this. Here also, the lack of long-range ordering is a signature and of the possible spin state, liquid state in this system. So a large number of work is going on in these directions, in these systems. Another example is the, say, sodium ion battery is a very important material now in, just to replace the lithium. So now this is a layered material where the we can, by neutron scattering, we can get how the sodium pathways here provides the percolation path for this current. And this can be, here it is shown that the stacking disorder controls the ionic conductions in this kind of layered materials. So this was the quantum materials which are being studied here. And to connect this, there is a very interesting and significant progress which is now taking place in this direction is the technology for quantum computations. So where, as we know that in a classical computer, with respect to this, there is something called quantum bits, and n quantum bits is equivalent to basically 2 to the power n of classical bits. So it's a huge computation power is increased. And in this direction, there is a development work which is being initiated here, and it depends on the quantum entanglement and the superposition. So it depends on, and it uses the Josephson junction. So there is a significant progress which is taking place in this direction at BRC. So now, we have already talked about crystallography and magnetic systems. Now, soft matter, nano scale materials, and surface science, it is another important arena in this, which is being pursued with the neutrons as well as X-rays. So for this purpose, we have 2 small angle scattering diffractometer at the Guy Tube laboratory and 1 reflectometer. Similarly, we have the complementary facilities like nano imaging facilities, field emission scanning electron microscope. We have also this small angle X-ray scattering beamline at Indus 2 and laboratory-based SACS facility, dynamic light scattering facility. And sample preparation also we have like a soft matter lab and the spray drying facility for making these nanostructured microgranules. And for thin films, we also have the sputter ion deposition, sputter deposition facilities. One example in this direction that the soft matter system is very useful in the various pharmaceutical companies, and where the stability of the soft matter system is very important. In this example, here it is shown that there is a reentrant phase which controls the stability of this kind of soft matter, where the optical transmission becomes very low in between, and then again increase of the salt concentration, it increases. So there is a not usual, it is some kind of unusual stability in the soft condensed matter system. Again, this kind of, normally if you, some protein solution, if you put some salt, it gets aggregated. But here, because of this some kind of zirconium salt, this opening of this chain, unfolding of the protein is prevented. And then the stability still remains, and this small angle scattering can give this kind of detailed quantitative information for understanding this kind of protein unfolding and the stability of this. Another important thing, I'll try to see this one important technique which is used in industry is called spray drying, where we take the advantage of very high surface area by atomizing the droplets, colloidal droplets. And what happens in this case, when this droplet passes through a hot chamber, there is evaporation-driven assembly in this system, and by these nanoparticles get interlocked in this system, and finally we get this kind of granules, which are nanoporous or mesoporous granules, and these has various applications. But physics-wise, there is interesting applications that during this process, there is a viscoelastic transition, and then there is a buckling of the system. So sphere, basically initially droplet was sphere, and then finally we can get a donut-like thing. So sphere to donut-like transition is very important in these systems, and we can use the small angle scattering, taking all these 2 instruments and a small angle X-ray scattering system so we can quantitatively analyze the correlation and this transition in this kind of materials. As it was mentioned, that directed basic research is also very important for the sustainable development. For these granules, we tried to get some applications where we created these granules with E. coli bacteria and the silica nanoparticles. And this, because of the shape matched pores, this from the this E. coli in the water can get trapped into this kind of granules, and we get the pure water. Of course, this kind of granule also can be incorporated in the ultrafiltration desalination membrane, and which increases the flux almost by 2 times. Another important application is the electroresponsive applications of these granules. Under the electric field, these granules get aligned in a particular directions. So these are some attempts to use these granules for some practical purposes. As I mentioned, that the neutron can also give the information about the surface. So here there is a strong work which is going on in the thin film and multilayer domain. So here this reflectivity profiles can give effectively the depth profiling of the magnetization using the polarized neutrons. So here it is I have shown an example for the copper and gadolinium multilayers in this system, and the alloying can occur depending on how the samples are prepared. This alloying depth profile is different. It is shown here. And normally this alloying occurs in bulk system at very high temperature, but normally it is this iron and germanium alloy system, it occurs almost at 250 degrees centigrade, but which otherwise occurs at 700 or 800 degrees centigrade. So this kind of how the interface is changed by this different processing, so it can be quantified by this kind of neutron scattering technique. So far I was discussing about the structural part. Now there is a dynamics in functional materials. So there are 2 instruments, like one is triple axis spectrometer, another is quasi-elastic scattering spectrometer. Of course, as a complementary technique, we have Raman scattering spectrometers for this understanding this the vibrational and dynamics part. Here one example that normally when the neutron is irradiated, in the reactor there is some graphite, and then this graphite there is a formation of this kind of because of this irradiation there are some defects, and it was shown that this in fact this 2-fold, 3-fold and 4-fold this Frankel defect, it occurs in this system, and when these are annealed at higher temperature, normally it releases the Wigner energy. So the mechanism of the Wigner energy was understood through ab initio calculations and experiments. And one interesting thing is that this kind of, because of this irradiation, the graphite becomes magnetic, and magnetic behavior sustains even up to 850 degree Kelvin. So this is one kind of dynamics part, what I mentioned. Now another dynamics is where there is a slower dynamics in the system, which is called stochastic dynamics. That means this chain is there, a long chain, and how they rotate, or this rotational frequency, or all these things can be measured by quasi-elastic neutron scattering. And here is an example of metallosurfactants. After putting this cholesterol, which arrests the local fluctuations, and the motion becomes slower. So all this quantitative information can be obtained from this quasi-elastic measurements. Now there is a lot of developmental work which is going on in this National Facility for Neutron Beam Research. One is the cold neutron source for the high flux research reactor, which is going to come at VISAC. And there is a upgraded triple axis spectrometer at Dhruva, time of flight spectrometer at Dhruva. These are all ongoing projects. And as I told, that neutron can be transported through the multilayer guides. So there is a now attempt to change this old guide by this new multilayer guides, which is nickel titanium based. Another important developmental direction is the development of this 2-dimensional position sensitive detector for the neutrons. So all these are ongoing developmental projects. So now I am switching over to from neutron to the X-rays. So Indus is the workhorse for various X-ray scattering experiments, as I mentioned. So BRC has here 9 facilities at this Indus 2, and which deals with various physics problems like crystallography and protein structure, local environment and ionic state, imaging, then mesoscopic structures, electronic states, etc. So these are the beamlines, imaging beamlines. Then there are 2 EXAPS beamlines, which are scanning EXAPS, and this one is a dispersive EXAPS. This is extreme condition X-ray diffraction beamline. This effectively gives a very nice idea about how the material behaves at extreme conditions like very high pressure or high temperature. Then there is a photoelectron spectroscopy, which gives the electronic states in the elements. There is a small angle X-ray scattering beamline, which deals with the nanostructures. Then protein crystallography beamline, and this photoemission electron microscope beamline, which is under construction, and another beamline, which is AMOS beamline, which is also under construction. So the protein crystallography is a very important field. As you know, that growing protein crystals is really difficult, and how to understand their structure is through this protein crystallography. One of the example is that these thyroid hormones, it expresses this various working function of the genes, and during the resorption of the tadpoles, this is basically the frog, and this resorption mechanism, which was understood through this protein crystallography. And this is one protein which is called PAP, which is something like 242 amino acid long protein. And then which was seen that there is a nice loop which gives to this catalytic or the triad assembly effect in these systems. So X-ray and neutron imaging is a very important thing, because through 3D tomography and the X-ray imaging, we can see X-ray and neutron imaging. Of course, they are complementary. We can see how the material is inside. There directly we can see, and there is an example of the various bone which are tested with this imaging technique. So this can give, as you can see, that with this 3D tomography, we can get the detailed structures of this bone and this kidney stones. Okay, as I told that EXAPS techniques is very important. And one example from this EXAPS technique is that this lithium-ion battery is very important, and the understanding of their charging and discharging property through these EXAPS techniques has been done, where it is shown that the manganese ions exist in both +3 and +4 oxidation state, and then during the charging that it goes to Mn4+, and the discharging, a non-uniform octahedral oxygen coordination is affected. And basically, this kind of in situ experiments can be done at the Indus synchrotrons. So, okay, another just example I would like to tell here, that cementation, because of the high carbon dioxide emission, this normally use of cement is now already, people are searching for the alternative for the cements, and that's why these pozzolans are very important. And how this, as I mentioned earlier, this spray-dried microgranules, silica microgranules, these are one kind of pozzolans, and how they behave with calcium hydroxide with time. So how this cementation takes place. So in situ small angle X-ray scattering experiments have been performed, and it was shown with the from the experiments as well as from the computations that the dynamical scaling, which normally takes place during this gelling formation, it breaks in this system. Probably this is because of the confined system, because in the interstices this reaction takes place, and this interstice is confined, very small nano confinement. So because of this dynamical scaling breaks. So these kind of physics problems can also be done using the in situ experiments at Indus 2. Okay, the materials under extreme condition is very important, because why it is important? Not only from the understanding the fundamental physics points of view, but at the same time, we can show that materials which does not exist in normally in the nature, it can be prepared under this high pressure or at high temperature. So what is happened that there is a diamond anvil cell which provides the pressure say up to 40 or 60 GPa, and then this kind of experiments with X-rays can be done. And here is an example that we are aware of this KBR, which is known, but this here it is shown that different kind of say KBR5, this kind of KBR3, this kind of transformation can take place under the pressure. So this is a very interesting thing, but at the same time with experiments, we also have the computational skills where see for a many electron system, it is very difficult to solve the problem because too many degrees of freedom. So they take different approach either by Hartree-Fock equation. But again, this taking the consideration of the whole orbital is important in this case. However, the density functional theory gives a relief, and with this density functional theory, various calculations have been performed, like this nuclear materials, where thorium nitride, uranium nitride, protactinium, and then they have shown that different kinds of phase transformation, how it validates with the experiment. These are theoretical calculations, and it shows, it predicts that there is a transition at 60 GPa. And of course, this role of F electron is very important in this kind of system, and these calculations, such kind of calculations can predict this. And of course, this phonon dispersion, which is the first derivative from the energy, and that kind of thing can be obtained from this kind of equation of state, which has been basically to validate the experimental thing as well as to predict the property at high extreme condition. At extreme condition, say when the material from bulk it goes to a monolayer, there is a nice prediction that this kind of thing can give rise to a superconductivity in this system, which is called LIBC system. Here it is shown that the sp2 hybridization which exists in bulk, and then after pressure, it goes to, after this monolayer formation, it goes to a partially sp3 hybridized systems, and that gives rise to this superconducting behavior in this LIBC system. So now, after this, I will enter in the development part. So development, so as we know that there is a various waste heat which can be used by taking into about the Seebeck effect. And this thermoelectric materials, where there is a strong, significant work is going on in this direction on different kinds of thermoelectric devices, and like this BI tellurium system, then lead tellurium system. And what they have done is this figure of merit is one thing, another is the efficiency of these thermoelectric devices. So here it is shown that over the years in this BRC, how their figure of merit, it goes up to say 2 here, and the efficiency wise also, it has reached something like 6 to 8%. Here it is next one shows that they have also got an efficiency of the order of 8.2% in this kind of bismuth telluride systems. Okay, another directed basic research is the surface modifications. By surface modification, one can create the anti-reflecting superhydrophobic surface, where you can see that this, because of the superhydrophobic surface, the contact angle is basically very high, and we can get a spherical droplets here. And how it is done? Basically, when the water droplet can rest on the nanopillars. So here it is shown that the FECM that how the spatially selective nanoplasmonic response occurs in this kind of nanostructured surfaces. So now, another important direction is the development of superconducting magnets. There are several high-intensity superconducting magnets which are developed here, and these are used for various studies, including this MHD. And here I have given the 4 examples where this 4 Tesla or 3.6 Tesla and all these magnets are already created, and these are very useful for these various experiments. Another one direction is the crystal growth. Single crystals are very efficient for not only for this understanding the fundamental thing, but also for the gamma ray spectroscopy. So in a BRC, there is a strong group which they are working on the synthesis of the single crystals to the Bridgman technique, which needs a small seeds and then growth of the crystals. So here is an example of cesium iodide crystals, and then another kinds of scintillators, all these kinds of scintillators and very large crystals which are prepared here. And one important thing is the germanium single crystal, high purity germanium single crystals. These are also made, and with this, with such kind of high purity germanium crystals, this HPG detector has been fabricated, and which shows a very high resolution. This SAR peak shows the very high resolution which can be achieved by this kind of detectors. Gas sensing devices is also important, which can differentiate that which kind of gas, whether it is H2S or whether it is NO2. So these gas sensing devices depends on the this kind of nano rods, and depending on the morphology of these nano rods, the efficiency and the depends on this kind of system. And we are in BRC, there is a significant work which is going on these gas sensing devices. Mass spectrometer is another important field, and there is several kinds of mass spectrometer, including the helium leak detector, which also uses this mass spectrometer, and this technology is transferred to various companies, as you can see. There is again this kind of different kinds of mass spectrometer, including the inductively coupled plasma mass spectrometer, and then electronics and associated instrumentation for this kind of thing is also developed here. And like the sputter and pumps, vacuum gauges, all these things are really essential for various condensed matter experiments. And like this ultra low level hydrogen gas sensors, these are which can measurement range up to 2500 ppb. So these are like this cryo finger for the cooling of this high purity germanium crystal, as I mentioned earlier. So all these things are built indigenously here. So I will summarize now. So condensed matter research using large scale facilities, basically indigenous facilities at NFNBR, Dhruva, and the synchrotron at Indus. Basically, we look at these fundamental aspects and applied aspects of the physics, like this quantum phenomena, mesoscopic physics, all these things on these various kinds of interesting materials. And also, we have a strong development program in this direction, parallel to it, as I have mentioned. And this is the future directions that fourth generation synchrotron and with high flux research reactor HFRR at Vizag, which is going to come soon. So there will be a nice extension and the new avenues for this condensed matter in this research direction, and of course development in this associated field of condensed matter. And I would like to acknowledge the contributions for these presentations from various divisions of our physics group BRC. And I would like to thank Director Physics Group and Director BRC for their kind guidance. Thank you very much.
Questions or comments? From anyone online? No. Okay. I just would like to make one comment. I mean, I see a lot of similarity and complementarity with the research that is also going on in SINP, at least so far, what was presented by you and by Professor Ghosh. Yeah. Dr. Yusuf and me have been discussing about a joint meeting. We did a similar kind of thing once before, together with a few other institutes. Okay, so this is high time that we do it again, and we'll listen to other institutes. I mean, we should try to find a time of convenience, and we'll do it again. Yeah. Okay.
Thank you for bringing this up, and I want to inform now. I thought of telling in the concluding session today that we have already planned. Dr. B.K. Nayak is here from HBNI, we have planned that this meeting will be followed by discipline-specific meetings between different units, and physics will be the first one in that. Very likely we'll have it in May, where we will invite physics specialists only from different units and then to share in much more detail. Now they have to be more general because of the audience. So in that kind of meeting, there can be more intense discussion on specific areas. This is planned, and I'm very glad for your suggestion.
Thank you. Okay. Thank you very much. I now request Dr. A.K. Bhattacharjee of BARC to come up to the stage, please. Yeah.
So good afternoon to all of you. Dr. Chidambaram here, and it is my fortune to talk in front of him. And my thanks to HBNI to actually organize such a workshop where we could all come together and share our thoughts. In fact, I've been sitting and then listening to the talks. Many things we don't understand, of course, but at the same time, it shows us what are the different ways to think about aspects. So I'm Anup Bhattacharjee. I will be talking about, I was looking after the engineering sciences in BRC, particularly related to electrical sciences, electrical discipline. And as you know that BRC engineering sciences are grouped into two parts. One is looking after electrical sciences, the other group is looking at mechanical sciences. So I'll be talking about the perspectives which are there in electrical sciences and what is the way to look forward. And this presentation is essentially a collection of matter which we have collected from various groups. The electronics and instrumentation group in BRC, as well as some aspects of engineering which happens in physics group, as well as in the MRG. So let me start with our pranam to our gurus who were there, who actually established this the electrical sciences domain in BRC. Let me say Mr. S.N. Sheshadri, who is, you can see in white shirt and pant, right, sitting on the, if you look at that image on the right hand side of the picture, the first picture on the top is considered to be one of the guru in BRC, who established in many ways that projects that we have executed. And I would also like to show our other guru, Mr. G. Govindarajan, who is, you can see his younger face, again on the top right picture, and standing there with his hands on the... so he is one of the person with whom I had interacted a lot. And then in the bottom picture, you can see, of course, Mr. Umesh Chandra, who was another guru, started the computer applications in control and instrumentation in nuclear power plants. And you can also see the respected Professor Chidambaram here, seeing and standing with Mr. Umesh Chandra. So my pranam to these gurus. And let me say that, the electrical sciences is essentially a very complex, discipline, looking after various aspects of control into, looking into applications into physics. And the main challenge is, how do you design such complex systems? In fact, you would see that on the left-hand side, the top picture that you see, Tiwari is there, who was instrumental in designing that, liquid zone control systems, which was a platform for validating various algorithms for the 500 megawatt PHWR. I mean, way back around the early, late 90s. Then the bottom part, you see also the simulators, which was, over a period of time, which was built in E&I group in BARC, and the nuclear reactor simulators, very complex, challenging technology. Then you can see on the top, you can see the isotope separation systems, which was done in by EMID. Mr. Malhotra is there in the Phys group. And you can also see various, control systems, like the middle picture shows some control systems which are indigenously designed. In fact, BARC, always the perspective is that various things that we do are completely indigenously designed, completely built, from scratch. Then you can see at the bottom, which is very interesting, is the GMRT, the Giant Meter Wave Radio Telescope, where the control system was built by, the E&I group, late 80s and early 90s. And you can also see a lot of other components which were done by various other groups here. So electrical sciences in BARC, if I look at, it is not a exhaustive collection. This is actually just showing a spectrum that we talk about nuclear reactor control, and what are the aspects that people have looked into is essentially design of control algorithms, sensors and electronics, process control and measurements, and of course, high integrity software. Similarly, in accelerator control, people have worked on magnetics and cavity design, beam diagnosis. Pulse power system, this is another area of the beam technology groups in BARC. Antenna control and imaging. Antenna control is one of the very strong delivery from BARC with respect to various antenna systems which are there even for ISRO. In fact, I would have loved to see Mr. Maya here, who was instrumental in designing various antenna control systems. The other important thing is about system security engineering. And system security engineering, we are talking about information security, cryptography, and also aspect of security by design. So if we look at these areas, and then if we look at what are the research verticals, which are essentially there in BARC, is in terms of theories and control systems for nuclear reactors, accelerators. I think there are stalwarts here who can talk about those. Nuclear instrumentation and signal processing, design and modeling techniques for high voltage pulse power systems, magnetic superconducting magnets, and RF design, where a lot of electrical engineers are working with physicists. High integrity software design and verification. Morning we had a talk from Professor Meena Mahajan, which was actually the mathematics part of this. How actually you have, what are the things that you can use there for verifying those software components. And of late, of course, cryptography was in some way that we have been interacting with ISI and IMSc with respect to cryptography. And Dr. Bala Subramanian was once upon a time a big collaborator also with us on cryptography. And recently, in the last couple of years, we have also started working on these trusted platforms. That means how do you actually ensure platforms which goes into C&I or on security systems, they are trusted? How do you assess their trust? There are a lot of theoretical work there, at the same time, the practical work. And of course, security systems, applying imaging for security systems. So these are some of the research areas which are there in the electrical science domain in BARC. And what I'm going to do is just show you some glimpse of work which has happened here. And then subsequently, I'll talk about, again, the research perspectives, which we should see probably in 10 years or 15 years down the line. So these are some kind of facilities which exist, supercomputing facility in computer division. We have a large number of embedded system design labs which are scattered over various, in fact, probably for the people who are from outside BARC, they would always get with these abbreviated names. So if I say RCD, it stands for Reactor Control Division. So like this ED stands for Electronics Division. So these are part of subgroups. So if you have any requirement of looking into or helping you into some very intense design, these are the groups which can actually help you. Reactor core kinetics modeling. In fact, RCD was one of the big contributor into this. Then facilities for intense electron beams. Then magnet design in EMID. and RF system design and testing labs in accelerator control divisions and also in the other divisions in E&IG. So I'll just now give a glimpse of what has actually happened in various domains here. So let me start with some development of theories, techniques, and facilities in reactor control, which was predominantly was in RC&D. And these people would have actually contributed in terms of developing algorithms, that how do you actually, the reactor core kinetics modeling, how do you implement them in software, building actually a simulator. You can see that I had shown you that simulator, building actually a simulator which is in the hardware. And a very important aspect is that once you build simulator, once you develop these simulator algorithms, actually you can put the hardware in loop testing. That means if I have designed a control system, I can actually put it into the, connecting with the simulator and putting the algorithms in the simulator and connecting to the field devices. And I actually look at their effectiveness of these algorithms and also the C&I systems, control and instrumentation systems. So this has remained a very big contribution from BARC, that how do you actually develop these simulators. Now, in terms of the current work which is there, which I can just tell that SPNDs, the SPNDs which are there for sensing the neutron population inside the reactor. So in terms of their fault detection and configuration, the kind of algorithms that they have used or developed based on Kalman filter based. And essentially there are a lot of challenges in terms of how do you actually model these SPNDs and how do you validate them. There are unknown model parameters because of the non-linearity, and also the very intense SNR variations in plant. So a good amount of contribution which has happened in terms of this work here, where actually there was an HBNI 1 PhD and 1 PhD is ongoing here. And in terms of sensor and actuator fault, because ultimately the control system is connected to, on one side there are sensors, other side there are actuators. How do you actually look at their faults? How do you manage these faults? So there is good amount of work which has happened here. In fact, I think there is right now an ongoing MTech project which is happening here. Now look at the signal processing and imaging for scientific and industrial applications. And this is remained as one of the very good contribution from E&IG in BRC. So again, algorithms for fault detection, instability detection in the flow instabilities in reactors, where if you look at the coolant channels, if you look at their the way that the coolant flow is there, what are the instabilities, and how do you analyze by using very advanced signal processing? How do you actually know that there is a flow instability going on? So this is one very important work which is happened and also happening in terms of a PhD thesis. A very interesting part was loose part monitoring system. In fact, we have started by looking at some of these modern reactors like Kudankulam reactor, where Russians have used loose part monitoring system to know that whether there is anything which is loose. And again, this work involves a good amount of signal processing, very advanced signal processing. The other thing that over a period of time where people have actually used signal processing was in terms of instrumented pipeline inspection gauge, where they have actually looked at oil pipelines and then looked into their defects into the pipeline in terms of, if there is a crack. And the importance is, or the academic contribution is that it requires a lot of nonlinear modeling, and signals are very, with low SNR. So you have this problem of how do you actually look at those signals and how do you actually analyze them. And of course, they are also working on some new projects which are with respect to combo IP with magnetic flux leakage and UT. There is another interesting aspect people are right now working on in control and instrumentation division is applications of signal processing systems in separation science. I think Dr. Mukhopadhyay is there from chemical engineering division. This work is in collaboration with them, that how do you actually detect onset of these agglomerations and measuring this or detecting this liquid-liquid interface. And again, it is actually a very involved signal processing job. And I think this is one of the good contribution that these people will make. Ultrasonic instruments, yes, there was one group in electronic division who are actually using ultrasonic instrument, developing ultrasonic instrumentation for inspection of reactor components. And they have a good collaboration with the FBR program in IGCAR to develop this instrument and also deliver them. And in this area, a good thing is that recently they have completed one PhD thesis in HBNI and the two are in progress. So you can see that the kind of the intense academic work going here. One important aspect is that BRC has developed, BRC has foray into developing instruments. And this is one thing that they have done is in developing a scanning electron microscope, indigenously completely designed in-house and can give up to 20 nanometer resolution. And there is right now one PhD thesis ongoing onto the design aspect of this and then going to the next step of field emission. There is another interesting work which is with respect to using imaging for analyzing component integrity test. Dr. Carr is here, who is actually collaborating with Reactor Safety Division to do this, use imaging to actually look at piping components and look at the way that this, components are going to go, have some cracks and then how these cracks actually, propagate. And measuring those cracks, looking at their propagation, this thing by using imaging. Very, interesting work. In terms of superconducting magnets, RF systems, which was also covered earlier here, I would just talk about some aspects of the engineering aspects. So EMID is involved in superconducting magnet design, and it's definitely a very multidisciplinary research field covering, electrical engineering, physics, and also mechanical engineering, because you need to also talk about thermal and structural design. And a lot of deliveries has happened here in terms of actually developing superconducting magnets. They have also worked with developing magnets, the liner cavities for LEHIPA, which is one of the very interesting work which has happened in DRC from EMID. The electromagnets for accelerator beamlines, which actually they have done and then delivered it to Fermilabs. One important thing about what I consider is important is that there are facilities to do this, magnetic measurements, which is there with EMID, and I think it would be nice if somebody can also utilize these facilities. They have facilities for magnetic measurement benches to qualify and characterize magnets. This is one good contribution was made from them is in terms of isotope separation, using lutetium separation. And I think it is a very interesting work because it actually involved a very intense design in terms of magnetics as well as this the total mechanical structure of the system. The accelerator control division has a lot of high power RF test facility, power test facility. They have a lot of good instruments, which in fact we have been also using them for doing a lot of RF measurements. And in terms of spectrum analyzers, signal generators, high-end oscilloscopes, group has very good capability. Also in terms of designing power amplifiers and looking at their linearity aspect of these power amplifiers. So these are some of the facilities which exist there in ACND. In fact, I should just go back. So I would just try to say that in this area, if I look at from the HBNI perspective, yes, they have produced 4 PhDs and 3 are in progress. Essentially, it's a very good thing. In fact, out of 4 PhDs, I would say that 3 PhDs are from HBNI, 1 PhD is from IIT Bombay. Then in terms of sensors, VLSI design for data acquisition systems, computing facility for nuclear applications, which are there in, of course, and I should have mentioned computer division also here. The electronic division and computer division have this program. So you have this fabulous VLSI R&D facility with electronic division in designing, ASICs, which is very important that they have this capability to design ASICs for high speed, low power multi-channel frontal electronics, multi-mode, multi-heat, octal time to digital converter ASICs. So this is some contribution which they have made in terms of which actually has gone into field. And very nice to see that actually in this spectrum, there are 7 PhDs. And I think out of these 7 PhDs, 3 are ongoing at this moment in HBNI. They also have this MEMS development in ED in looking at these MEMS pressure sensors, Raman detectors, and also strips, diamond detectors for fast neutron spectroscopy. Very good ability in Dr. Anita Topkar's group in electronic division has this computing facilities with in BRC with a very good computing facility, 1.35 petaflop speed with a very good architecture. And recently, actually, they have also installed one machine learning system with that means the hardware fabric they have actually installed, and then I think this is now probably could be used by people who are using or designing these algorithms and to run these algorithms onto these systems. Another interesting thing about BRC computing facility is that we have a private cloud system at this moment. That means actually we could use them for our storing our documents, and also you can fire your jobs on the cloud. So just to cover now, I mean, I've just given you a glimpse of what is the technology which is there, not exhaustive, definitely not exhaustive, just covered some aspect of this. Now, if I look at what we should look probably in 5 years or 10 years down the line. So I have been talking to people that what would you consider as some of the research areas? So definitely there is a lot of interest in building theories and techniques for reactor control, modern reactor control theories. And I mean, if you look at these, that how do you design a large nuclear reactor, and what are the kind of stochastic filtering techniques that you can use? And I'm sure that Dr. Tiwari is here. He is guiding a lot of PhD students on this area, and it would actually give rise to a good knowledge and actual deliverables which are coming out from this. And another interesting area that I have been talking to and understanding is that how do you design reactor simulator based on data-driven models when you don't have, the what do we say, that the mathematical models which are could not be built because you have some uncertainties there. And how do you actually build these models based on data? And how do you make them actually learn from your simulation streams and then understand that how this model could be refined? Another important area in terms of looking at when you design big systems, because ultimately when you look at a reactor control systems, accelerator control system, they are essentially very large, distributed. So what are the distributed control systems? I mean, the mechanisms that you should have, and what kind of signal processing that you would require to actually design them, and what kind of data-driven approach you could use to build those models. I think this is going to be a big research area. One important thing is that when you build such systems, definitely code, the software aspect of this needs to be at a very high level. That means, how do you actually design that I could write a specification for this system and I ultimately synthesize this code? And this is actually lead to a correctness by construction. That means I know the specification is correct, and so hence my code is correct, which will run on a nuclear reactor. So the verifiability aspect of this is very important because we are looking at safety critical systems. Now, when you design these connected systems, ultimately communication, that means that the high-speed data connectivity between these edge devices is very important. And I guess that today's this 5G or 6G technology, which is coming up now, I think we need to learn these technologies, and then how do you actually build systems? And this is going to be a big spectrum. And at the same time, I also must admit that communication system, we didn't do too much of actual research there. The way that you actually communicate over the air, and how do you build such systems which are also used in strategic sectors, defense sectors. If I look at, say, MANETs, mobile ad hoc networks. How do you build those protocols? This is going to be one very important area where I think BRC should spend time and then put people. AI for system optimization diagnostics, because we talked about connected systems where you have the edge devices collecting signals, communicating over communication systems, and then coming up to some nodal computer where you are going to process this. So this system optimization and diagnostics of the system where you could actually use AI models is, I think, going to be a very important area in terms of, I've seen in, if I look at Kudankulam reactor, I have seen, even though they have not used AI, but they have actually thought about this architecture where you collect data from various systems and then do an integrated analysis. They call it system integrated analysis. So I think this is going to be a big area where we should definitely put an academic program. That how do you use these technologies in doing for reactor system optimization, accelerator control, and also coming out with diagnostics. Computing, yes, that should be one big area where we talk about this exascale computing framework from petaflops to exaflops. Quantum computing system is definitely a very big research area, and I would like to see that we have PhDs produced from BRC. Definitely, I'm talking from BRC. Yes, I'm talking from BRC, that BRC actually should produce people who actually understand quantum algorithms, and we produce PhDs in quantum algorithms. Algorithms to process big graphs. We had in the morning nice talks about biological systems. How do you, probably if I look at even social networks, how do you actually process big graphs? And this is going to be very enabling computer science. It is already enabling computer science, and I think definitely a big research is required there. Game theory applications in security. This is one aspect which personally I feel that is very important. How do you apply game theory for these win-win situations for security systems? Today's security systems are built ad hoc. There is no analysis. So personally, I feel that we should also produce academic program where we look at game theory applications in security systems. Very important aspect is that we also must have a robust cyber physical system design in presence of AI. Morning we heard Professor Meena Mahajan talking about formal verification, specification verification. So the cyber physical systems is what she meant by saying the aspect of theoretical computer science, where we now talk about actual computing systems connected to physical devices. That's called a cyber physical system. Verifying these, using satisfiability, using SMT, SAT. What we discussed is, yes, we understood some aspect of this. We know still the scalability is a big problem. But today, now you see that you are coming out with cyber physical systems with AI. And how do you essentially assess their robustness? This is, I think, going to be a big area where we must spend our resources. System security, how do you essentially, trust a system? And I think this is where today's world, we must talk about how do you essentially look at the security of your hardware? How do you assess their security? How do you know that your network is, there is no man in the middle? And the other aspect is that the assessment of trust on software, and that is going to be very complex. And here, essentially, you require, the theoretical computer science, the programmers, and talking about various aspects and looking at how do you qualify or how do you specify trust and how do you model the system so that you can verify this trust. Very important when you talk about the security of hardware and also software, unclonability. That means I always this question that I have some hardware module which goes out for repair. How do I know that the same devices come out? So now, okay, we put some maybe some barcode and we put scanning device and then say, okay, it has come from there. But I think the hackers are much more intelligent than that. So unclonability of your hardware, what we call as physical unclonability function, how do you actually implement it into hardware to show that this hardware is not clonable? And I think this is going to be a big area where we also talk about immutability using blockchain. That means you use, like, if I look at, say, a reactor operation where operator is controlling a reactor, his actions are getting recorded, and we would like to see that this entire trace is immutable. And this is some place where you should see that whether we can use blockchains. Security for edge computing devices, because you have sensors, and recently there were cyber attacks which talks about control-aware attack, because the attackers, they know the control aspect of this, and they actually try to spoof, as if I have replaced this sensor. The sensor is a spoof sensor which is giving you data. So the security for edge computing devices is an area which we must look at. And definitely quantum resilient cryptography. Morning we heard Dr. Chidambaram talking about this. Very important that how do you look at the post-quantum cryptography? How do you harden them? Looking at lattice-based cryptography. This is something area that we should also spend. Superconducting magnets, of course, not my area, but this is something that what I understand is that material science studies of superconducting magnets from the engineering aspects is one of the area. Designing superconducting magnets for high energy accelerator and synchrotrons is another area where a lot of challenges are there. In fact, probably we would like to see that a lot of PhD thesis coming onto this area. Quantum computing, and with respect to design of superconducting resonator cavities, Josephson junction-based qubits, definitely, as I told that, we must now produce PhD which will be targeted for quantum computing. And this is not only with respect to looking at only at the the hardware aspect of this, the physics aspect of this, also looking at quantum algorithms. And I'm sure that quantum computers are not going to be that some computer where I connect a screen and I program. Ultimately, it is totally a problem-driven algorithm that you need to develop, where we need to actually look at that how do you actually design such algorithms. RF systems is how do you actually design superconductor resonators, RF solid-state power amplifiers optimized for use in accelerator applications, and linearization techniques of these high power amplifiers. In fact, I understand these linearization techniques of high power amplifiers is very important because we have seen that when you look at a power amplifier, looking at their linearization techniques, which is a lot of IPs are there, and even though it may be we may have to reinvent the wheel, but it is important because these IPs the other nations will never give us. And the moment I go into communication systems, this high power amplifiers is going to be very important. If I talk about this 5G, 6G, high power amplifier is going to be one of the area. Radio access networks where high power amplifiers are used. Instruments for science and engineering. And I mean, this is, I've been always thinking when we look at various instruments which are used for basic science, medical and security. If I look at, say, NMR instruments or MRI systems for medical, I always see that, these are always bought out. And why we can't, we have so many good engineers, why we can't develop instruments? And I mean, today, if I talk about this, that we talk about that if you have to buy an equipment, 20% indigenous. If I look at an oscilloscope, what is the meaning of 20%? There is nothing. It just comes from some Honeywell or, Roden Schwartz. So I think this is one area where we need to look at that. How do you actually design your instruments? And so that, in fact, the first picture that you had shown with Dr. Chidambaram, where it was showing this diffractometer. That is a time when E&IG was also developing some instruments. And field emission ACM, of course, ACM, some aspect that we have now mastered, but then I think we need to go to the next step by using field emission GAMS. Then digital image correlation systems for miniature component studies, which is now happening, but I think we need to take it to a big scale that how the safety engineers could actually work with us in terms of using these imaging techniques. Physical protection security systems, a lot of, anything that you buy comes from Israel or, comes from the US. Video analytics, behavior-based analysis, in terms of individual and crowd behavior. I think we need to actually put a good PhD thesis onto this, that people actually come out with these technologies. Virtual fence localization techniques. How do I know that at what far that intruder is there? So this kind of computational challenges from images is a very important aspect. Robust perimeter intrusion detection systems by using various scientific principles. That is where we need to work with scientists to actually design very interesting perimeter intrusion detection systems by using microwaves, by using fiber optics. Already some work is going on, but I think this is something that is a good enabler. So I would like to end my talk. I think I have not overstepped. I would like to end my talk by showing that our ENIG, I'm not talking of only ENIG, of course, but ENIG was very contributed in a big way in terms of always first of its kind. So if I look at that first picture, it shows the programmable digital comparator system, which was actually safety. What we talk about nuclear reactor, safety device, safety system. So this system was actually designed in our late 80s, early 90s, which was put into Kakrapa, the first computer-based system. And that's why I was showing all those pictures earlier, our gurus. If I look at this, the other picture, which is on the top right, is the reactor regulating system, which was used in Aurora, the first microprocessor-based reactor regulating system. The bottommost on the left side is first microprocessor-based load monitoring unit and first digital recording system for nuclear power plant. So if you look at this picture, this is something that in our early late 80s and 90s, early 90s, we have designed. So I'm just showing an evolution that we need to now, whatever the research wish list is there, that's the kind of evolution that you have to progress from what you have done, what we thought that a very interesting work, and how do we actually take it forward. So I think this is a very interesting and important aspect of this HBNI forum, that now there is a way that ultimately, if I look at a PhD thesis, what is a PhD thesis? It's a documentation of your own work in a way that it is reviewed, challenged by somebody, and then you defend it. So I mean, various things that probably in a year, last probably decades, it has been done. Many people would have got PhD if we had documented. And I think this was one thing that when I was sitting with Dr. Banerjee once, then he said that, that documenting your work is very important. And I think these are the students should learn. So I would end here. So thank you. And I'm thankful to all my people who had given me this input from ENIG, from Phys group, and also from Accelerator Control Division. And I actually interacted with a lot of younger people that this is a time. And then my wish started that, can I join again as an SOC? Because now I can actually work with again with my hand. So thank you very much. Thank you.
So the session is open for discussions.
Very good talk. You covered highlighting all the developments in electrical engineering sciences. And I'm very glad you mentioned about Seshadri. Seshadri, in a sense, kind of spirit of BARC. He was a model exhibiting the spirit. There's nothing BARC cannot do. That was, and there are many instances of that. Your talk on the security systems was very good. There's one area I think we should continue to both the cyber security and as well as the physical protection security, because the attackers are also getting smarter all the time. So you have to be one step ahead of them. And your mention about the supercomputing facilities, maybe it's worth mentioning that BRC is the only organization which has built indigenously supercomputer at the petaflop level as you showed. So again, very good talk. Thank you.
Is there any other comment or question? Anyone online? I mean, do you see anyone online? No. Okay, thank you. And I mean, this the last talk in the pre-lunch session.
Yes.
So I thank all the speakers in this session. And I think the main takeaway is what Dr. Chidambaram had stressed, and Dr. Bhattacharjee and Dr. Prasanna had reiterated that to know very well how much we don't know. I mean, that is the main thing. I mean, it reminds me that in cricket, I mean, the strength of a batsman is how well you know where your off stump is so that you can, in red ball cricket, you can leave the ball, dropping all egos. So here it is also very important to drop all our egos and to admit how much we are helpless in front of nature to, that we don't know how much we know to know how much we have to go beyond our present ability. Thank you very much.
This concludes session 2. I thank Professor Bhattacharjee and all the speakers for their presentation. We will now break for lunch, which has been arranged at the cafeteria adjoining this auditorium. I request you all to please assemble back at 2:30 for the post-lunch sessions. Thank you.
किसका पेन ड्राइव है ये भी मुझे पता नहीं है. Let them come then. Anyway, until IT people are there, it's part of this.
Welcome back, everyone. We now commence session 3, which will be chaired by Professor B. Venkatraman, the Director of Indira Gandhi Center for Atomic Research. I hand over the session to you now, sir.
Good afternoon to all of you. So we move on to session 3. At the outset, I think our Honorable VC had arranged an excellent meet, I should say. The morning sessions with the presidential address by Dr. Mohanty, the inaugural address by Professor Dr. Chidambaram, and all the other distinguished speakers who had given their insights into the various facilities and the research that is being carried on in various institutes was not only an eye-opener for me. I think you would agree when I say that this has been an eye-opener for many, where a need for the interactions among the units has also been felt, as has been pointed out by Director SINP, Dr. Bhattacharjee. And VC had been kind enough to indicate that we would be having focused interactions, probably starting from May, in the different physical sciences, biological and chemical sciences, etc., which would definitely foster a good amount of collaborations within the institutes where excellent facilities are available, and we need to share all these. So with this, let us go on to session 3, where we have 3 speakers. We have on life sciences, Dr. Harapriya Mahapatra, and in chemical sciences, Dr. Hassan, and in physical sciences, Dr. Samal. So we start with Harapriya Mahapatra.
Yeah. So at the outset, I thank HBNI for organizing this meeting, and it's a wonderful experience this morning, and we got to know each other. So I represent School of Biological Sciences, which is affiliated to the Board of Studies Life Sciences at HBNI. And I will be restricting my talk only to the School of Biological Sciences. Just for the audience, at NISER, we have 7 schools or departments. School of Biological Sciences is one of them, and we have chemical sciences, physical sciences, mathematical sciences, computer sciences, School of Earth and Planetary Sciences, and School of Humanities. So out of these 7, 4 basic sciences school will be covered in this meet, and my colleagues will be delivering talks on other subjects in the coming meeting. So in the School of Biological Sciences, I will take you through a brief introduction of the members, starting from the youngest members, giving an overview snapshot of the academic programs that we have, and introducing you to the faculties. Currently in the School of Biological Sciences, we are running 2 academic programs. One is the 5-year integrated MSc program, and the other one is the PhD program, which are both affiliated to HBNI. And just to give you an overview, we have around each batch 45 to 55 students majoring in biology or opting for biology as the majors and taking other subjects as which is compulsory for them as minors. So as of this date, we have a total strength of 240 cumulative strength, which have, including the graduating out batch, which just passed out in 2022, graduated out in 2022. 2021, sorry. So out of all the students who have graduated out, most of them pursue higher studies and PhD, either in India or in abroad, and they get very good placement in many institutes of repute in India as well as abroad. And few of them also opt for alternate careers in R&D industries, in drug discovery industries, and some also have gone into scientific writing. Now coming to the PhD program. So we have currently in our school 81 PhD students enrolled as of 2021 intake. And out of these, in the last year, so this in this histogram, you can see the breakup of the graduating number of students who have graduated out each year-wise, and the total cumulative strength and the intake capacities. So one of the hallmark feature of our PhD program is a very rigorous and thorough coursework, which is, of course, a mandate of HPNI and also UGC. So we take it very seriously. And during this coursework time, the students are also exposed to regular workshops, symposiums, and to train them, on contemporary research techniques. They are also exposed to hands-on workshops in handling small experimental animals, which forms a very important component of basic science research. And they are also provided platforms for developing or honing their presentation skills. And these platforms comes in the form of journal clubs, research seminars, and activities clubs. They also participate actively in organizing various conferences, seminars, workshops, which gives them managerial ability or ability to handle technical sessions and those skills. Definitely with this kind of a training, they also get welcoming gates in various other institutes in India as well as abroad for pursuing higher studies and postdoctoral studies, some of which are listed over here, and I will not go into the details of it. Now coming to my colleagues and faculty members in the school, we are currently having a strength of 18 faculty members. And this slide gives you a single snapshot of all the 18 faculty members currently that we are. I will briefly spend a few minutes telling about the area of research that each of them does. So we have with us Dr. Abdul Rahman, and his area of research is on mechanism of nuclear expansion and membrane remodeling. Followed by Abdul Rahman, it's listed over here, is Dr. Ashima Bhattacharjee, and she works on gastric cancer. Now, most of us, we carry out a fundamental research or fundamental basic research, what we call as. And we have Dr. Chandan Goswami, who is investigating TRP ion channels and its role in pathophysiology. We have Dr. Debashmita Alone, and her area of work is genetics of aging disorders. She deals with eye disorders, Fuchs endothelial dystrophy, and glaucoma research. And myself, I deal with antibiotic resistance, virulence, and persistence in gram-negative organisms. We have Dr. Kishore Panigrahi, and he's the only person currently at NISER who is working on various aspects of plant biology and plant developmental biology. His work involves flowering time control, effect of different abiotic and biotic stress on flowering and rootings. And recently, he is also expanding his research to his model system was Arabidopsis, and now he is expanding to mung beans and other psychometrilla that I'll show to you in a couple of more minutes. We have Dr. Manjusha Dikshit. So Dr. Manjusha, she deals with angiogenesis regulation and cancer genetics. So her work basically focuses on development of blood vessels in tumors, and she uses cell lines and some patient samples, which is accessible as and when to investigate different aspects of angiogenesis. My colleague, Dr. Palo Kaich, he works on systems biology, microbiome, and omics. So metabolomics, all aspects of omics. So his work is on gut microbiome. And the larger question that he is looking at is, how do we use a gut microbiome technique or therapy to reduce certain diseases like inflammatory bowel disease and things like that, and how gut microbiome is perturbed during stress and physiological disorders. Then another colleague of mine, Dr. Pankaj Alone, he deals with the basic molecular biology, and he investigates the translational fidelity and genetic code and role of ribosomes in maintaining this translational fidelity. So his work focuses on suppression of initiation phenotype or SUI phenotype, which in a given scenario, in a SUI phenotype system, the AUG, the start codon, is skipped and an alternative start codon is selected for going further. I have my colleague, Dr. Praful Singru. He works on chemical neuroanatomy and neuropharmacology. So his work is basically studying the brain circuits or the circuitry elements and the distribution of the endocrine and signaling molecules in tissue sections of the brains. And this, of course, he does using mice and other zebrafinch as the model system. I will come to that in a short while from now. We have our Dr. Rudresh Acharya, who specializes in structural biology, and he is also deeply involved in studying the de novo protein, designing de novo proteins, and studying the structure function relationships of protein enzyme function at different conditions. One of his paper got recently accepted in JBC. And we have Dr. Ranjit Matthews. Now, his area of research deals with mechanisms of cell and tissue morphogenesis as well as degeneration, tissue degeneration in aging population. So he uses Drosophila as his model system. We have with us Dr. Ramanujan Srinivasan, whom many of them in the audience would know. Debasis knows him well. So Dr. Srinivasan Ramanujan, his area of work is in prokaryotic cytoskeleton, how the bacterial cell divides, how the plasmids are maintained in the bacterial cell. So these are some of the questions that he is interested in studying. We have Dr. Subhashish Chattopadhyay. Now, Dr. Subhashish is an immunologist, basically by training, and his research interest is on seeing how the immune system is perturbed in response to a cancer development and viral infections. We have a structural virologist colleague of mine, Dr. Tirumala Chaudhary, and he is interested and he's investigating how the viruses enter the human cells or the animal cells, if I put it. So he uses a pseudovirion system expressing the viral envelope proteins, and then using both biochemical and insect cell lines, he studies how that entry process happens. We have with us Dr. K.V. Badrinath, and Dr. Badrinath is basically he has a pharmaceutical background, and he delves into drug development, improving drug delivery, and pharmaceutical nanotechnology. Recently, two of their colleagues joined in 2019, Dr. Mohammad Salim and Dr. Aniruddha Dattarai. So Dr. Mohammad Salim's interest is in membrane biochemistry and biophysics. He looks into how the membrane bends in response to particular vesicles coming out of it, and how that affects the host pathogen interaction and the disease progression. So he uses Mycobacterium tuberculosis, or that is his model system. Of course, he does not handle Mycobacterium, but he uses those proteins to study. And last but not the least, the youngest member of our school, Dr. Aniruddha Dattarai. His area is very different from what we have been hearing since morning. He deals with biogeography, systematics, and biodiversity. So he studies lineages and dispersion of different, species of fauna in different parts of Indian subcontinents, and also traces their origin, how it has originated during the continental drift and other aspects. This he uses the molecular markers and signature markers to see this phylogenetic dispersion. So this is the 18 of us, and we have three very dynamic technical staff with us. Dr. Shyamashri Basu, who is Scientific Officer, F, Dr. Saurav Chawla, who is a scientific officer E, and he's a veterinarian by training, so he is completely in charge of the animal house, and Dr. Chandramohan Bhattacharjee, who looks after all the instrumentation, day-to-day maintenance, and coordinates with various aspects for smooth functioning of the department. So this is a very small snapshot of our entire strength or the diverse areas of research that we have. Now, going further, if I broadly try to classify all these areas, so it kind of radiates out from the basic research, and it involves cancer biology, cellular biology, age-related tissue generation, which again can be a subset of cellular biology, basic molecular biology such as protein translation, bacteriology, cytokinesis, antibiotic resistance, virulence, aging disorders or non-infectious disease such as aging disorders, immunology, neurobiology, microbiome, drug designing, and structural biology and membrane biophysics. Also, we have, as I mentioned, a very unique area, biogeography, systematics, and biodiversity. With all this, so we can very well see that ours is a very diverse area, and we work on various different aspects of biological sciences. And of course, to achieve this, we need to have robust model systems. So most of our work involves bacterial cells, yeast cells, cell culture systems, animal cells, human cell lines, insect cell lines, and plant systems. Arabidopsis thaliana is one of the well-established plant systems. We have a good Drosophila facility, which is a fly facility for studying various aspects in, like I mentioned, age-related disorders and all those things. And we have mouse also in a model system that's because of the DAE funds to set up the animal house facility, which I will be talking up next when I deal with the facilities. And using these systems, we study various aspects of life sciences, as has been listed over here. Now, with this background, we have been doing well and performing well, and this graph or a histogram is a snapshot view of our publication statistics exclusively from the School of Biological Sciences that has come out as of now, and the source is PubMed. So as of 2021, we have around 100 or so odd publications coming out, and we are progressing further, and we would like to establish ourselves as a vibrant and prominent research group in the country. Now, I will take you through select recent publications that has come out from the school just to impress upon you the quality of the publications that comes out. As you can see, highlighted over here are journals which are of high repute, such as eLife, ACS Omega, Journal of Cell Biology, Cell Death and Diseases, Journal of Biological Chemistry, the EMBO Journal, Journal of Virology, Journal of Human Genetics, Experimental Eye Research, Frontiers in Cellular Infectious Microbiology, Frontiers in Immunology, Nature Communications, Plant Cell Reports. So as you can see, we being very relatively young in the hierarchy of HBNI, we are still striving our best, and we are moving forward in the direction to make a mark for ourselves in the national as well as the international fields. Now, apart from these publications, contributions of our faculties has also made them being recognized by peers in India as well as abroad. So in this slide, as you can see, one of my colleagues, Dr. Chandan Goswami, he got nominated as the DAD Research Ambassador from 2018 to 2022. That was the tenure. And Dr. Kishore Panigrai, he was nominated as the coordinator for student and staff mobility by the European Union under the Erasmus K107 program and the DAD student exchange program. My colleague, Dr. Palok Aich, received the badge of honor from from Bulgaria's Public Health Sofia Medical Academy of Bulgaria in 2018. And my youngest colleague, Dr. Aniruddha Dattarai, has made himself immortal by a species of skink. So these are smaller relatives of monitor lizard that we know. So this species of skinks, Eutrophis dattaroyi, has been named after Dr. Aniruddha Dattarai, and this was discovered from Nicobar Islands. And this is to commemorate his contributions in study of skinks from the Indian subcontinent. And for looking into his contributions to the various aspects of study on skinks, he has been nominated as the regional coordinator for South Asia by International Union for Conservation of Nature and Natural Resources. And last but not the least, my colleague, Dr. Salim Mehmet, he received the Wellcome Trust DBT Intermediate Fellowship for the year 2021. So all this work would not have been possible without a robust or without at least a sufficient infrastructure support and instrumental support, for which again, I would humbly acknowledge the help from in the form of financial support from DAE and my administration at NISER for facilitating us to establish this. So we have, among the major facility, we have this animal house facility, and with all hiccups, we were able to complete this facility in December 2021. However, prior to that, we were still functioning and we needed things to go on. So we had developed a temporary animal house facility in one of the existing biological building floors. And there we had set up our animal house, the entire setup of the animal house. And we had over there all the cages, the cage changing stations, as you can see, the non-ventilated cages to maintain the animals. And we also had ventilated cages to segregate the infectious animals. And we also have an anesthesia setup and a hood also attached to the hood so that we can perform the dissection and functions. For tissue histology and sample seeing the anatomy, we had a rotary microtome, we have it. And all these facilities, as I mentioned in my previous slide on when I was discussing about the PhD program, every semester we try to give a hands-on training on handling this animal and small animals to our PhD students. So this is one of the training sessions going on over there. Now coming to the other facility which I mentioned, it is the greenhouse facility. So this is the overview of the greenhouse that we have at NISER. And inside this building, we have this kind of a chambers which are called as a walk-in plant growth chambers. There are 4 to 5 of such walk-in plant growth chambers, each being maintained as specific temperature. The purpose of it is to see the effect of temperature on flowering. And of course, when you talk about flowering, that leads to fruiting also. So how it affects the flowering and fruiting in plants, again, taking Arabidopsis as the model system. Now, some of the proteins cannot be expressed in Arabidopsis very well. So the other model system, which is shown over here, is the Psychometrilla, that is a bryophyte, a small moss-like plant, and that is used for expressing any human immunoglobulin protein or anything in a higher quantity in plants. So this is the kind of the facility we have at the greenhouse. And then I move on to the next major facility which supports, rest all of us. So we have the central instrumentation facility which houses confocal microscope. We also have a single crystal X-ray diffractometer. We have a Sanger sequencer. We have microthermophoresis apparatus for measuring protein-protein interactions. We have LSR Fortesa model of a fax machine. This can detect four lasers at a time, but it cannot sort out the cells. So this is the limitation of this machine. We have steady state fluorimeter to change the fluorescence activity in a given live system over a period of time. And of course, we have the Quanta Studio 7, which is a real-time PCR machine. This can be operated either in a 96-well format or a 384-well format. Now, this was just a basic snapshot of what are the major equipments that are there in the CIF. But apart from that, we have in our building walk-in cold rooms. We also have sufficient cryo storage facilities. We have tissue culture rooms, animal tissue culture rooms, cell culture rooms, and radioactive facility, as well as the fly facility. So this is what, within the constrained times and keeping the broader nature of this meeting, I have prepared. So that's all from my side. Thank you for your patience hearing. Any questions? I'm ready to take it.
That was an excellent snapshot of your department. So we have some time for questions. So let me start. In the last slide, you indicated about the central instrument facility. What is this radioactive facility you are mentioning about?
So radioactive facility is a, that room has been constructed in a way so that we can handle P32 isotopes for labeling our proteins, for nucleotide labeling, P32 and S35 also. So mostly for wet lab studies. So they have very small half-life of 15 days or 20 days. So, but they have to be contained in an environment till that happens. So this is the facility that we have.
Any questions? Okay, one more. In the list of publications, there was one by Dr. Alone, I think, on eye diseases.
Yes.
Experimental eye research.
Yes.
So what exactly is the nature of this particular work?
So as I mentioned, Dr. Debashmita P. Alone, she works on genetic disorders and endothelial FUX genetic disorder, and the other one is this corneal dystrophy. So these are two prevalent eye diseases which mostly happen in the aging populations, and that is what she has collaboration with eye institutes in Bhubaneswar, LB Prasad Eye Institute, as well as there is another private Bandyopadhyay hospital. So they have published this, and pardon me because I do not have not updated myself with exact content. I do not recollect it now. So that is the communication that has come up in this specific experimental eye research journal, because it is in that field only. Yeah.
I just have a query. It's not very technical, but maybe Dr. Venkataraman also can add to my query. We have large hospitals in DI, start from BARC hospital at Kalpakam and several places. These hospitals, in a way, also serve as excellent data systems for people who want to do research on epidemiology or prevalence of various types of diseases, their relationship with age or environment, whatever it is. So I think there is a scope for that kind of collaboration between NISER and other people, because you can get a lot of information about actual patients from those places.
Definitely.
So that is why I just wanted to suggest that.
Yeah, definitely. Well taken, sir. Just to mention, I told you about
because the doctors in those hospitals, at least I know about Kalpakam, I think similar thing is true of, they are too busy actually attending to patients only. But at the same time, they are generating so much of data. That data will be valuable to us if we see what kind of information can come out of that.
Definitely, we will take it up. As I mentioned, she currently is associating single nucleotide polymorphisms to the onset and progress of the disease. So that is the current work of Dr. Alone that is ongoing. And definitely later on, whenever she wills, we would definitely consider this and progress further for epidemiology.
No, I was not mentioning only about her. I'm mentioning in general.
In a broader perspective.
It can be regarding eye, it can be regarding prevalence of various types of genetic disorders, various types of chromosomes, whatever. I'm not a specialist, but I can know that large amount of data is lying to be analyzed and used. That's what I'm trying to say.
Definitely, that would definitely serve our purpose. Yeah.
Any other questions? Yeah, one question on WebEx.
Yes.
From the WebEx. Yeah. So somebody from online has.
Okay.
So we'll hear the question.
Yeah.
Yeah. Okay, I want to
Did
ask,
you study
related to this,
COVID?
Yes, 19 virus and their possible mutations.
Okay.
You have a QS7 RT-PCR also with you.
Yes. So as you would know that for handling COVID virus, the ICMR guidelines did not permit inactive virus during the first and the second phase. It's only after the second phase that they allowed inactive viruses to be handled. Now, one constraint that we had in our setup, in our infrastructure thing, we did not have a stand-alone BSL-2 facility. So that is why we could not do it ourselves. But yes, we had lent out, we had rented it. I mean, not, sorry, rent is not the word. We had let it out to RMRC, Regional Medical Research Center at Bhubaneswar. They had taken our machines and they did do the RT-PCR in the first as well as in the second phase. So that we supported it indirectly, and we also provided them, because they were lacking the cold storage system, deep freezers, -80 deep freezers. So we also shared a deep freezer with them so that they can keep the samples as well as the testing kits that come. So that way, indirectly, we supported the government's initiative, but per se, ourselves, we are not able to handle because of these limitations.
Thank you. Yeah. I think that was an excellent overview. Let us thank Dr. Harapriya Mahapatra for the excellent overview.
Thank you.
Thank you very much, Doctor. So we move on to the next speaker, Dr. Hassan from BARC, who will be talking about chemical sciences.
Okay, thank you very much. Very good afternoon to one and all. At the outset, I would like to compliment the entire HBNI team for creating such a wonderful platform to share the activities at various CIs in a common platform. And I am thankful to the organizers for giving us an opportunity to share some of the R&D activities that is being carried out in chemistry group, BRC. So I would like to acknowledge the contributions from the various heads of divisions in chemistry group and the director chemistry group for giving the guidance and overall compilation of this work. So what I'm going to talk to you here is about some of the fundamental research in diverse areas under the themes as disclosed here, especially related to materials for nuclear applications, then reactor water chemistry, hydrogen technologies, healthcare materials, various functional materials, then environmental and separation science, chemistry with lasers and accelerators, biofouling studies, analytical services, and computational chemistry. So these are some of the major thematic areas in which chemistry group in BRC has made significant contribution during the last couple of decades. To go into detail, I will just highlight some of the activities. So one of the activity in the area of nuclear material that has been taken up recently is to develop various sacrificial core catcher materials to deal with the problem of under unlikely accident conditions, to deal with the containment of the molten corium. So in that respect, we are in touch with the collaboration with the NALCO. We have been studying the fundamental basic studies related to the interaction of various typical corium component constituents of the corium, such as the thorium oxide or uranium oxide or other fuel materials with the, as well as the matrix material, as well, the core catcher material, basically this Fe2O3 and Al2O3 component and their other silicate material, to understand their interaction using X-rays and other high temperature studies. This processed red mud from NALCO has been used as a potential core catcher material after proper conditioning to fix this complex molten mixture. Another area in which we have been working on is to develop appropriate alloy matrices for immobilization of the zirconium-based metallic nuclear waste, that is the hull, metallic hull, which contains various loosely bound contaminants, so it can be fixed in various, obviously, looking at various metallic alloys like a stainless steel zircaloy system and iron zircaloy binary alloy system, looking at the microstructure and their stability in order to accommodate such type of metallic matrices. Again, we have been working in the development of alpha particle detectors in highly corrosive environment. Naturally, by virtue of the robust properties of the diamond as a material that can withstand highly corrosive environment, efforts have been made to develop in-house these diamond-based thin films and then fabricate appropriate electronics to detect alpha particles in highly corrosive in situ monitoring of alpha activity in a highly corrosive environment like nitric acid. Of course, there are efforts to develop synthetic material, inorganic ion exchangers, which has been predicted to have very high radiation and thermal stability. So in this respect, I would like to point out one layered material, that is the manganese oxide hydrated layered material with a lot of sodium and potassium. So I will say sodium potassium brennesite. So intercalated inside this layered structure. And these sodium potassium ions can be easily exchanged with strontium or cesium, and there is a selective separation of the strontium from yttrium. It has been observed by using this material. So such inorganic ion exchangers, development of inorganic ion exchangers are also under development. Then alternative matrices for immobilization of nuclear waste in addition to the glass matrix. So these such ceramic matrices which can mimic the synthetic rock, which is called syn rock, a composition of various perovskite and zirconolite, rutile, etc. This composition. So the variation in this composition, how it can affect the stability of the material that is formed in terms of their ability to incorporate various fission products as well as minor actinides or surrogate material for actinides has been investigated to incorporate in such type of synthetic rock mineral. Also, recently we have been working on understanding the thermophysical properties of various material for MSBR, that is the molten salt breeder reactor application, especially the fuel salt and the coolant salts. They are basically fluorides or eutectic fluoride mixtures. So many thermodynamic and thermophysical properties of this material needs to be investigated over a wide range. The enthalpy of fusion, heat capacity, viscosity, all those things plays a major role in designing these reactors for their application. So in this respect, the thermal conductivity, viscosity, heat capacity, then the phase diagram of these fluorides, eutectic composition, all these experiments are underway. Again, the corrosion studies for MSBR application, again, is an important aspect. So the corrosion behavior of inconel, hestalloy, this type of alloys under different fluoride medium has been investigated by using the Tafel plots as well as the impedance spectroscopy. One can get the corrosion rate information, the accelerated corrosion, as well as by using appropriate electrochemical equivalent circuit models to fit the impedance data. One can get information regarding the coating or the passive layer that can be formed in the surface of this alloy material. This will have major implications in understanding the corrosion behavior of these alloy materials for molten salt application. Again, catalyst development for nuclear application is one of the application is for decomposition of dioxin and furan. As you all know, even minor quantities of dioxin and furan. Today morning we heard from the IOP the development of plasma-based incinerators to tackle the problem of minor dioxin and furan in the off gases emanating from the incinerator. So we have been working on developing appropriate catalysts that can decompose the dioxin and furan at appropriate temperature or in the plasma temperature, so that there is no concentration of dioxin and furan that is emanating into the atmosphere from the incinerator. So various catalysts have been developed and optimized to understand such type of decomposition behavior, and once such material is these mixed oxides of vanadium and tungsten on TiO2 substrate, which can degrade a material orthodichlorobenzene, which is used as a surrogate material to understand this corrosion behavior. Again, we do have a very good ultra high purity laboratory which can process various material as per demand, and a good number of metals or ultra purified metals have been developed and delivered. And some of them, that is, I just show you a couple of photographs where high purity arsenic, antimony, and again the gallium arsenide crystal that is developed by using the arsenic and antimony high purity that is delivered from chemistry group, that is BARC. And currently we are looking at developing 12N purity germanium from commercial germanium metal. Again, supported noble metal catalyst for a passive catalytic recombiner device, which has been developed. The basic R&D has been carried out in chemistry division, and to develop a platinum and palladium based supported catalyst, which can, under accidental condition or in case of where the hydrogen concentration exceeds certain limit, it can be passively converted and the hydrogen concentration can be decreased to a level that is safe enough to handle. So this technology has been handed over to ECIL, and more than 1,100 such prototype device has been fabricated and is deployed in various power plants. And efforts are underway to develop advanced material for other reactors in the future, forthcoming reactors as well. Then in the area of reactor water chemistry, these chemical decontamination technologies. So as you all know, for different reactor components, for example, one recent development is the use of ozone in addition to the well-known manganese permanganate oxidation process. So the use of ozone in accelerating the chemical decontamination process in chromium containing alloys. Of course, we are also working under the water and steam chemistry division, the corrosion issues due to partial boiling in 700 megawatt electric PHWR. So a high temperature, high pressure loop is already set up. That is operational in WSCD Kalpakkam, where experiments are being carried out to understand the corrosion behavior of various materials under this partial boiling conditions. Also, research have been done to control the corrosion by using various surface passivating agents, such as organic molecules like octadecylamine. Their ability to control the corrosion in carbon steel or incolloy has been established through various experiments. Then in the area of hydrogen technology, we have a robust program on both generation and storage of hydrogen. So one of the areas in which the BRC has been putting its effort is thermochemical hydrogen generation by the iodine sulfur cycle as well as the hybrid sulfur cycle, and which requires a very high temperature of the order of something like 800 degrees Celsius for sulfuric acid decomposition, as well as for hydrogen iodide, HA decomposition, something of the order of 450 degrees Celsius. So a large number of catalysts have been tried for effectively reducing the temperature as well as converting the decomposition of sulfuric acid. And this has been taken in collaboration with the chemical technology division. Another area is by photochemical, that is photocatalytic hydrogen production, in which a large number of catalysts have been developed, and one notable catalyst that has shown promise in recent years is the graphite carbon nitrate, as well as doped or substituted graphite carbon nitrate, with its ability to produce hydrogen under photochemical photocatalytic conditions. Of course, we are also have developed a supramolecular strategy to release hydrogen. You know, this ammonia borane is a good material which can be used as a hydrogen storage material, which can actually take up hydrogen and then it can be released. So the nano cavities formed by cucurbitural type of supramolecular assemblies has demonstrated the ability in a catalytic manner to release the hydrogen under appropriate conditions so that it can be used as a appropriate molecule for storing and release of hydrogen for potential applications. Again, as you all know, these titanium-based alloys, by virtue of their ability to form hydrates, this has been studied in, as a very good material with a very high absorption capacity for hydrogen. So a good amount of titanium, chromium, vanadium-based alloys have been prepared, and their absorption and the absorption profile at appropriate temperature has been investigated to demonstrate its capability to use it as a material for hydrogen storage. The area of healthcare material, a large number of material has been prepared. So a couple of them I would like to highlight. One of them is the iron oxide nanoparticle, Phy3O4, which has got the super paramagnetic behavior at a very small size, and which can use it as a alternative therapy by using hyperthermia, that is by applying AC magnetic field, one can generate heat and locally, and hence it can be used for a therapeutic purpose. And protein stealth can be the human serum albumin, or a protein is a very good biocompatible material which can be, which is already present in our blood. So this protein stealth around the particle can act as a stabilizing mechanism to make it a biocompatible material. Again, hydroxyapatite is a component of bond which can be used as in a nanoparticulate form with appropriate surface functionalization using folic acid as a receptor to specifically target to cancer cells. And this also has been demonstrated by various molecules. Another important development which we have observed recently out of our curiosity-driven research is the develop a nanocarrier that can deliver gene and interfering RNA. I would like to mention that the process of preparing these liposomes are different from the conventional process. And this is by we use the supercooled micelles, which is normally the micelles and such colloidal systems or self-assembled system exists in liquids. So our attempt to develop a solid matrix that can trap micelles in a solid phase led to the development of a new process to prepare surface charged liposome. And this is the X-ray scattering data, which clearly shows that the scattering can be simulated with a core shell model. And we can even get, by using analyzing the X-ray scattering pattern, the core and shell dimensions, as well as the electron density of the core and shell, and which will again corroborate the microstructure that is present in combination with other complementary tools like electron microscopy. Again, we have a very good spectroscopic tool, the vibrational sum frequency generation tools that can probe the molecules at the interface very judiciously at a very low concentration. And this technique has been judiciously used for probing the interaction of various molecules at the interface. Say, for example, you can think it of as a mimicking system for lipid bilayers on the surface, how the drug molecules can interact with the bilayers. This type of information, fundamental information, can be generated by studying the vibrational sum frequency generation or the higher spectroscopy by using the VSFG technique. This method is available in our laboratory in chemistry group. Again, there has been a lot of effort in developing new drugs. So one such in-house developed molecule is the diseleno-dipropionic acid, 3,3' diseleno-dipropionic acid, which is abbreviated as DSEPA. So this molecule has got excellent radio protection as well as the ability to prevent pneumonitis, a side effect of radiation in lung cancer treatment. And as a next step, we have investigated the deuteration of effect of deuteration. You know the isotope effect. From substituting hydrogen with the deuterium will have a tremendous effect in the dissociation of the bonds and metabolism of the drug molecule. So here we have investigated the effect of deuteration, and the first time a deuterated diselenopropionic acid has been synthesized and their effect has been demonstrated. A superior performance or therapeutic index of this molecule has been demonstrated in vitro models. We are also looking at developing sensors for cancer detection. This is one sensor which has been developed in our laboratory that can effectively differentiate between the normal tissue and the cancer tissue in real tissue specimen from biopsy specimen. This has been tested. Basically, it work on the principle of using an appropriate matrix, conducting matrix that can probe the changes because of the changes in the chemical environment, in the extracellular environment in the tissue that is present in normal and the cancerous tissue by way of the changes in the metabolism in these two cells. Again, plasmon-assisted colorimetric sensors based on Raman as well as optical detection has been used by developing various surface plasmon sensitive inert nanoparticles like silver or gold nanoparticle capped with appropriate reagent that can specifically bind with the pesticides or any other ions that is present in the medium, and hence it can alter the surface dielectric constant or the Raman scattering intensity because of the interaction of these molecules. So this can be used as a probe to identify the sensors for development of this type of material. Again, fibrillation is an important phenomenon that is associated with neurodegenerative diseases such as Alzheimer's disease. So there have been effort to understand such fibrillation process or preventing the fibrillation or disintegration of the fibril that could pave way for developing new generation drugs for preventing or early treatment of amyloid associated diseases such as Alzheimer's disease. A large number of work has been carried out in this direction to understanding the defibrillation process. Again, various smart energy system, especially the bright blue light emitting electroluminescent display materials have been prepared. This gallium or germanium doped zinc halide is one such material which can give you a very narrow emission electroluminescent behavior under appropriate conditions. This is again a new research. Again, for a battery application in the area of functional material, a large number of materials have been investigated for its potential application of as cathode materials or anode materials in the area of both the lithium as well as sodium ion batteries. Today morning we had some other research by using neutron scattering, how you can investigate the lithiation process or the sodium intercalation. So here again various layered materials have been prepared that has got the ability to incorporate these metal ions under electrochemical conditions. Again, in the area of sensors, a good number of sensors, thin film sensors based on palladium oxide or even tin oxide, and again other composite materials have been developed to detect their changes in the conductivity upon absorption of various oxidizing or reducing gases, which could lead to novel sensors that can work at ambient conditions. So this is the objective here is to monitor at room temperature this type of different gases such as hydrogen sulfide or hydrogen, even other H2S, SO2 and NO2 like that. Again, photoanodes for photoelectrochemical water splitting, another area of research. A large number of composite material, bismuth 188 based anodes have been developed which show promising photoelectrochemical water splitting, which can be used for hydrogen production application. Again, nanocomposite material for sensing and environmental application. Composite material for chromium sensing have been developed by making use of nickel sulfide and reduced graphene oxide, which shows a very good sensor response for actually chromium by means of pre-concentration and stripping and further electrochemical detection. Again, we have a good group working on gaseous reaction kinetics, especially to understand the fate of atmospheric pollutants. So in this respect, I would like to mention that the kinetics in gas phase of various volatile organic compounds, experimental facility has been set up and estimated their rate constant at different conditions to understand the decomposition of these various volatile organic compounds in the troposphere, which will have implications in understanding the global warming potential of these molecules and their relevance to the environmental pollution. Again, photochemistry has been done by using lasers and different laser system, femtosecond and picosecond techniques. Singlet fission dynamics in various aggregates have been investigated, or I will say the organic molecules have been investigated, the effect of substituents on various organic molecules, which can be used as a component in the solar organic photovoltaic application. So this is very important. The singlet fission dynamics is very important to enhance the efficiency of a photovoltaic material. So this has been studied in detail. Again, our group has developed a two-dimensional IR spectroscopy when for the first time when it was not available in the market. The technology has been developed in the laboratory. Yeah, 5 minutes, right? In the laboratory. So it has been used for estimating various parameters, like you can get the two-dimensional IR spectra can be used to elucidating the bond-specific dynamics of materials at a different length scale. For example, in this case, it has been used for understanding the phenomena. Again, aggregation of various protein aggregates for DNA detection, their limitations or complications that can arise when you use conventional methodology for understanding the nuclear staining of or DNA staining by using DAPI. Again, single molecule spectroscopy to understand by using the fluorescence property of molecules in a single molecule level, one can study the binding of various molecules even at a very low concentration, binding of actinides to various ligands, many other phenomena like the dipole imaging, super resolution microscopy. All those things can be carried out to get fundamental insight into molecular processes. Again, interaction of intense laser pulses with the clusters. This has been demonstrated. The formation of multiply charged ions in clusters have been demonstrated for the first time. The area of analytical chemistry, we have the program on development of various certified reference material, which is very much essential for calibration as well as for validation of the results generated in various analytical laboratories. A good number of analytical standard reference material have been developed and released. One of them is the quartz CRM, in bauxite CRM. They are all developed and released. And NCCM also has a state-of-the-art surface characterization facility by ion beam analysis, which can be used for getting information, compositional information, depth profile, and all other information by using various techniques like Rutherford backscattering, then PIXI, etc. Then biofilm control, another area of research, various organic molecules, ionic liquid, their ability to control the biofilm growth, which has got important implications in corrosion point of view on various material like stainless steel has been developed. As an offshoot, we have also developed a bacteria-laden granules for treatment of wastewater, and this technology has been patented and transferred to more than 9 companies, and its various capacity water treatment plants have been installed based on these bacteria-laden granules for their separation purpose. We also have some of the computational facilities for chemistry research. Many of our activities, experimental research is being supplemented by the computational studies by the group of computational chemists in our laboratory. So some of the recent results I would like to show that the prediction of the trapping of the radioactive krypton or xenon gases in MOF type of materials. Then variation in the thermal conductivity of fuel matrices like a UO2, incorporation of the fission product. How does it affect the thermal conductivity or the thermal expansion coefficient? These are all relevant for material property evaluation. Again, designing suitable ligands for separation of various materials such as zirconium and hafnium, separation by judiciously choosing the donor groups in the ligands. This also has been developed. So in a nutshell, I would like to say that chemistry group in BRC has a program on various fundamental aspects relevant to materials for our processes for energy, environment, and healthcare. Finally, I would like to acknowledge the colleagues, heads of divisions and director chemistry group who have helped me to consolidate this work in this fashion. Thank you very much, and I will be happy if you have any to answer your queries.
Thank you very much, Dr. Hassan, for an excellent overview on the gamut of applied and directed research and chemistry group. Any questions? Okay, let me start. You indicated about the sacrificial materials.
Yep.
So the sacrificial core catcher materials. So this you are targeting it for which type of reactor systems? Light water, pressurized heavy water?
Yeah, it is actually for the futuristic reactors where you are actually planning to do HWR and other type of reactors. So in the existing reactor, this technology they may not be implementing at this stage. In futuristic reactor, it is proposed to understand the interaction of the fuel materials with the sacrificial core catcher or incorporation of various neutron poisoning agents in the core catcher material so that it can bring down the system to subcritical level as well as to contain at a minimum geographical space that is possible.
You had also indicated about Fe3O4 for magnetic hyperthermia and the hydroxyapatite for cancer therapy. These have been translated. I mean, you are collaborating with any hospitals?
Not yet we have collaborated because currently in India there is no clinical instrument which can actually do the treatment with hyperthermia, though this has been done in Japan and other places. But we do have an in vivo experiment we have been doing in collaboration with other bioscience group as well as ACTREC to explore the possibility of magnetic hyperthermia in mice to kill the cancer cell, especially in, or the tumor, to suppress the tumor in combination with other therapeutic modalities. So that is one thing what we are exploring.
I have a question here.
Yeah.
Your the detector that you use that differentiates between normal and cancer tissue, does that do you use biopsies for that, or I wasn't quite clear on how that detector worked.
Sorry, sir, I didn't get the question.
The detector that you showed that would differentiate between normal tissue and cancer tissue.
Okay.
Is that on biopsies, or because I was not quite clear how that worked?
Yeah. What?
Device.
Yeah. This has been the experiments initially has been done in the laboratory, but right now we have an MOU with the TMH. And we did obtain a couple of more than 100 biopsy samples to test or to validate the machine that is developed. This is basically based on a polymer that is capable of undergoing change in conductivity of the polymer with respect to changes in the pH, because the glycolysis mechanism in cancer and the normal tissue is different.
So this is based on biopsies though?
Yeah.
Okay.
Yeah, what is the operation temperature of supramolecular hydrogen storage system? One more question is that what do you mean by 2D IR spectrometer? Is it having a spatial scanning capability?
Okay. Yeah. The supramolecular hydrogen release, typically it is of the order of 150 to 200 if I believe, but I cannot exactly tell the number right now. Typically this ammonia borane is used as a hydrogen storage material, which can release the hydrogen typically in that temperature range, 150 to 200. And regarding the next question.
A 2D IR spectrometer,
Yeah.
does it have spatial scanning ability?
Yeah, 2D IR spectrometer that is capable of doing the IR spectra when you, after exciting with another source at the same wavelength in which actually the IR spectrum is observed. Okay, so you have something like another axis where you excite the molecule by using a pump laser and you wait for some time and then you monitor at a different time. You can monitor the IR spectra. So basically you have a scan of the pump laser wavelength can be scanned and then the probing is done after excitation. So this will give you, that way you can get the correlation of the IR correlation at different space. So this is something similar to something like a 2D NMR what we do in order to get through space correlations in molecules and other things. So it is a new development in IR spectroscopy. So this is possible.
Excellent. I think thank you, Dr. Hassan, for the excellent overview.
Thank you very much. It's
So
my pleasure.
we move on to the last lecture in this particular session by Dr. Samal from Institute of Physics.
Good afternoon, all of you. So first of all, I would like to thank HBNI for organizing such a wonderful meeting through which at least we know what are the research activities going on in various institutes or departments and also the facilities as such available in various places. So I am from Institute of Physics. By training, I am an experimental condensed matter physicist. But I have a difficult task here because I need to present IOP where the research is manifolded. So yeah, just to tell here, this is a glance of research programs carried out at IOP, experimental condensed matter physics, quantum condensed matter theory, biological and statistical physics, high energy physics experiment, high energy physics theory, nuclear physics, as well as various other areas such as quantum computation, nanoscience, and ion beam related material science research. So let me, I'll give one by one. Basically, I will just make a quick tour what people are doing at IOP. So these people are experimental peoples, including the present director, Professor Karunankar Nanda. And let me go first to this research activities of Sikha Verma. So who does this devices and sensing applications related to nano and biomaterials. So her research activities mostly focuses on sensor and detection of arsenic and mercury, glucose sensor, and also nano bio interaction, DNA absorption, DNA as sensor of toxic elements. And she uses Raman spectrometer to probe many of the things. And here some research highlights where she is probing when this mercury is attached with the DNA, how the IV curve or the current voltage curve that changes, and it can be used as some kind of sensor. Also, she looks for arsenic detection using some organic molecule. Let me not get into the details. And this is a angle result photoelectron spectroscopy group where they look at they map the electron structure in the materials. And it is a very versatile tool to map the electronic structure in various kind of materials. And this work is carried out by Bijura Sekhar. And you can see this is the experimental setup at IOP, which is known as angle result photoelectron spectroscopy. And they study various kind of exotic materials, quantum materials, like topological insulators, wild semimetals, and strongly correlated electron systems. And this is a facility at IOP. And this is a group headed by Tapabrata Som, who works mostly on the surface nanostructuring, and patterning. And he's involved in various activities. You can see in the left-hand side, he works on micro to nano materials, where he works on like gas sensing, radiation damage studies, nanoscale electronic transport, various kind of nano pattern formation, and memory devices, mainly neuromorphic computing, where they look at to understand how our brain complex structure works, and also thin film voltaics. Also, they have, this is a one system facility where this is a integrated ion patterning and MB molecular beam epitaxy facility, where they do the ion patterning, and there is a distribution chamber and there is a MB chamber. Also, they have the ECR, electron cyclotron resonance facility, which is also stationed at IOP, which they use very much for their activities. And here are some of the research highlights. As I mentioned, their group is mostly involved in doing the work related to neuromorphic computing. And also they want to mimic, they want to understand this, how does the nervous system that works this through this artificial synapse. And also, as I mentioned, various pattern, nano patterning, like this, here it is shown, this gold decorated and grating-like patterns. And these are the various kind of research activities. And this is one of the group led by Dinesh Tobbal, where he is mostly involved in looking at the correlated electron systems and magnetism, multiferroic, or magnetocaloric effect, and also mapping the band structure and the facilities which he uses very often. There is a PPMS, physical property measurement system, and also PL spectrometer, photoluminescence spectrometer. And here are some of the highlights from the work where he's mapping the electronic band structure in a topological material, and also this magnetocaloric effect, and also how he can tune, how he can tailor the multiferricity properties in various oxide materials. And this is a low dimensional group, which is headed by Satyaprakash Sahu. And their group is mostly focused on 2D materials and heterostructures for optoelectronic applications, and also for this resistive random access memory and neuromorphic computing. And the facilities they have is clean room facility. This is a 10,000 class clean room facility. Also, they have a photolithography system. And these are some of the representative research work where they are looking at this, they are making the heterostructure of the two-dimensional materials and making devices through this photolithography techniques. Then comes mine. This is, I am interested mostly in designer quantum materials, and most of my study is focused on magnetism, superconductivity, topological materials, and various of, because in the recent days, there is a lot of thoughts on materials where there is strong spin-orbit coupling. So we work a lot of this spin-orbit coupled physics, and these are some of the work where we look at how spin-orbit physics can change the electronic properties very much, like we get some kind of Dirac material in 3D while semi-metals, and these are some of the works. And the facilities we have, this is a facility maybe 3 years old. When I joined this, we installed, we commissioned at IOP. This is a pulse laser deposition system assisted with reflection high energy electron diffraction, where you can grow the films and you can monitor in situ how the films are growing. And also we have a squid VSM magnetometer, where we use it to measure the magnetic properties. And the work is basically threefold. If you look at the triangle, at one corner, we grow the films by using this facility, and we characterize them using X-ray diffraction or any other tools that characterize the structural characterization. And the main motive is we look for emergent electromagnetic phenomena. Either we do magnetic measurement, we do transport measurement, we do any kind of spectroscopic measurement to look for some kind of emergent electronic phenomena. And you can see in the top of the, here, you can see here, I show you a signature for superconductivity between, at the interface, where two materials which have been joined to make the interface, they are non-conducting, they are insulators, but at the interface we get superconductivity. So this kind of structures we make through this pulse laser deposition system, and we study their properties. And now we come to the quantum condensed matter theory group.
It involves two faculty members, Arjit Saha and Saptarshi Mandal. And Arjit Saha is mostly involved in studying the flow-cat generation of higher order topological phase systems and the characterization of these phases by dynamical topological invariant, and also how this the topological properties in the system gets influenced by strong electronic correlation. And also he is involved in a topological magnetism like skyrmions and topological superconductivity like Majorana physics. So he is mostly involved in this kind of research. And the Saptarshi Mandal, he is also interested in topological systems in 2-dimension and 3-dimension, and how various symmetries and anisotropic interaction that influences the topological properties. Also, he is involved in studying the hydrogen bonded materials. So that is one of his expertise where he is pursuing his research. And this is biological and statistical physics group. And here 2 members who are actively in this group, Debasis Chaudhary and Gautam Tripathi. And Debasis Chaudhary research activities mostly focus on chromosomal organization. So basically he looks at the helicoid shape of chromosomes, precise chromosome positioning, stability of membraneless nucleates, and also chromosome loop information. And also he is mostly involved in active matter research, like dispersion of active particles, then phase transitions in active matter, and also various pattern formation in active fluids. And these are some of the highlights where there is an experiment has been done and they have done the simulation. This is, and it exactly matches, there is a good match. This molecular dynamic simulation of a Father-Boa model of a bacterial chromosome. And also here you can see there is a pattern formation in active membrane. And this is the work from Gautam Tripathi. He's also from this group, biological and statistical physics. And he is mostly involved in phase transition in non-equilibrium interacting systems, and also rheology of soft matter and active systems, and also interfacial fluctuation in self-organized critical systems. And there is a facility also, he uses experimental facility, rheometer, and he is involved in the rheological study of how the matter flows. That is what he is mostly interested in. Then comes experimental high energy physics. These are 2 colleagues here involved, Pradeep Kumar Sahu, Arun Kumar Nayak, and they are mostly, Pradeep Kumar Sahu is mostly involved in heavy ion collision experiments and theoretical models. And there is a collaboration with the with ALICE, STAR, and CBM. So mostly these are mega collaborations, and the work is carried out through this collaboration. And here are some of the works which has been, I think it is done at IOP. So these are kind of measurement of ion backflow fraction in GM detectors, and also some simulation work. Arun Kumar Nayak, he is also involved in this mega project, the CMS experiment at SON LHC. And basically he's involved in understanding the Higgs properties measurement and beyond standard model Higgs searches. And this is basically a mega project research. And then we come to nuclear physics theory. So we have one colleague, Professor Suresh Kumar Patra, and this is nuclear physics theory. And he is involved in a various kind of nuclear physics research activities. And among them is finite nuclei, nuclear matter, neutron star, and gravitational waves. As you can see, his research is, it extends in various directions of nuclear physics. So this is, he talks about finite, he studies about finite nuclei, binding energy, charge radius, skin thickness, magic numbers, and nuclear matter, binding energy, effective mass, and incompressibility, symmetry energy. And you can see that there's a lot of works. He basically focuses on this nuclear physics theory. Now comes the theoretical high energy physics group. And we have Professor Ajit Mohan Srivastava, Professor Pankaj Agrawala, Professor Sudipta Mukherjee, Dr. Sanjeev Agrawal, Dr. Samik Banerjee, Dr. Devotam Das, Dr. Malimala Mitra, and Kirtiman Ghosh. And broad research area from this group, theoretical high energy physics, is string theory, quantum gravity, black holes, mathematical physics, collider and neutron phenomenology, then radiative correction, then QGP, gravitational waves, cosmology, and quantum information. So in various directions, these colleagues, they are involved in doing work in this theoretical high energy physics. I'll just little bit illustrate. I will not get into the details of what they are doing. Kirtiman Ghosh, he is a member from this group. He basically looks to address the puzzle of non-zero neutron masses and dark matter at different collider and non-collider experiments. And he focuses mostly on, his research focuses mostly on neutron mass and mixing, dark matter, large extra dimensions. This is Monimala Mitra. Her research goal is to understand the origin of neutron masses and mixings, the nature of the dark matter in the universe. This is Debatam Das. He is also involved in the research activities related to beyond standard model phenomenology, in particular the supersymmetry phenomenology, which includes quark, lepton, flavor violations, etc. Also, he is involved in dark matter, and also he studies this collider physics. I mean, to identify beyond standard model signatures at colliders. This is Samik Banerjee. His research interest mostly focuses on the flat space holography, asymptotic symmetries of gauge theories and scattering amplitude. And the long-term plan of his research is to develop a symmetry-based technique for the evaluation of scattering amplitude in gauge theory and gravity. So, and this is Sanjeev Agrawal, and his main research is focused on exploring the fundamental properties of massive neutrons and dark matter. And there is a world-class, and he works on various collaborative projects. There is a world-class international neutron experiments like DUNE in USA, T2HK in Japan, and IceCube or Deep Core at the South Pole, where he is involved in those kind of mega collaborations to understand this neutrino physics. Then Sudipta Mukherjee, his research activities are mostly based on string theory, classical and quantum aspects of black holes, and cosmology. And then comes Ajit Mohan Srivastava. So his research interest focuses on demonstration of existence of analog black hole and Hawking radiation in relativistic heavy ion collision, as well as the hydrodynamic flow of electrons in condensed matter systems. So basically he wants to make an analog of black hole in these two different kind of systems. Then comes Pankaj Agrawal, who is the dean of our institute, and he is mostly associated with HBNI activities. So his main interests are in high energy physics phenomenology and quantum information. And high energy physics phenomenology basically looks for new signature of the Higgs boson at collider. And also, as I mentioned, he also pursues the research on quantum information. So various quantum communication protocols, quantum cryptography, quantum noise and error corrections, and various kind of this exploration of non-locality using Bell-type inequalities. And this is a part of all this quantum information. So we have various facilities. I did not want to put intentionally the normal facilities which is available, but I want to just highlight a couple of major facilities. So this is one of the facilities for which IOP is known, this mostly experimental point of view. The 3 MEV Pelletron accelerator facility at IOP. This is the old sketch, I think when it started or something like that. So this is the real picture now. You can see this is 3 MEV Pelletron accelerator. And this is the Pelletron accelerator beam hall where various probe stations are there. You can do the experiments. And now here is a like low energy negative. Besides that, besides the 3 MEV Pelletron accelerator, we will also have a low energy negative ion beam facility. And the accelerator facility provide a unique opportunity to carry out advanced research, not only in physics, but biology, medical science, and environmental science. And I did not put a list, but if you look over the years, if let's start 10 years down the time, I mean, you will see there are various users from many state universities, central universities, and research institute. They come to IOP and they carry out the research. Also, just I want to mention, if anybody wants to know more about this pelletarian facility, the faculty in charge is Sikha Verma. You are welcome to contact her. The next is the major facility is this transmission electron microscopy, HRTEM, and it seems it was procured long back in 1999. Again, I think it requires a little bit remodeling, but still it is a old system, and the faculty in charge is Sikha Verma. And here also we have this FESEM, field emission scanning electron microscopy. So these are the major facilities where people from various disciplines, not only the researchers only at IOP, but from various other organizations, they come and take the advantage of these facilities. And also we have a computing and network facility. This is known as Sankhya. So this is high performance computing cluster, and it is 60 nodes. And this has been featured in top supercomputers in India list since January 2018. And people from various institutes, the researchers from various institutes, not only limited to IOP, they take an account to use this facility and they do their computational work. So with this, I think I'll thank you for your attention. And I would like to acknowledge to all my colleagues who contributed these slides so that I could consolidate it. And I would like to thank also the director for his support. Thank you very much.
So thank you, Dr. Samal, for a holistic snapshot of the facilities, research activities at IOP. Questions? Let me start. Okay. You have indicated about sensors for detection of arsenic and mercury, and also about the glucose meter in the second glucose sensor. Has these been, technology transferred, or they are at the lab stage?
No, I think these are at the research stage. The technology has not been transferred.
In the research stage.
Yeah.
Any other questions? Online, do we have any questions?
It's more a suggestion for thought than a question. The aim of this meeting was to make every faculty aware of what other infrastructure and facilities are available in other places and what programs are being done by others. So in that context, I think the computational facilities also need to be thought about, because, for example, I'm giving an example. In the same city of Bhubaneswar, we have IOP and NISER. Whether computational facilities can be shared online by students by logging in and submitting jobs, etc. This kind of optimization may become in future important, because overall there is always a pressure on funds. Even for library, we are being asked why we are not sharing it. But now I find so many institutions having high-end computing facilities. So what way this could be, utilization could be optimized by across the CIs is another point which can be thought about, especially when it's in the same location. That's what I'm.
Yeah, do I have to answer or? Yeah, I think that's a good question, because as I mentioned, this facility, because it's not only shared by utilized by the IOP people, but I know some of the people from IIT, close by IIT Bhubaneswar, they also have account in our institute and they use it. So Professor Ponda is here, NISER director. So I think IOP always free, welcome if anybody wants to get a account and use this facility. So I think it depends upon who are interested to use the facility.
If there are no other questions online, so then we would like to thank Dr. Samal for the excellent overview.
Thank you very much.
In this particular session, we had 3 excellent overviews on biological sciences from NISER by Dr. Harapriya, Mahapatra, chemical sciences from BARC by Dr. Hassan, and physical sciences, you can see by Dr. Samal from IOP. So we come to the end of the session. Once again, thanking HBNI for organizing this particular wonderful, I should say, unique meet, which has really opened our eyes on the various facilities. I hope that we would move forward through the sharing of these facilities and trying to make the facilities available to each of the researchers, as has been mentioned by our Vice Chancellor also. So thanks to all the participants and thanks to the speakers and their institutions. Thank you very much.
Thank you, Professor Venkatraman, and thank you all speakers. We will now break for about 15 minutes and meet back at 4:15 for the final session.
The atomic energy program was started in the country in 1948, and the Department of Atomic Energy, DAE, was established in 1954 by the visionary Indian nuclear scientist Dr. Homi Jahangir Bhabha, who envisioned it as the hub for the development of nuclear science and technology and their applications. The objectives for DAE were multifold, namely to create know-how for harnessing atomic energy for power generation, using radiation technology for societal applications in agriculture, healthcare, and industry, while carrying out basic research in a variety of domains of mathematics, science, engineering, and medicine. Right from its inception, DAE has placed great emphasis on the in-house development of human resources for carrying out its research and development activities. To meet this objective, the BARC Training School was established in 1957. Subsequently, to further strengthen the framework for human resource development at DAE establishments and push the frontiers of nuclear science and engineering through academic programs, the Homi Bhabha National Institute, HBNI, was established in 2005. It was recognized as a deemed-to-be university by UGC and given the status of a grant-in-aid institution of DAE in 2014. HBNI was accredited with an A grade by National Assessment and Accreditation Council in 2015. HBNI conducts postgraduate and doctoral programs in various disciplines across its 11 campuses, comprising the 4 research and development units of DAE, Bhabha Atomic Research Center, BARC, Mumbai, Indira Gandhi Center for Atomic Research, IGCAR, Kalpakkam, Rajaram Center for Advanced Technology, RRCAT, Indore, and Variable Energy Cyclotron Center, VECC, Kolkata, and the 7 grant-in-aid institutions of DAE, namely Harish Chandra Research Institute, HRI, Prayagraj, Institute of Mathematical Sciences, IMSc, Chennai, Institute of Physics, IOP, Bhubaneswar, the Institute for Plasma Research, IPR, Gandhinagar, National Institute of Science, Education and Research, NISER, Bhubaneswar, Saha Institute of Nuclear Physics, SINP, Kolkata, and Tata Memorial Center, TMC, Mumbai. HBNI is thus a conglomeration of constituent institutions and off-campus center with a thriving academic and research environment. The organizational architecture of HBNI, with a central hub at Mumbai being linked to centers of excellence all around the country, is one of its strengths, and has facilitated research and development across diverse disciplines while sharing common objectives. The academic and research activities at the constituent institutions have significantly enhanced the country's indigenous capability in nuclear science and technology, and generated capable and dynamic human resources to man and spearhead these programs. HBNI offers options in 32 diverse academic programs across physical sciences, chemical sciences, engineering sciences, mathematical sciences, life sciences, medical and health sciences, as well as humanities. In addition, HBNI also runs several academic programs towards skill development for the country. In the 15 years since its inception, HBNI has awarded over 1,600 PhDs, with around 250 PhDs being awarded in 2019-2020 alone, a notable academic achievement. More than 2,200 publications in high-quality journals during 2019 bears testimony to the faculty and student quality of HBNI. Students are also encouraged to present their work at international conferences by extending financial assistance. Apart from the quality of faculty, mentors, and students, excellence is enabled by world-class research facilities such as research reactors, accelerators, state-of-the-art equipment, and ultra-modern experimental and computational facilities across all its centers. This has created the ecosystem necessary to push the boundaries of innovation and solve crucial and challenging problems. HBNI has been ranked 14th in the list of top universities in the country by the National Institutional Ranking Framework. In recent times, MOUs have been signed with several eminent national and international institutions. These measures shall also add a range of value-added programs to the curriculum and are expected to lead to a further enhancement in the quality, outcomes, and ranking of HBNI in the future. HBNI is also rapidly adapting to the new age teaching methodologies, and capacity is being ramped up towards improved infrastructure facilities in sync with the current trends of online teaching, webinars, and incorporation of augmented and virtual reality in the teaching learning methodologies. This is expected to increase opportunities, raise academic standards, and widen the base across various segments and strata of the academic community. HBNI is today recognized as a world-class university in the sphere of nuclear science and technology. With the zeal and motivation of its faculty and students, and steered by an able administration, HBNI is expected to scale new heights in the years to come. It provides a vibrant platform for bright young minds to explore, endeavor, and succeed in the fulfilling pursuit of scientific and technical advancements across a gamut of domains.
Not this. Welcome back to the fourth and last session of today's program. This session will be chaired by none other than Professor Sudhakar Panda, Director, National Institute of Science Education and Research. Sir, please.
Okay. I congratulate HBNL team, the Vice Chancellor, the Dean, the Associate Dean, Registrar, just to force us to come and we get together after years of not seeing each other, except photographs, etc. I also congratulate HBNL being a member of COM for organizing this, and I expect many more such things where many COs will join hands and we'll have science discussions. With that, again being the last session of the day, but I hope the coffee is taking outside more, and I know that BARC came a bit late, so people are getting late. But we should start. So I invite Professor Hema Rajaram, BARC, who will be speaking to us on BARC Live. So we had one NISER Live, and then we'll have a BARC Live. So let's see that how the lives are different in these two institutes. Okay, Hema, your time starts now.
Sure. At the very outset, I would like to thank HBNI for giving me an opportunity to share the work of life science at BARC with other CIs here. And I'll just take you through the flavor of work which is being carried out here, which is basically in the field of radiation biology, cancer biology, DNA repair, gene regulation, bioremediation, structural biology, and two unique areas of nuclear agriculture and food technology, which I'll take up first. So what is nuclear agriculture? Here we are basically looking at 5 major things: crop improvement, integrated pest management, biotechnology, bioregulators, and agro-waste management. And this is basically grouped into applied physics, applied research, as well as basic research. The applied research, we are referring to plant breeding program, looking for enhanced yield, earliness, plant type, disease resistance, improved nutritional quality. While in basic research, we are characterizing these mutant traits. Then DNA markers are being developed, characterization of promoters, and abiotic stress tolerance and other features. Till date, 55 crop varieties have been notified in Trombay, which is in the field of oil seeds, pulses, cereals, and others like banana, sugarcane, ornamental flowers. Ornamental flowers, along with cluster bean and moringa, are the new initiatives. While these agronomically useful plants are being released, we also need to know what are the mutations which are arising, which is giving them the beneficial, which is giving them the advantage. So some of the examples I'm sharing here, for example, in case of cowpea, a particular mutation was obtained that there was a change from the indeterminate growth of this plant to a determinate growth. So this helps in actually mechanical harvesting when the growth is stunted. And this, through gene sequencing, was found to be a single base mutation in the protein, in the gene TFL1 homolog. Similarly, in case of black gram, the whole genome sequencing was carried out, which helped identify about 1659 disease resistance genes. And what is the utility of this is, this can now serve as a reference sequence for further studies on characterization of various radiation-induced mutations which are obtained, and also help develop DNA markers. This can be suitably employed for the future breeding programs as well. And several of the genes which have been identified in black gram is also common with other pulses which we have seen here. Now, when we are talking about stress, this thing, one of the major stresses which is being seen, especially in the areas of West Bengal, is that of heavy metal. And quite often the rice kernels there have a lot of arsenic. So we were looking at different chemical agents which can help mitigate it. And one such agent which we found was thiourea. And this was initially found that it increased the length of the roots, but later it was found that it was also preventing the uptake of arsenic in rice plants. As a result, the rice kernels did not have arsenic or had very reduced content of arsenic. So now this can be used and tried in the West Bengal fields, which have a lot of arsenic content. Similarly, banana, which is a very important fruit crop, it is vegetatively propagated. As a result, its propagation process is very slow. Here at BARC, we developed large-scale propagation systems using shoot tip multiplication, somatic embryogenesis, and cell suspension cultures. And now this several laboratories in India are using these things. And the advantage it has given is that we are now able to do a lot of genetic engineering in banana and also study several transcriptional factors which are involved in stress tolerance and growth so that you can develop better banana varieties as well. Now, for all this work, we have a greenhouse facility. There's a climate controlled plant growth facility, which you can see here. And this is the inside of the plant growth facility. Now, when we are talking about increasing harvest and better yield, we also need to actually, we do have losses in the storage of these food grains because of spoilage. So we are also looking into different processes to actually prevent this spoilage, and we are using gamma radiation to this effect. So for example, we've used gamma radiation to control spoilage of food grains and spices, control sprouting in potato and onions, and also helped, these irradiation has facilitated overcoming the quarantine barrier as in case of mangoes. Now, what the work, right now we have 25 irradiation plants across India. Now, what is one has to do is for different food products, you need to actually develop the dosage as well as the packaging facility and the food storage facility right through the system. Now, what does this, why does the spoilage occur? It is because of the microbes. So you need to detect the microbial content which is there. And normally, if you want to look at count the microbes, it takes almost 1 to 2 days. So here in one of our divisions, they have understanding the biochemical changes which were measured with GCMS and FTIR, they were able to directly get the microbial count within 15 to 20 minutes. And they use several computer programs like ANN, etc. for this purpose. So, and then once we are looking at that there is microbial growth, is there any other way other than radiation where we can prevent it by intervening? So when we talk about microbial infection, it is because of quorum sensing that it happens, that the microbes have to get together. So if we can block this quorum sensing using certain novel molecules which have been identified now, that will be one way of actually reducing the microbial growth. And when we are talking about microbial growth, one of the important pathogens which has been studied is the Xanthomonas species, which is known to cause almost 35% crop loss in case of soybean. And why is Xanthomonas also very famous is because this was the first bacteria in which programmed cell death was actually identified, because it used to be, it was a phenomenon which was associated with eukaryotes and not with prokaryotes. And now they have identified that this PCD is related to its virulence. And this is genetically controlled. So if we can target the elements of PCD, we can also target the pathogenesis as so that we can help save the loss of soybean crops in this process. From the plants, we have isolated several natural bioactives, some of which are now being used for fortifying food for its beneficial use. And some of them are used for health benefits like malbaricone C from fruits of rampatri, then dihydroxystilbene from Yucca periculosa, and allyl paracaticol from piper beetle leaves for different cancer treatment and other diseases. From here, I come to another unique area, which is in radiation biology, is looking at the high-level natural radiation areas in the coast of Kerala. So here, earlier, the entire work was centered around looking at the mutations, epidemiological approach, etc. But now the focus has shifted to looking at what is causing these biochemical changes, etc. So for this, a transcriptomic and a proteomic approach has been taken. And what has been found is that there is a radioadaptive response, and there is higher expression of DNA repair and pro-survival proteins and transcript in the people who are staying in that area compared to the people staying in the normal background area. So which kind of tells that how they are able to sustain in those areas. Then what I was talking about when you're talking about high-level background area is that there is a chronic exposure to radiation. But what we face when there is radiotherapy or radiation accident is a sudden acute dosage. So under those conditions, what happens? So this is something which we have started looking into. So one of the aspects we are looking into is what happens to the immune system. So what we have seen is that if it is done with mice here, we can't do it with humans. So when you prime it with a lower dose and then challenge it with a higher dose, there is a radioadaptive response. So not only in case of chronic radiation, but even in acute radiation, a radioadaptive response is possible. Then now I'll come to cancer biology. You have heard several people talking about it, and we are looking at another aspect of cancer biology here, looking at the basic biology, therapeutics, as well as diagnostics. So we are looking at the microenvironment in the tumor region, basically looking at the interaction of tumor and immune system. This is basically to help identify different prognostic markers and develop immunotherapies to strengthen the immune system. Until now, about 3 agents have been identified, and testing of these is currently underway. Then we're looking at, when we talk about cancer, one of the hallmarks is DNA repair. And an important protein in this, which is being studied worldwide, is RECQ helicases. Here we are looking at two of the RECQ helicases. One is the Werner RECQL helicase, which they have found using RECQL deficient, Werner deficient mice, that these mice are actually, can be targeted for radiosensitization as well as chemosensitization. So if you can develop drugs to target this particular protein, you can radiosensitize and chemosensitize cells, and thus for better cancer treatment. Similarly, in case of breast cancer, the RECQL5 levels are found to be very high, and that results in poor prognosis. So one molecule has been identified, which is called 4A, which is able to bind to RECQL5, and it stabilizes the RAD51 RECQL5 complex, so the homologous recombination is suppressed. So this results in sensitization of these cells to therapy. Of the breast cancer cells to therapy. Another agent which we are testing for sensitizing the breast cancer cells is DBET6, which is a degrader of BRD4. This bromodomain 4 protein is important for DNA replication, and if its levels are low, then it results in high double-strand breaks, so that you can target the breast cancer cells now to radiation and get a higher loss without affecting the normal cells. So right now we are looking at what is the mechanism of this DBET6 on BRD4. Now, we also need to, like I said, we are also looking at different biomarkers as a way to detect cancers. And this is both for predictive, prognostic, diagnostic, and pharmacodynamic markers, which are being looked into. And having cytokines, chemokines, proteins, miRNA, and DNA are the different things that we are looking into. One such example I'm giving here is for NET, neuroendocrine tumor, where blood biomarkers are being used. And why blood biomarkers? Because they offer better insight into the disease dynamics. And this can actually, if you're able to identify it, then you can actually give a specific therapy to the specific patients, and you know what is going to be the outcome of the therapy. So better therapy can be used for these people. Then we are also developed several organofluoromolecules like BODP, DPP, etc., which can be used for laser dyes, photodynamic therapy, organic electronics, photovoltaics, and chemical biological sensors. Then in the same line, several organic molecules have been identified or synthesized rather, which act as ligands for radiopharmaceutical target, using as a radiopharmaceutical for targeting for both diagnosis as well as for therapy. And here it is linked to either, in this case, a radioisotope, and then this actually binds to specific targets. For example, MIBI for myocardial perfusion imaging, PSMA 11 for prostate cancer diagnosis, and PSMA 617 for prostate cancer therapy. Another way of targeted therapy is through use of nanoliposomes. In this case, magnetic nanoparticles were used with the oleic acid, and either putting chemotherapeutic agents inside it, like deoxyribicin, or just as it is. They were found to inhibit tumor growth as well as cause radiosensitization. So this is a good approach, and a patent has already been obtained in this field. Then we are looking at other newer approaches or novel approaches for this. Now, when we are talking about any kind of a radiation injury, then it does cause toxicity to humans. Why does it do so? So using different studies, it was found that these actinides are able to interact with human hemoglobin as well as with human serum albumin, which is one of the reasons for this toxicity. So by knowing that where exactly they are binding, this can help in the development of novel synthetic multidentate agents for decorporation of these actinides, specifically thorium and plutonium. Then other novel agents which we are testing, you need to test them in bulk, because you know that it's not that single agent. You will have to test around 100 agents to get one agent. So we have a high content screening system for this purpose. So we are able to screen several drug libraries, small RNAs, kinase inhibitors, etc., and undergo in vitro and in vivo validation for this, then preclinical trials followed by translation into clinical studies. And newer strategies are also being adopted, like cold atmospheric plasma irradiation therapy, which this unit has been designed with the help of IPR. Then we have our own Babatron 2, that is cobalt-60 teletherapy unit, an alpha irradiator, and a hypoxia chamber. Why hypoxia chamber is? The tumor cells actually have less oxygen compared to the normal cells. So this hypoxic chamber actually mimics that condition when you're testing. So you get a more truer approximation to when you want to do any kind of testing with these cells. And we're also looking at stem cell therapeutics, which is an upcoming field. So what has been done is mesenchymal stem cells from Wharton jelly from human umbilical cord has been used and introduced into irradiated mice. So normally when irradiated mice, the animal dies. But in this case, these cells are able to regenerate the damaged tissues through modulation of intrinsic abundance of stem cells. And there is no rejection of the stem cells either. So as a result of it, the animal survives. So it will be good if this can be now propagated to the next level and test further. For all this work, we have Animal House facility, which is shown here. We have the IVG cage system for immunocompromised mice. And these are some of the tumor models which have been developed here in the Animal House facility. From here, I'll go to some amount of structural biology, which we are carrying out, where basically we're looking at structure-function relationship, different targets. Here I'm showing one of the protein is PSP94, where its dimerization and its binding to different proteins has been shown. Then SARS-CoV-2 proteins have been characterized. Some of these are being characterized, which is a very recent work which has been started. Then several cancer drug targets, malarial drug targets, and those with biotechnological applications like SPAP and CATB. What is CATB? It is basically a manganese catalase from Cyanobacteria anabina 1720. Why it is important is it is highly thermostable, almost at 80 degrees. It is as stable as that. And this stability through structural analysis was found to be due to the N-terminal region. And what we are now trying to utilize this in the textile processing industry, which is done at high temperature, and normal catalases are degraded in this process. So now we are testing it in collaboration with ICT right now. And this is work which has been carried out in RRCAT, and already Dr. Debasis has talked about it, so I'm skipping this slide. Then we're doing some basic research in DNA repair. Till now, I was talking about DNA repair in cancer cells. Now I come to radio-resistant organisms, where we are studying DNA repair, that is in Deinococcus and Cyanobacteria. So in Deinococcus, DNA repair is being studied world over, but we have certain unique niche areas where we are looking at it. One such protein which has been identified is RQKA, which is radiation-inducible quinonoprotein kinase. This has been found to phosphorylate several DNA repair proteins as well as cell division proteins. So having seen that, now the inquisitiveness is whether this phosphorylation affects the genome segregation in Deinococcus, because that is a field people have not looked into as yet. Then another important aspect, especially it was in human cells, where it was seen that G4 quadruplexus plays an important role in cancer. Here we are seeing that in Deinococcus also, there are a lot of G4 quadruplexes. So, and when an agent was added, which stabilizes the G4 quadruplexes, it was seen that the DNA repair gene synthesis actually came down. So this kind of indicated that G4 quadruplexes may be playing an important role in regulation of DNA repair genes and in the radiation resistance or sensitivity of this organism, as well as possibly other organisms. And this study is being undertaken right now. When we talk about radiation damage, it is mostly double-stranded breaks and lots of them. And so which other stress causes these double-strand breaks? It is desiccation. So is there is some commonality between these two? So this was studied by looking at the proteome of irradiation and desiccation stress in Deinococcus, and several proteins, as you can see here, belonging to DNA repair, transcription, translation, folding, and ROS detoxification, which are found to be common for both these stresses. And we see that it is not that each abiotic stress is independent of each other, but there is a lot of overlap between these stresses, and which is required because the cells have to evolve in that process. Now, while studying DNA repair, I talked about two aspects which were studied. A third aspect which is being studied in Deinococcus is identifying the proteins which are involved in the homology-dependent DSB repair pathway in this organism. So this was done through co-IP-MS based methods, and the proteins have been identified, and now further identification and deciphering the mechanisms of radiation resistance using other pathways is now being undertaken. Similar work is being undertaken even in cyanobacteria, where the pathways is different from that in Deinococcus. So we are trying to identify the different genes which are involved, as well as the interactome responsible for the DNA repair there. So when we're talking about changes in gene expression, that means there are regulators involved. And one of the DNA repair regulators, which is very famous in bacteria, is LEXA. But when we looked at in cyanobacteria, this LEXA was found to be a global regulator. It was affecting photosynthesis, it was affecting oxidative stress management, DNA repair, as well as metal homeostasis. So now we have identified the region where this LEXA protein binds, but we are looking at how right through the genome where all it can bind, so as to have a global picture of it, because this is the first such report that has come out in any bacteria. Other gene regulation aspects which we are looking at is in plants. Like in case of rice, we have found that superoxide dismutase, there are several, from a single gene, several splice variants have been obtained. So gene splicing is one of the ways of regulating the gene expression. And in this, though the process, how it happens is not very well known, we are looking at plant bromodomain gene family, because bromodomain proteins are known to regulate gene splicing in mammalian cells. But how they regulate in plant cells is not known. So that work has been undertaken right now, and we are looking at the significance of these genes here. Then till now, I've been talking about proteins which have a definite structure and playing a role, regulatory role. But there are certain proteins which are intrinsically disordered, and these proteins generally undergo liquid-liquid phase separation. So how can these proteins also affect gene regulation? So we took one of the examples as RNase H, which is capable of LLPase, and we showed that if we disrupt its process of undergoing liquid-liquid phase separation, then there is increased generation of R loops, resulting in destabilization. So the mechanism here is also now being, we are looking at how to understand this mechanism of liquid phase separation in this particular protein molecule. Then we are using CRISPR, is something which almost all of you would have heard because of the COVID times. Here we have done a lot of work on using the CRISPR technology. We have established, in case of eukaryotes, we have engineered type 1 CRISPR-Cas system as an antiviral system in yeast. Then we have used it to study essential genes in E. coli, for example, RACR, which has been identified as a toxin-antitoxin system. And in case of used also as an antimicrobial agent, and see, in this case, we have used it for selective targeting of drug-resistant mycobacterium. Basically, we are able to distinguish between different species of mycobacteria using targeted CRISPR. Then coming to the last topic of bioremediation, which is very important because here we are looking at both solid waste management and liquid waste management. For solid waste management, we are using fungal spores, and several hypersporulating mutants of these fungus have also been obtained. And this causes a very rapid composting. And this compost can actually be used to enhance the plant growth as well. In case of liquid bioremediation, one of the important metals that we are looking at is uranium, where several bacterial species have been tested. For example, 2 cyanobacterial species, Anabina and Senecococcus, then Serratia. And right now we are focusing our work on Chrysiobacterium, which has been isolated from the uranium-rich regions in Domiastat. And here we have identified a metal transporting P-type ATPase, which we think is responsible for its high resistance to uranium as well as its ability to sequester it. And this organism also shows beautiful gliding motility as well as iridescence. And this has actually come as on a cover page of one of the recent journals. And one of the instruments which is being used for this study is SEM. And here you can see the self-assembly of the Chrysobacterium cells when it is spreading across the plate. Then we are also using, when we talk about bacterial cultures usage for heavy metal bioremediation, it could be single culture or multi-cultures, a lot of cultures together. So here we used axenic cultures and we found that it was capable of sequestering metals at a wide pH range of 5 to 10 and concentration of 1 to 100 ppm. And now we are looking into the biology of it, whether the EPS which is being produced by this organism is responsible for it. Since the EPS biosynthesis pathway is unknown in this organism, we are now trying to decipher it and also help modify this organism for better bioremediation. One of the instruments we are using, we have here is an electron force microscope, atomic force microscope, which can, where we can see the EPS formation on these cells. And when we talk about metal microbe interaction, then that is bioremediation, there is an interaction between the metal as well as the microbes. And here this has been used to actually detoxify selenium and tellurium to selenium 0 and tellurium 0. And this actually then is present as metalloids here. And these actually forms like granules, so it is very easy to separate out. Then this has already been shown, like for sewage treatment, hybrid granular sequencing batch reactor has been used, which can be actually used for different processes such as biodegradation, denitrification, phosphorus removal, bioreduction, mineralization, and nitrification, etc. So in this case, we have granulars, means it is a lot of different bacterial cultures depending on from where you have used the sewage. So with this, I want to thank you all for listening to me. And these are some of the mutations which have been generated in NABTT of all our ornamental flowers. And I want to thank all my BSG colleagues for sharing their work for me to help me present this.
Thank you, Professor Hema. Wonderful talk and explaining the life of BARC life science people.
Thank you.
Couple of questions, comments, anyone? Yeah, just type. Sorry. Yeah, back.
Yeah, there was a lot of discussion about the usefulness of basic science.
Yes.
And I just, in one of the slides, I saw a mention of Bhavatron.
Yes, sir.
Cobalt-60, which you use
Yes.
for irradiation, right? Now, in 1956, Cobalt-60 was used to establish the handedness of weak interaction. I mean, that weak interaction is left-handed was, experimentally proved through Cobalt-60 experiment using Cobalt-60. Now, nobody thought at that time that, how many years, 60, 65 years down the line, it will be used for irradiation.
Okay, but just to answer your comments, yes, I know people do talk about usefulness of basic science. Why should you do this? Why should government fund for it? I think they never think about what is basic science. And they think that it's like corporate sector. I give you this much money, 1 year later, how much you return to me? That is the mentality. If that is the mentality, we want to do science, yes, basic science will be beaten up. And the day basic science will be weakened, you cannot do any other science. There is no applied science exist without strong basic science. So that is our job to talk to people that how much you know about basic science. That's our job, but we shouldn't just listen the criticism of basic science and run away from the platform. So anyone who argues with me about basic science, he goes back his own way and I go back the other way. That's it. But I wanted to know, just basically not a comment, actually curiosity. Is the Akruti program of BARC the spin-off of your plant biology?
Yeah, I think Dr. Gautam will be able to answer because he is involved in Akruti program.
Well, most of the thing, Akruti program things I listen, basically I see that it's the research of this lab out.
See, actually, this concept of Akriti came long back at the time of Dr. Kakotkar. Actually, they want to take this applied R&D done for the society. And that's why all the technology in the area of nuclear agriculture and all other technology, even the instrumentation, etc., they want to take to the society. That on the more cost-effective way, and other thing, to generate the workforce among the users. So that's why they want to train the farmers or the associated people, and they become the trainer for the others. So that's the purpose of Akriti. And certainly many of the technology of the bioscience group are the important contributor in the whole Akriti program, particularly from the nuclear agriculture and the food technology division. Many of our technologies are the part of Akriti technology, and Mrs. Mule is taking care of those things. And many are, they have established many Akriti center. One is the Pandharpur, now they have established Tarapur, NPCIL also helping them and their CSR activity to promote it. So now this is really coming out. We have seen a few, many good products coming out from that, and many people are getting implied also.
Yeah.
So that's the way Akriti is doing. So
Thank you.
Thank you.
Any
Yeah.
questions?
And Dr. Ghanti,
Group
Director Bioscience Group also want to add.
Yeah, just I would like to add here that Akriti technologies are also at subsidized rate.
Subsidized, but what I was interested to know is that your technology is a spin-off of this research from this.
Yeah,
it is a spin-off.
Yeah, in the website it is, there are lot many technologies are there through Akriti, it is transferred. And also one more important thing, this rural women self-help group, they are also involved in propagating and using this technology. That is the most important part. So, thank you.
You can see that also the whole thing was basic science research, which got transported to to agricultural output, and really we are using that. So, anyway, we human beings have the habit of that criticizing each other's things, right? So not only basic science, in basic science we also argue that it's physics better than chemistry or mathematics better than computer science, etc. So that's our habit. So we should not worry too much about who is criticizing. We take it off our own head and we decide what we should do. Okay, so if there are no more questions, let's again thank Professor Hema. A wonderful talk. I made this statement because in my early days of when my PhD time, when I started doing string theory, people told me that it is neither physics nor mathematics. So that continues forever. Yeah. So the next speaker is Harishchandra Research Institute Maths by Professor Thangadurai. Please come over to the stage. The stage is yours and your time starts now.
Yes, sir. I'm thankful to HBNI for this nice discussion meeting. And I'm thankful to all of you. You are going to listen to mathematician. Okay. So in HRI, there are two divisions, physics, theoretical physics and mathematics division. Okay. So my colleague Anshuman Maharana will speak about theoretical physics tomorrow. I am going to talk about mathematics division. So for a mathematician, what we need is good office space, library, good library, and basic computing facility. I mean, I'm not expecting HPC or something. Okay, that's what a mathematician, this is all just I'm confined to only maths in the library, whatever I'm saying, it is pure maths books. Okay, so like HRI has all this, therefore I will proceed. So only possibly the database, I should say, Science Direct from consortium, and Maths Scinet, it's meant for our mathematics search engine for our papers, and Project Euclid. This is also kind of Project Euclid, Jester. These are all particular journals you can able to get it online. Okay, Springer. These are the special thing. That's it. I guess many other place they may not need it, just that because wherever mathematics is there, they will be using it. Okay. So what is our program? We have one program, PhD program, which is basically started from 1993. 65 students. I am talking only maths again, because you should not think that HRA produced only 65. Oh, mathematics students graduated till 2021 is 65. Among them, 40 are kind of in this all academia only. All are in this particular. You can there's a list, and 10 of them in the private universities, and the rest of them are in postdoctoral degree. Okay. So currently we have 28 research scholars. We are 11 faculties and about 16 postdocs currently. Okay. So other activities is visitors program. It's really active, but except last 2 years. Throughout the year, we have a visitors program for our collaboration. And also we have a lecture series. I mean, distinguished or junior level or senior level visiting faculties. They give advanced courses. This is the way we go ahead with it. 2 weeks to a month long. It depends how much they can spend time. Okay, this is the other outreach program. Okay, so from plan projects, of course, we have a focused workshops for a research call. It's which meant for postdocs or young students. Other than that, we have every year there is a summer program, which is just to motivate the university students to do higher mathematics in better way. Okay. So every year we do that. What we do is it's like a workshop. It's summer program in other institutes. It may not be like a workshop. It's kind of reading course. But here from 2001, we have been following like a workshop covering only the MSc level, subjects. I mean, in maths, we have a fixed kind of subjects which are needed for higher studies. So those things we will cover just because there is always saying that, okay, many universities, students teaching, many universities teachings are not great. So we wanted to give a kind of atmosphere, which is very successful. We found out very successful. This has been going on from 2001. So the other one for schools, this is talent search program. We do it for maths and physics in and around Allahabad schools, okay, high schools. Okay, let me get back to. Okay, so what are the research areas mainly focused in HRI in mathematics? One is algebraic geometry, 2 members, Umesh Dubey and Raghavendra. Other is differential geometry, Hema. Finite group theory, Manoj Kumar. Harmonic analysis by Ratna Kumar. Lie algebras, Punita Batra, all are kind of 1-1. So number theory, there are 5. Dalavat, Apramipal is a new addition. Gyan Prakash, DS Ramana and myself. Okay, but though we have 5 people are there in this number theory, but you will see that all are different type. Anyway, I will get into. Okay, so I would like to explain kind of some glimpse of what all we do. Okay, main theme is going to be one major kind of question. We progress towards that question. That's the way I have written. Okay, first geometry, Umesh Dubey and Raghavendra. So algebraic geometry is a study of solutions of sets of system of polynomial equations. Okay, so that sets are called algebraic varieties. So whenever we introduce some kind of objects, we would like to classify, because two new objects may look like different thing, but whether it is one and the same or not, that is the major question we always address. So the main object, the central problem in geometry is a problem of correct classification of algebraic varieties. Okay, this is a solution set. Fundamental to the study of this problem is the notion of moduli space. That's what these two colleagues, they look at it. These are spaces that parameterize interesting families of geometric objects, such as curves, surfaces, etc. Okay, Umesh and his collaborators have obtained results on moduli spaces related to functorial constructions. All are, leading to the same question only, but with some technical names. Okay, functorial construction of moduli of parabolic bundles. Indeed, okay, some three results I have mentioned, what he and his collaborator have done. The functorial moduli construction of for pure sheaves on higher dimensional smooth schemes was done already. What this Umesh and Sanjay has done, Sanjay Amurtya, he was ex-HRI student, right now he is in IIT Gandhinagar. Extended the functorial construction to the moduli of parabolic sheaves. Okay, everything leads to the main question only, but more technical. Okay, they also kind of gave moduli construction of filtered representation separately. Okay, another work of Umesh along with Raghavendra and Pradeep. Pradeep Das is a student of Raghavendra. Okay, studied the semi-stability of T-tensor product of representations on internal product of two QS. This is again special towards the same problem using algebraic and symplectic methods. Okay, the last one is the classification of compactly generated tensor T structures of unbounded derived category of quasi-compact. These are all just really technical terms, but it is really classifying one particular object again. And okay, quasi-separated schemes in terms of filtrations. Okay, this work was done with his student Gobinath Sahu. Okay, so the next one is differential geometry. Yes, okay. In the theory of harmonic manifolds in differential geometry, the central question was conjecture, which says any simply connected harmonic manifolds is either flat or a rank 1 symmetric space. Okay, so the conjecture has been proved for dimension 4 by Lichten or Wicht, because this is my subject is number theory. I may not know all this mathematicians. Okay, I may not pronounce it correctly. Okay, so it follows from earlier work of Hema that an asymptotically harmonic manifolds of dimension 3 is flat or a rank 1 symmetric space. Okay, thus proving the aforementioned conjecture in dimension 3 for asymptotic manifolds. Okay, the similar she has done, she has proved this conjecture for dimension 4 also for asymptotic, harmonic and Einstein manifolds, which by proving that is either flat or it is of rank 1 symmetric space. Okay, so this okay, that's what it's explaining in some sense. The proof has something interesting in her proof, which says something stronger. The stronger merit of this proof of her is construction of some Singer-Thorpe basis. Okay, the recent work She has shown that asymptotically harmonic manifolds with minimal horospheres are flat if they are either Einstein or homogeneous. Okay, this is also related to that similar conjecture. Okay, so it's just a glimpse of differential geometry. Okay, now it's finite group theory. One of the most important and beautiful theme unifying many areas of modern mathematics is a study of symmetry. Group theory is the mathematical study of symmetry and explores general ways of studying it in many distinct settings. Manoj Kumar and his collaborators use their work in group theory to enumerate skew left braces of small orders to obtain so-called set theoretic solutions of quantum Young-Buster equation which is arising from physics. Okay, cohomology theory for braces acting trivially on abelian groups was recently introduced by Leb and Vendramin. The other mathematicians suggested that some ideas about non-trivial action. Okay, the Manoj and his student Nishant investigated the second cohomological group of left skew brace acting on abelian group, which viewed as a trivial left brace, but and it established a bijective correspondence between the second cohomology group and class of extension of the left skew braces. Okay, I'm just okay. So in another major problem in group theory is kind of finite group theory is classification of finite groups that Thomson has done, but there is a sub classification, in some sense finer classification. Which was left is to classify all finite groups in which every element of the commutator subgroup is a commutator element. Okay. In this problem, he has been working on this and he has continued to work on this. Along with his student Rahul Kaushik, he investigated the finite P groups of order P power 7. Okay, P meant for primes. Okay, and presented a fine characterization of those groups G of order P power 7, whose commutator subgroup contains elements which are not commutator. Okay. So therefore, their work along with the existing theory suggests that this phenomenon may take place in finite P groups in general. This is the first time they are. Okay, next is harmonic analysis. P.K. Ratnakumar. I will mention two of his work. Okay. One of the question is whether function and Fourier series, I mean Fourier cap, these two, how far it is reciprocal to each other. That problem is kind of, I'm telling it very roughly, uncertainty theorem. For each group, one has to find out what is the uncertainty principle. Okay, so in some years ago, Ratnakumar along with E.K. Narayan, they proved yes, type of uncertainty theorem for Heisenberg group. This result is interesting because the analogous results fail to hold in the setting of usual Euclidean space or more general simple Lie groups. Okay, so other modulation invariance his work is recent one with Ramesh Manna and Anupam, another postdoc. Okay, this says that he was kind of classifying one particular space, Hilbert space, having two properties, which is nothing but L2 Rn. That's what first work says. Okay. The another work with Sohani, he's also, alumni of HBNA, a HRI student. Along with him, he proved a well-postness for the initial value problem for non-linear Schrodinger equation. Okay. Okay. this is going on. The last work is kind of, I mean, he has done many, but he has picked and he has given one. Another interesting result proved with his student, ex-student, Divyang Bhimani, which concerns about the functions operating on the modulation spaces. Okay, this result is important in the sense, I mean, this their proof gives a negative answer to a open question. That is the reason this is really important. Okay, so next one is Lie algebra. It's a Punita Batra and her collaborators and students. Okay, the representation theory of infinite dimensional Lie algebras is of great interest in both mathematics and physics. An important question in this topic is the classification of simple integrable modules. Again, classification problem over this algebras. The classification of such modules for certain infinite dimensional Lie algebras called twisted full toroidal Lie algebras was obtained by Professor Punita Batra and her students. Just I am naming Priyanshu Chakravarti, Shaubik Pal, and Shantanu Dubey. Okay, these Lie algebras are universal central extensions of twisted multi-loop algebras, which are additionally enlarged by adding certain derivations. Okay, so again the classification problem, but for a particular type of algebra, they could do it. Okay, now number theory. This is algebraic number theory as Dalavad. So fundamental theorem, fundamental problem is in mathematics is to parameterize set of finite extensions of rational field of rational numbers. That is a harder problem. So if you change the field of rational numbers by the local field, which is periodic field, QP, okay, then one can ask whether we can characterize all the finite extensions, how Galois extensions in some sense, how one can parameterize. Okay, the tamely ramified extensions of local fields are easy to parameterize. Some years ago, the Dalavat gave a canonical parameterization of the set of degree P extensions and derived Sayre's mass formula in this case. More recently, he has been working on extending this result for the set of all primitive extensions. Okay, so this is a kind of classification problem once more. Okay, additive number theory. That is algebraic. This is more of combinatoric, so one can understand what is the problem. Given an integer k, the problem of finding k additive basis for the set of non-negative integers has been important problem in additive number theory. This means what? Given a set A, whether we can able to write every positive non-negative integers as sum of k elements from this set, given set A. That is a kind of additive basis. Okay, why this is important? Because very old conjecture of Goldbach, which says that every even number can be written as sum of two odd primes. This is if you start looking at computation. Okay, so the 6, 3 plus 3, 8, 5 plus 3, 10, 5 plus 5. You can go on. You can keep on, but this is the statement we need to prove. 1600. Nobody could prove so far. Okay, Goldbach conjecture is still alive. So this kind of additive problems are, people might think that addition is easy to understand. No, actually multiplication is easy to understand. Addition is the most hardest. Why? Because if I give two primes, I can multiply. I know the prime factors are going to be this only. If I add two primes, I don't know what prime factor is going to come. That is why all the number 3 problems are in trouble. The Goldbach problem is really based on that difficulty, I mean, in the sense. So these are the additive problems. So we will be interested in every natural number can be written some particular summands or not. So for instance, even classically, Lagrange proved that every integer can be written as sum of 4 squares, then 9 cubes, then 19 fourth powers. This is a theorem of Balu. That's the reason I was trying to say this is a Warring's problem. And from how manyth, I mean, if you fix the k greater than or equal to 7, number of minimums number of summands needed to cover all the natural numbers. This is what Waring conjectured. What is that exact number? Again, this is the Indian contribution. S.S. Pillai in 1930, he proved for k greater than or equal to 7. The main leftover part was k equal to 4, which Balu and Deshwe proved in 86. Okay, so this is also additive number theory. This is I have not written it here, but that is part of the major Indian contribution. Okay, so D.S. Ramana and Gyan Prakash and his students, they were working on this kind of additive basis problem. Okay, and they were looking at, in fact, sum and product kind of. Okay, I'm not getting into sum and product. They sum as well as product. It will be twisted. Okay, I have also worked before on this type of number theory. Okay, so we given a abelian group. I don't know group. Everybody knows abelian means just commuting elements. Okay, so given a abelian group, you can always attach some combinatorial invariance. So one has to know what is that exact value of that. Okay, so in that there are two conjectures some time back I have proved along with my collaborators. Okay, I am not getting into because I have to go more. Okay, so this is a new addition to HRI mass group, Aprameyopal. His area is Iwasawa theory. The Shimura-Taniyama conjecture, everybody possibly would have heard about Fermat-Law's theorem, x power n plus y power n equal to z power n has no integer solution when n bigger than 2. N equal to 2, this is Pythagoras theorem. So to prove this particular Diophantine equation, it was a long story. It's Fermat wrote it in 1700, and it has been going on. In 1996, Wiles and Taylor they proved this particular problem. That is the one he is talking about. Shimura-Taniyama conjecture. This Diophantine problem has been converted into elliptic curves problem, and that is converted into kind of representation theory problem. This is a conjecture on representation theory. Okay. Every elliptic curve is modular, kind of over Q. So Shimura-Taniyama conjecture is one of the fundamental conjecture in arithmetic geometry and number theory. The study of arithmetic of elliptic curves depends heavily on the fundamental theorem of Wiles and Wiles-Taylor, Taylor-Wiles, anyway, on Shimura-Taniyama conjecture. Employing the results of Deligne, okay, so this one can form two-dimensional Galois representation associated with an elliptic curve over rationals. The Shimura-Taniyama conjecture can then be seen as a special case of Langland's program. In the sense, whatever Shimura and Taniyama conjecture, another Canadian mathematician Langlands, he has seen the whole picture in much more generality. This falls the dimension 2 case, kind of. So therefore, if one wants to kind of continue in this line, one has to really understand what Langlands has suggested. So that's what it says. So it is imperative to know more about Langlands correspondence and more generally. So other than GL2, I mean, other than two-dimensional case, this Langlands program is not well understood. So our knowledge is quite limited. Okay, so this is a technical thing, which what it says is in order to understand something more, one has to come to local. Means if I have to study integers, it is enough to study in some sense about prime numbers, because every integer is kind of comprised of prime numbers. So this is but this is not, this local is something different, but this is a localizing. Around primes, if you can study the same concept, whether we can study the global. That is the concept. So one of Aprameyo's Paul research interest lies in dealing with Iwasawa theory of multivariable phi gamma modules. Phi gamma modules are coming from Fontaine's notion. Okay, so to deal with Langland's program. Okay, which are expected to arise naturally in periodic Langland's correspondence of higher rank reductive group. Okay, this is the last of transcendent number theory. In 1844, Cantor, using just counting argument, he proved that almost all real numbers are transcendental, but he could not give one example. He could not produce. Almost all we know in the sense of Lebesgue measure. It's a measure kind of, except for a thin set. A real number, almost all are transcendental. Transcendental in the sense of like E or pi. This will not be a root of equation over Q. Okay. So, however, given a real number, it is hard problem to determine whether it is a rational or not, first of all. Forget about transcendence. Given a real number, we don't know whether clear-cut algorithm is not there. It is going to be rational. It is going to be rational, kind of. So, for instance, everybody knows the summation zeta values, Riemann zeta function, odd values. It's supposed to be transcendental, all odd values, but not even we know all the numbers are going to be irrational. Oh, very difficult question it is. So forget about algebraic numbers are transcendental, but rational itself harder question. The irrationality itself harder question, but transcendental is much more generalization. Okay, one nice approach. The techniques are very few so far in 1800 onwards, because somehow this is very hard. Though we know almost all. In number theory, if it is thin set, we can understand. We may think that we may not be able to understand. If you know more elements, we may understand. No, this is not true always. Most of the time, the plenty of elements will be there, one particular set. We don't understand anything about the set. But something very thin set, we will know everything about it. Somewhat contradictory way it is. Okay, so one approach is very interesting, is a rational approximation technique. Because if you see real numbers, any two real numbers, there will be in between, there is a rational number, A by B, it will look like. This is kind of approximation. This approximation has been studied more, and the generalization is called so-called subspace theorem. Recently, along with my former student Vikesh Kumar, we proved the Ross theorem in a multi-dimension generality. Roth proved a stronger version of this rational approximation, which fetched him Fields Medal. Of course, not our work going to fetch, because this is ideas are same, but we could get much stronger results. Okay. Okay, so as an application, we can obtain transcendental criterion as well. Okay.
Questions? Okay, the question is that, are there only a few conjectures made by Indian? If yes, why?
Are there
only a few conjectures made by Indian? If yes, why?
No, we have many conjectures as well, but I have not mentioned it in this short time.
Okay, so
Yeah, so
this question is
of course,
from
no.
IGCAR. This question is from IGCAR. Can I answer on paper?
Yeah.
There are many conjectures made by others have been proved by Indians.
Okay.
And so also Indians have made their own conjectures which are not yet proved by others. As a chairman, I can give you this answer. Don't put India so behind.
No, it's not. Okay. Oh, one reason maybe. Okay, so that when they popularize, it becomes so popular, we have to attack that problem. That is the reason, maybe.
Yeah. So.
Okay. Yeah.
I'm just curious to know how old is the culture of doing number theory in India? Did it start in the later half of the British period or even earlier? I'm talking about number theory only.
Well, much before, in the
Yes.
sense, no, it is known, very well known because of Ramanujan.
No, that is much later, right?
Much later.
Much later. Before that.
Previously, Kerala, that
Yes.
algebra is more.
That is true. But there was a discontinuity. I'm talking about somehow number
theory. No, it is progress is less.
Are you referring to the discovery of zero?
No.
No, those things are kind of.
Those things I'm not talking about. I'm talking about the way you see that you look at science in other respects. I mean, physics or chemistry. The culture of doing it at a mass level, en mass. I mean, it started during the colonial period. I'm just curious. I mean, some pockets in southern parts of India, like in Kerala or in Tamil Nadu, I mean, they have been working on number. I mean, this was my my idea, but maybe I'm wrong.
At least
that's nothing that.
No, I didn't hit upon because Ramanujan onwards, yes, because he created the kind of spirit.
Yeah.
After his success.
Okay.
Before that, possibly it is there, but not as many.
Not well documented,
not
perhaps.
well
Yeah.
known.
Okay. Yeah. Okay. From the Madhavan school till that time, there was a discontinuity. Yeah. Okay. Thank you.
Any more questions? I have one question. You mentioned somewhere about translation invariance and modulation invariance.
Yes, sir. That is
I do understand translation invariance, but what is modulation invariance?
I have to ask Ratna, sir.
Okay, so you ask him and you let me know later on.
Yes.
Yeah. I know modular invariance, but I'm hearing for the first time.
No. Modular invariant is something different.
No,
I can answer.
I know, yeah. But modulation invariance, something
this is like a translation, some other operation. This is what roughly I understand.
Once I know the operation, I can understand that.
Yeah, okay. I will let you know, sir. I will let you know.
We'll do it.
Yeah.
Okay, so let's thank
Professor
Thangadurai for his explaining all the mathematics activity going on at Harishchandra Research Institute. And I'm seeing already the audience number of seats is much less than number of seats vacant. And but still we have one more lecture to go. So let's quickly invite Professor Arup from VECC, Engineering Science in Lab, to be talking about. I request people not to go away at least till the end of the talk.
Hello, everybody, and probably it's time to say good evening. And good to still see some audience. And to appreciate your presence, I'll try to make my presentation very simple so that it doesn't go over the head. But still, I believe I'll not be able to make happy everyone. So for those who want to know more, I have put my email ID there. So please do contact me. I'll be very happy to provide further information if necessary. So I'll be talking about the research opportunities in variable energy cyclotron center. Oh, very good to know, sir. So I'll be talking about the research opportunities in Variable Energy Cyclotron Center, Kolkata, in engineering science. And these are the research goals of our center. First is basic sciences, where we indulge in experimental research in low and high energy nuclear physics using accelerators. And also we have a strong theoretical nuclear physics group, especially in high energy. Accelerator-based applied research in the field of material science and radiation damage studies. Then I'll go to the rightmost column, technology development, that is primarily and totally engineering science, but let us come the middle two, that is the accelerator research, indigenous accelerator development, and R&D on advanced accelerators. And the other part is accelerator applications like medical cyclotron for isotope production. Now, for both these accelerator-oriented goals, you need a lot of engineering input, because if you design an accelerator without the engineering considerations, your accelerator will never see the light of the day. So it is very important we have the rightmost column, that is the technology development in the field of RF, superconducting RF, detectors, data acquisition system, instrumentation, power electronics, mechanical engineering, cryogenics engineering, and last but not the least, computer and IT services. So the accelerator research and accelerator applications, I would like to say that it has very good connection with both physical science and engineering science, and I'm an accelerator physicist myself. So, as I said, that the name of our institute is named after a machine, that is variable energy cyclotron. So let me start with the cyclotron. Just to brush up the memories, in a cyclotron, the particles, the ions are accelerated in a circular orbit. Basically, if you have a uniform magnetic field, the particles move in circular trajectory. And if you can place two electrodes within those magnetic poles, so they will be getting regular kicks if you can apply an RF potential between them. So in that way, they are accelerated using the same two electrodes again and again. And this is possible because the frequency of revolution of a charged particle in a uniform field is independent of particle speed, and it is governed by this equation. But here the assumption is mass doesn't change. So if the mass changes, you have to do some jugglery with B or as well as frequency of the revolution. So with that basic principle of cyclotron in mind, we have three different cyclotrons. The first one is room temperature cyclotron, which is operating since June 1977. So it is 44 years in operation. People who are in the field of accelerators, they should appreciate keeping a machine operating for more than 44 years with sustained performance is a very challenging task. And I'm very happy to share with you, we are doing pretty well. It accelerates alpha, proton, nitrogen, oxygen, neon, and recently it has accelerated sulfur beam also. It is special because sulfur, you start with solid as the feed material. For the other is the gaseous, is a gas which is the feed material. Next we go to superconducting cyclotron. It has extracted beam in December 2020. We have extracted already nitrogen at 252 MeV, neon at 360 MeV. Oxygen, it is in yellow color because right now we are tuning it. It has reached almost the extraction radius. It has not yet come out of the cyclotron. So probably within a day or two, we'll get it. And this white color energy is what I am showing here. These are the next goals. Hopefully within next 2 to 3 weeks, this will be achieved. So it is not those discrete energies experimentalists will get. So for example, for nitrogen, we will get all the energies between 252 to 270 MeV. And it will be available to the users probably from a period, say, by the end of this year. And finally, we have the medical cyclotron, which is a fixed ion machine, that is a proton. It can provide 15 to 30 MeV proton, but the beam current can be quite high. it can reach as well as maximum as 500 microampere. So it looks like we have 2 or 3 cyclotrons. So people do not really appreciate unless you pinpoint. It looks like all are similar machines. No, all machines are different, and the challenges are also quite different. First point I want to drive at, when you want higher energy, you need higher magnetic field. So for example, room temperature cyclotron, which provides comparatively lower energy, so that for that we need only magnetic field of the order of 1.7 Tesla. But when we are going for higher energy, we need very high magnetic field of the order of 5.8 Tesla, so you need superconducting magnet. That is a totally different technology. Then for medical cyclotron, again, it is a room temperature machine, only proton, 30 MeV proton, so the field is again less, 1.7 Tesla. So for higher energy beams, higher magnetic fields, 5.8 compared to 1.7, and the compact, here it is the pole diameter 2.24 meter, where it is almost half 1.42 meter, although we are getting much higher energy. Then another aspect is for accelerating different ions, different profiles of the magnetic fields are required, because mass does not change in the similar fashion when we are accelerating the particles to higher energy. So you have a main coil which provides you the average magnetic field, over and above which you have series of trim coils. I have shown it here. So for example, room temperature cyclotron, we have 17 pairs of trim coils for fine tuning of these magnetic fields. For superconducting cyclotron, we have 13, but medical cyclotron, it accelerates only one particle, so there is no trim coil, there is only one main magnet coil. RF, when you want different energy of the machine, RF systems become very complicated because you have to vary the frequency, both the frequency of the RF transmitter as well as the frequency of the RF structure. So here I'm showing you the RF structure for the room temperature cyclotron, the RF panel and the D. So in order to change the frequency, this top panel and the bottom panel, it closes and expands. It is a huge mechanical structure. For superconducting cyclotron, this is the structure on the top and the bottom, and the structure extends almost 12 meters from the median, measured from the median plane. And that is quite a lot of engineering challenge. So for variable energy ions, variable RF frequency requires very complicated RF technology. So although the 3 machines are same as our cyclotron, but they're quite different, and the challenges are also quite different. It is not that our center has expertise in cyclotron only. So that, to see that why we need other accelerators, I'll just touch upon this slide. Is there any way that we can get rid of this thing so that the slide is visible, whole slide? Is it on? Yeah, it's good. Yeah. So in variable energy cyclotron center, we have another facility we have developed, which we'll call rare ion beam facility. In cyclotrons, what I've been talking about, we are talking about accelerating only stable ions, means beta stable ions. So for example, here I'm showing you, suppose you have 14 nitrogen, 15 nitrogen, 16 oxygen, 17 oxygen, 18 oxygen. So these are all stable elements. So if you want to accelerate those are called stable beam accelerators. But then when you are going away from these black rectangles to the outside, which are the beta unstable nuclei, and accelerate them and provide those as ions, that becomes rare ion beams. So if I magnify the scale, this is the whole nuclear chart, you can see the number of black dots are very few, but when we'll be accelerating those unstable beams, the number of available beams will be increased enormously, and that provides much more flexibility in the planning of experiments. So that is the new trend, that is the rare ion beam facility that we have developed already in VECC. And in order to do so, as I said, that these are beta unstable nuclei, so you do not have it in a cylinder or in the form of a solid material, you have to first produce it using a primary beam accelerator. So that hits the target that we are calling it RIB production target. So the lot of reaction products will be coming out. You feed them to an ion source. And after the ionization process, you select a particular isotope which is of interest to you. And after this, we are having RIB of the order of energy, typically 1 to 2 keV per nucleon. And these RIBs are useful at this energy even for material science research, but for nuclear physics research, you need much higher energy. So you use a series of ion accelerators. Why I'm telling you all these stories? Because the maximum number of RIBs is determined by this equation, I primary, NT, sigma, and eta, where NT is the number of target atoms here, sigma is the cross-section, and eta contains all the efficiencies like efficiency of acceleration, efficiency of ionization, everything. So you need accelerators which is highly efficient. Cyclotron is a very good accelerator, but overall efficiency of cyclotron is not that good. So one goes for linear accelerators. So in VECC, we have developed lot of linear accelerators, and this is a list of that. So first we have developed heavy and radio frequency quadruple. We have 2 of them. The first one accelerates from 1.38 to 29 keV per nucleon. Second one accelerates to this energy range. We have 5 IH type of linear accelerators, and I have shown here the energy values. So after the 5th one, we'll be reaching around 1 MeV per nucleon. We have lot of rebuncher cavities, which are designed for these different energies. Rebuncher cavities are nothing but linear accelerators, but that does not provide you any acceleration. It basically ensures that the longitudinal bunch length of the beam is within your control. So we have already developed all these accelerators. So we have we are in equal comfortable zone, whether it is a cyclic accelerator or in linear accelerator. But then the next thing comes. For example, take us the case of RFQ, which accelerates from 1.73 to 98.8 keV per nucleon. It requires around 40 kilowatt of RF power. And then the 5th LINAC tank, it takes energy from 717 to 1038 keV per nucleon that requires almost 25 kilowatt of RF power. And in order to produce this much of RF power, you require almost double of the wall power. So the power requirement of all these accelerators is very high. And that is one of the bottlenecks for any accelerator project. So when you are going to higher and higher energy, people go for superconducting technology. So we have started working in that also. And I will just share a few slides to show how we are doing. The first one is a superconducting electron LINAC. So this will be used for the production of RIB using photofission route. The design acceleration gradient is 10 million volt per meter. This is the layout of that, out of which there will be total 3 superconducting accelerators. The first one will have 1 9-cell cavity. The next 2 will have, each of them will have 2 9-cell cavities. So this is the, for any such superconducting cavity development, you go in steps. The first step was development of single cell cavity. This is a picture of that. The next one is the development of the 9-cell cavity. This is a picture of that. This 9-cell cavity will go into the cryostat, which is shown here. And beam has been already successfully tested to 10 MeV using 1 single 9-cell cavity. And this project is being done in collaboration with Trump, Canada. So we have already developed 1 superconducting electron LINAC accelerator, and now we are commissioning it in our center. Next, superconducting proton LINAC. Here the difference is the earlier one which I described, that operates at 1.3 gigahertz. This operates at 50% frequency, that is 650 megahertz. It is designed for beta is equal to 0.61. This superconducting proton LINAC is designed for PIP2 project of Fermilab as a part of IIFC collaboration, in which VECC is also a part. There we have already developed 2 single cell cavities. This is cavity 1 that reached 30 million volt per meter acceleration gradient. Cavity 2 reached 25 million volt per meter acceleration gradient. Sorry. And the operating gradient is 19 million volt per meter. So it has exceeded much more what is the design gradients are. And VECC has fabricated these single cell cavities, but we don't have the electron beam molding setup still. The electron beam molding was done by IUSC New Delhi, and the cavity processing is another very complicated thing that was done at Fermilab. And now the next step, that is the final goal for this 650 megahertz cavity, is this 5-cell cavity. So this 5-cell cavity, this is what you are seeing. I'm showing you is the copper prototype. So that has been already made, and the RF measurements have already been done. And the niobium cavity is under fabrication now. So this is the picture of niobium cutting using electro-discharge milling machine, formation of the niobium half cells, and this is coordinate measurement machine. So after the forming, you check the dimensions, and these processes are going on. So in the superconducting regime, I started with electron accelerator, then I showed you proton accelerator. Now I'm coming to heavy ion accelerator. The structure here is quite different. The earlier two was elliptical cavity. This is a different type of cavity that is called quarter wave resonator. It looks like this. It has got it is like a cylinder, and from the center there is a another cylindrical shaft. So there is a hole here. There is one projected tube from here and another projected tube from the opposite side. So you have two accelerating gaps. So this is one single quarter wave resonator. There will be 4 such quarter wave resonator, 1, 2, 3, 4. And at the center, there will be a superconducting solenoid for transverse focusing of the beam. And this is the whole thing will be hanging from the top. And only the outer enclosure I have not shown here for clarity. So 4 such resonators have been already built. All of them has exceeded the required operating gradient of 5.5 million volt per meter. I'm showing here just one picture of that. You can see we can safely operate it up to 6.5 MV per meter. Now, I'm just shared with you that we have expertise in cyclotrons, in linear accelerators, in superconducting accelerators, whether it is electron, proton, or heavy ion. Any such accelerator activity starts with physics design. And in the initial level of the physics design, you assume a particular field profile, and you determine the shape of the separation and the length of the drip tubes so that the ions are accelerated properly in every gap. And you do a preliminary beam dynamics for which you have to use different types of codes. We have those codes, and sometimes in critical cases where those codes are not sufficient, we write our own codes. These drip tubes should not hang in the air, so you have some supports which we call it as a drip tube stem. Then the next structure I'm showing you is the drip tube base. Finally, this is what showing are called ridges, and this whole structure, what I'm showing you, after drip tube, whatever I'm showing you, there the mechanical considerations become very important because the structure should be rigid. It should not vibrate during operation. You have to have internal cooling channel, so you have to have sufficient space for that. How we have to fix them, all these considerations go there. And then the whole thing goes inside a vacuum enclosure, we call it cavity. Now here another set of simulation starts, which we call RF simulation. So there you try to determine each and every dimension of the cavity to get the desired frequency, and you try to reduce the power consumption in the cavity. These are done by commercial codes. Examples are Microwave Studio, NCs, COMSOL, HFSS. We use all of them. Some researchers have some preference, some others prefer some other code. And finally, after this RF simulation, you get almost close to the actual field that the particle will see. So the final beam dynamics, which is hiding behind me here, is done using this particular RF field profile. So that is the final stage of beam dynamics calculation. After that, you come with the mechanical engineering simulation, because you have to see when you give the power, what will be the temperature rise, whether at proper places you have provided proper cooling or not. There are cases that if you forget to provide the cooling, the things will melt, or maybe that will work like a heater for your cup of coffee. So you have to do very important consideration for that we call at thermal or thermomechanical simulations. Here we are considering the deformation of the cavity. That is another very critical component. Typically, for this particular LINAC, from beam dynamics, it turns out that all the drip tubes should have an alignment error within 100 micron. Now, if all these components are fabricated, they have their own fabrication tolerances. But finally, you have to achieve that tolerance, and that tolerance should not be affected during operation when, because of the thermal effect, there will be deformation. So you have to, all these considerations go into the picture. So finally, these are the steps for the design of any accelerator: physics design, preliminary beam dynamics, optimization of the RF structure, final beam dynamics with RF fields available after RF simulations, thermal and thermomechanical analysis with RF heat load, cold model fabrication, measurement and design of the fine tuning, actual cavity fabrication, alignment and leak testing, low power RF measurements, high power RF conditioning, and finally commissioning. So people who are from different fields, who cannot appreciate why it takes so much time. It takes so much time because these are the steps involved. And then what I have not included here is the almost undefined step of finding a suitable vendor and getting it fabricated. Then I'll talk about some other parts. So I have covered the basic parts of the accelerator. Now, accelerator doesn't work alone. The first, it has to get its own ions. We have different types of ions in our laboratory. The first one is a penning ionization gauge PIG ion source we are using from 1975. ECR ion source 1992. Incidentally, this is the first ECR ion source of our country. Then another ECR ion source we have built in 2017. So these are the three ion sources we are using for room temperature cyclotron. For superconducting cyclotron, we have a commercial ion source, Hypergun from Messrs. Pantechnic, which we procured in 2007. For online isotope separator facility, we have surface ionization source and hollow cathode type of arc discharge source, indigenously built. We are operating since 1988. For rare ion facility, we have 1, 2, 3 different ECR ion sources, but I don't have the time to go into that. All of them are different. And right now we are working on medical cyclotron, where we have multicast ion source. So because I have told about so many ECR ion sources, I have one slide for ECR ion source. This is how the ECR ion source work. Basically, for any ion source, the idea is you have to create a plasma. And if you can create a plasma, and if you can feed your material you want to ionize within that plasma, it will be ionized. The efficiency you have to optimize. Now, in order to confine that plasma, you have to have magnetic fields. And you need confinement both in the radial direction and as well as in axial direction. For ECR, the axial confinement is generally done by 2 solenoid coils. I'm shown here in this diagram. And the radial confinement is done by hexapole, shown here. So because of this, what will happen? The electrons will move in a circular path, but they will do just like swing in between those two maximum of the solenoid field. And in the radial direction, it cannot go beyond a certain level. So in that way, you confine the plasma within a small volume, and you feed microwave power at the same frequency, that is the ECR frequency, we call it, determined by this equation, 28 gigahertz by TT is the field. So ionization takes place and the ions are extracted using DC potential. So this is how an ECR ions work. And the configuration of the magnetic field differs from one source to another. The next and very important part of, especially for cyclotrons, is magnet design. So I have shown here the magnet for 3 cyclotrons, that is the room temperature cyclotron, superconducting cyclotron, and the medical cyclotron. So you can see this is code simulated using Opera code. It is reasonably okay to design a magnet, but the question is, when you have to design a magnet with a very high accuracy, you need a lot of expertise. Why I'm telling you? Because in cyclotron, ultimately all these shapes what you are seeing, these are not the artistic shapes. This has come from detailed beam dynamics simulation. And ultimately you have to arrive the simulated field within 0.1, 0.2% accuracy. And if you cannot do that, your beam will not be centered. There will be loss of beam. So you have to have a very reliable magnet design. And that requires very special effort and expertise. We have learned that in the course of designing all these cyclotrons. Designing magnet is not only enough, you have to have very accurate magnetic field measurement system. We have a 3-axis magnetic measurement system using Hall probe, which is important for dipoles to determine the field uniformity and also the fringing field. We have probes with an accuracy of 0.01%, because if you need a field accuracy of 0.1%, your measurement system should have higher accuracy than that. And this Hall probe is calibrated up to 2.2 Tesla. We have a rotating coil bench, which is important for quadrupoles to determine the field harmonics. We have NMR probe, which is used primarily for the calibration purpose. But then this list is not exhaustive. This does not do your entire job. Hall probe, as I have said here deliberately, it is calibrated up to 2.2 Tesla. But for superconducting magnet, we have a field requirement of 5 Tesla. So when you are trying to determine field of a very high field superconducting magnets, you need some special technique. So this is shown here. We have done in the case of superconducting magnet, we call it search coil technique. So basically, you have to have a bench which can, through which a search coil is moving along the radius, and you have the option of rotating that bench so that in any azimuth and in any radius, you can take the data. So in our system, we can move the search coil from -50 to 685 millimeter in radial direction in 2.5 millimeter steps. Position readout accuracy is less than 200 micron. We can take full 360-degree map at 1 degree azimuthal step. The angular readout accuracy is 1.7 arc second. I'm mentioning these numbers because these numbers are very important. Because unless you know accurately the coordinate of your search coil, that data does not help you much. And the motor and the electronics was 2 meters down of the median plane, because otherwise those will be affected by the magnetic field of the superconducting cyclotron. So we have this measurement system also. Then another very important part is the power supplies. Ideally, would like to develop all the power supplies ourselves, but there are are too many. So we develop only the power supplies which are critical in nature. For example, the first one I'm showing you here, there was a criticality. We needed a high current power supply, but there was a severity of the water supply. So we wanted to develop high current power supply, which should be totally air cooled. And so this power supply have been developed. It is a current stability 100 ppm. This is true bipolar steering magnet power supply, ±5 ampere. High voltage DC power supplies, these two power supplies are used typically for ion sources, extraction voltages, etc. This is a special technique, resonant or soft switching power supply. This we are using for ion source extraction voltage. Then we have high voltage and high current power supply. 0 to 20 kV DC, we add 20 ampere maximum, and it is a floating type of power supply. This is a picture of that. That also we have developed. Design and development of RF systems, because any accelerator needs a lot of RF transmitters. So we have the capability of electromagnetic simulation of RF cavities, couplers, etc., using codes like CST Microwave Studio, Particle Studio, HFSS. We have developed solid-state RF amplifiers up to 10 kilowatt at around 75 megahertz frequency. We have designed and developed tetra-tube-based RF amplifier up to hundreds of kilowatt of power. We have developed high-power IoT-based amplifier for high-frequency application. And all these RF systems require low-level RF design and development for your amplitude control and phase control. We have expertise in that also. And we have all the requisite infrastructure for doing this type of research, like network analyzer, spectrum analyzer, vector voltmeter, signal generator, etc. These are some of the picture of those RF transmitters. These are IMAC tetra-tube-based RF amplifier for cyclotron. And I have 5 minutes, right? Oh. Can you give me 5 minutes? I missed the bell, actually. We have, for any accelerator, the control system is another integral part. We have APIX-based control system, where which operates all the cyclotron and all these control parameters. It operates almost 3,000 parameters. These are offshoots of technology. We have a digital picometer, which can measure current in this range. We have a mini picometer. This is a specialty that it works under high vacuum. We have RFID-based library management issue and return system. This is used in these 3-4 different institutes all around India. These are some of the topics on which our present PhD students in engineering sciences are working. Studies on plasma cleaning technology in the field of accelerators. Design studies on RF system for accelerator application. FPGA-based multi-channel digital data acquisition system. Development and optimization of SPECT imaging system. Development of ultra-low bit video compression system. Development of algorithm for migration of swarm robots. And development of Indian Sign Language to spoken language translator. I will take 4 minutes only. These are the final part of my thing. So we are supposed to talk about something about the recent research achievements. This is a medical cyclotron, which was commissioned by VECC. Since June 2020, we are producing FDG on a regular basis, even in the lockdown days. And we supply it regularly to nearby hospitals around Kolkata. Recently, we have developed the radioisotope sodium fluoride prepared using this 18-fluorine. The commercial production started in January 2021. It is a replacement of 99 MTC MDP. The Bonam tech is considerably higher, so it provides better image quality, increased clinical accuracy. This is a picture of that, courtesy Command Hospital, Kolkata. We have developed recently 201 thallium, thallus chloride, that is used for SPECT studies. The commercial production will start soon. We have supplied it to 4 different hospitals. This is an image of biodistribution carried out at Rabindranath Tagore International Center of Cardiac Science. Recently, we have produced 68 gallium, and there we have supplied it to these 3-4 hospitals. And this is a picture from Netaji Subhash Cancer Hospital. You can see how clear this picture is. This is the indigenously produced gallium 68% available commercially for human application and will help common people in prostate cancer diagnosis at affordable cost. Looking at the requirements, we have started developing an 18 MeV 50 microampere H- cyclotron. The first part of is the beam injection system, which involves an ion source. We have already developed a cylindrical cusp ion source, tested up to 300 microampere, goal is 2 milliampere. We have already designed the magnet. This is a simulation model. The fabrication will be done by BRC. This is a project jointly with BRC. The iron and copper coil procurement is in progress. This is the RF system. This has been already designed. And this is the final stripping mechanism and the beam extraction system. And this is the mechanical design of the movement of the stripper system. Finally, we have also recently commissioned on 1+ ECR ion source. I showed this slide earlier. Now here, what happens? You need, instead of one ion source, 2 ion sources sometimes in cascade you have to use. So this is a picture of that. So this is the 1+ ion source I'm talking about that will be used for ionizing RIBs immediately after the target. This is a picture of that. It has been commissioned recently. It is a totally permanent magnet-based ECR, and the beam current measured at the Faraday cup after ECR is 1.6 milliampere. It has been also commissioned recently. So last slide. Thank you for your kind attention. And I acknowledge the scientific and engineering contribution of my VECC colleagues and other collaborators. Thank you so much for giving me this time.
Any short questions? Yeah.
Limits.
I mean, yeah, because you can have more magnetic field superconducting magnets that can give more
No.
field.
So you can look it like this, that from an ion source, it goes like this. You have a certain number of ions in your mind, and you know what is the expected charge state of that. And for those charge state, what is the magnetic field required, you determine that. So from there, you determine what is the magnetic field maximum is required. It is not that we cannot reach beyond that, but that is what is our design requirement. It is not for any limitation. I don't know whether I could...
But can I think of that? Because I know that the more you have magnetic field, you can have more energy because it is nothing, it is just...
Yes, but then more complicated the technology is. It is K500 machine. So then after this, probably when you go for K1200, you'll need much more higher field. So yeah, but you have to go in steps. Okay. In the K500 machine, this field requirement is the optimum field requirement.
All right, thank you.
Any other questions? Yeah.
So I think that was almost a magical talk. Thank you very much. Since I come from the Tata Hospital, I have sat in all these meetings where we were trying to negotiate with people for the LINAC and also for other kind of cyclotron for treatment, at least for radiation delivery for the patients. So maybe I'm naive. Are these meant for such applications, and can you produce machines of that kind that can be applicable in hospital?
Can you be a little louder?
Can you hear me now?
Yeah.
Okay, since I'm from the Tata Hospital, I was wondering whether your linear accelerators can be made applicable for radiation therapy for the patients. And is that one of the applications of these? And is it practical to see these in production for hospital use or at least for testing?
Yeah, I think she's the head of the RIB. She'll be the appropriate person to answer this question.
So if I have understood you correctly, so basically you want to know whether...
Madam, you have to be louder. So that,
whether these linear accelerators can be used for therapy or not, or these accelerators. So basically for proton therapy, if you are talking, you need energies of about 250 MeV or higher. For carbon therapy, you need further higher energies, typically GeV level. So mostly people are using either cyclotrons or synchrotrons for that. So basically, the starting point is the same technology. So you use the same technology of cyclotrons for making therapy cyclotrons, and the RFQ and LINAC heavy ion, what he has explained, is basically the injector for the synchrotron, which is used for therapy. So these are basically initial building blocks. But of course, we have to build further higher energy machines to reach those energies that are required for therapy.
Yeah, madam, in that way, I can just add one point. I am somehow more integrated to the cyclotron part. So right now, seeing the requirement of the medical cyclotron, the department has already approved us project for 18 MeV cyclotron. And I showed it very quickly. Our target is around 2024, March 2024, we should be able to complete it. So that is our first target. In the same project, after this, we are going around 30 MeV cyclotron so that you can produce some other isotopes, which is not possible with just this 18 MeV cyclotron. And then we have that therapeutic machines in our mind. But you know, you cannot jump at one go. We have to go stepwise, because research accelerator and these medical accelerators are different league. In my institute, we are having engineers and scientists. If there is a problem, they can go and rectify it immediately. But when we are giving it to the industry, that should be foolproof without much failure. So that is that reliability becomes a very important factor there. So that is a new regime in which we are working now. We'll go stepwise. But surely what we are telling, that therapeutic type of machine, that is also we are having in our mind. This much I can tell you.
Okay. Let's thank Professor Bhattacharjee again.
Thank you, sir.
Beautiful explanation about cyclotron technology. I think that the end of the scientific talk for today.
Thank you, Professor Panda. On behalf of HBNI, I thank the three speakers of this session, and once again, thank all session chairs and speakers for giving a stimulating start to DI MBS 2022. If any of you have missed the previous presentations, please be assured that all the talks will be available to you all the time on the YouTube link. We hope to meet you again tomorrow by 9:30 a.m. for sessions 5 to 8. Thank you and have a good evening. I have an announcement for the delegates staying in training school. A bus has been arranged outside to take you back to training school. From there, another set of buses will leave for the dinner venue